So let's start with GATE DA course. So this is the first module of GATE DA course is probability and statistics, and the first concept in that is counting. First, like, what is the motivation of counting? Why do we count? So we want to do ML, right? We want to do ML and AI, and these are standard problems. You can get these problems even in the aptitude section. Doing this problem without breaking it down like this is impossible, okay? Permutation is nothing, but in how many ways can you arrange objects? I lost marks in GATE, I remember, okay? But just because of this mistake. With repetition or without repetition, okay? There is just one out. Why probability? Why? Because we cannot be sure of certain outcomes of certain events. Basically, whenever you call an event in terms of probability, you will have a universe. So basically, you will be doing an experiment. Independent events is a big topic. Most of the questions in probability comes from conditional probability and independent events. Hi everyone. So let's start with GATE DA course. So this is the first module of GATE DA course is probability and statistics, and the first concept in that is counting. So we will finish counting first, and we will put every video of counting in a playlist, so you can access them all in the same playlist. This is lecture 1, and we will discuss rule of sum and product in this session. So first, what is the motivation of counting? Why do we count? So we want to do ML, right? We want to do ML and AI, and we will have data sets of large quantity. We will handle large numbers of data. We will have large amounts of data. And one good example is let's say I have 1,000 entities of some kind, and I want to do some sort of pairing. Okay, so let's say I want to keep object A and object C together. So how many different ways of pairing are there? Walmart used this problem. Okay, so if you know about it, it is called associative learning. So back then, what happened is in every grocery store, if you see in US, items were placed here and there. And generally, in India, we still have shops. We go to a shop and we ask for an object. I want, let's say, toothpaste, right? And they will bring it for you. You have to mention the brand and the toothpaste name. Walmart was the first store with what they did was they removed the shopkeeper concept and they made the store free, right? You just go in there and pick objects, whatever you want. And they had large amount of profits. It's the number 1 company in retail right now in world. And what they did was they did a beautiful thing, associative learning. They kept bread and butter together. Very easy concept, right? They just understood what are the things which people tend to buy together. Pen and pencil together. So all stationary items together. Nowadays you see it in every mall. But think about it, small problems. But where does counting fit in? Let's say I have 1,000 items. How many different pairings or triplets do I have? So that's a math problem now. So it's that's where we will need the concept of combination, permutations, and counting. So that's the motivation. In ML problems, generally counting all possible ways is what you will need in day-to-day life. So yeah, many times one needs to calculate the number of all possible outcomes for a series of events. You're doing some task and then some task and then some task. In how many possible ways I can accomplish my goal, right? So that's counting. For example, we know that in India we have 10-lettered PAN numbers. So in how many ways we can generate 10-lettered PAN numbers such that the first 5 letters are capital alphabets, next 4 are digits, and the last one is again a capital letter. So this is a counting problem. And in most of the times what happens, counting might go astronomical. So astronomical numbers are huge. They so for example, if you want to see the distance between sun and earth, it will be astronomical, right? It's in 10 to the powers. So counting can go astronomical, and that's where ML will come in. So you have a large space, but you want to just go and hover over a small space, and ML will help you reducing the dimensions, reducing the data set, and so on. So the first concept in counting is the rule of sum. So if a sequence of tasks T1, T2 up to Tm can be done in W1, W2, Wm ways. Okay, so what do we want to do? We want to perform a task T1. Let's say I want to do laundry. Then I want to do some other task. I want to cook something. Then I want to do some other task. Okay, we are doing sequence of tasks one after the other. Okay, and T1 can be done in W1 ways, T2 can be done in W2 ways, T3 can be done in W3 ways. So what we want to do is, the condition is that no task can be performed simultaneously. They are not dependent. So I should actually remove this. There is no connection between these tasks. Okay. Let's say we will come to connection in the next slide. Don't worry. So let's say there are three tasks, T1, T2, T3. They can be done in W1, W2, W3 ways, and no task can be performed simultaneously. Then the number of ways you can do one of these tasks is W1 plus W2 plus up to Wn. So you just sum all the possible ways. So for example, in how many ways? So it's like OR. In logic, we discuss OR and AND, right? It's like OR. So yeah, T1 can be done in W1 ways, T2 can be done in W2 ways, then T1 or T2 can be done in W1 plus W2 ways. So this is the rule of sum in counting. See, why are we learning all this? Right now, straight away you don't see a use case, right? But the problem that will come will involve all these concepts at once. Rule of sum, product, permutation, combination, everything will be applied in one single problem. So you need to learn every bit and piece. Okay. So we can write it this way as well. So consider two tasks, A and B. So right now we are doing it in set notation. Okay, this is set A. This is my task A. And this is set B. This is my task B. And they are disjoint. Okay, this is very important. They are disjoint. They don't have anything in common. And A has W1 ways to do it. And B has W2 ways. So for example, 4 and 3. And they are disjoint. Then mathematically, in how many ways can I do A or B? I can just take union of these two sets, right? So what is the cardinality of union of A and B? You will have 4 plus 3, which is 7 elements. So that's just the rule of sum. Very easy. So for just see this example. There are 4 types of cookies. So just see the problem once. There are 4 types of cookies and 3 types of cakes available in the store. In how many ways can we select any one item to eat? Okay. Disjoint problems. Cakes and cookies are disjoint, and also I just want to select any one item to eat. Okay, so I'm not doing tasks one after the other. I'm just selecting one item. So I can either select a cookie or I can select a cake, right? How many different choices do I have? 7 choices, right? 4 plus 3. Sorry. So next is rule of product. Now a sequence of tasks T1 and T1 up to Tm can be done in the same W1 up to Wm ways respectively. And here the condition is different. The tasks are not disjoint. The condition is that every task arrives after the occurrence of the previous task. Now we have that sequence, okay? So we are doing T1. So you can always put rule of product in a diag like this. It's an acyclic graph. So I'll tell you how it works. So let's say I am at a start point. I want to do first task T1. Then I want to do, let's say, task T2, and I want to do task T3, and here is my ending point. Basically, you just want to calculate in how many ways can you reach the ending point, right? Now, T1 can be done in W1 ways, T2 can be done in W2 ways, T3 can be done in W3 ways. Okay, you can perform T1 in W1 different ways. With an example, it will be more clear. I will show you in the next slide. But the number of ways in which you can reach the ending point from starting point will be W1 into W2 into W3. So whenever you can put the tasks in a sequence, you apply the rule of product. Okay. So again, mathematically, we are just multiplying the cardinalities of all these sets. So consider this example. There are 4 types of cakes, cookies, and 3 types of cakes again. In how many ways can I select one cookie and one cake? So now I want to select one cake and one cookie. So here are my cookies. Let's say C1, C2, C3, C4. And cake, let's say I'm saying D, D1, D2 and D3. Okay, these are my 4 cookies and these are my 3 cakes. What I want to do, I want to select one cookie. Select one cookie. Again, in logic, what we are doing? In logic, we are doing an AND. Select one cookie and one cake. Here we don't have an OR, we have an AND. So again, rule of product. Whenever we have AND, rule of product. Select one cookie and then select one cake. And this is my ending. So in how many ways can I reach the end? First select one cookie, there are 4 ways. Then select a cake, there are 3 ways. So there are 12 ways in which I can select one cookie and one cake. What are those 12 ways? I can select C1 and D1. First cookie and first cake. Or I can select C1 and D2. C1 and D3. And so on. Last one will be C4 and D3. So there are 12 ways. Okay. Whenever you have AND, rule of product. Now let's try to solve this problem. So I'll explain the problem first. A boy lives in a town X and wants to go to school at Z point. Okay. So X is his home and Z is the school. From his home X, he has to first reach, let's say there is a bus stop or something. There is some stop which is Y. So from X he has to reach Y and then from Y to Z. And he may go from X to Y by either 3 bus routes or 2 train routes. And from Y to Z, he has 4 bus routes and 5 train routes to Z. So in how many ways can he go from X to Z? So what we want to do here, we have a boy at X and there is a station Y and there is a station Z. We want to go from X to Z, okay? From X to Y, there are 3 bus routes and 2 train routes. From Y to Z, there are 4 bus routes and there are 5 train routes. So in how many ways can I reach from X to Z? That's what the question is. Okay. So think about it. Consider this task as one. In how many ways can I reach from X to Y? So either I will take a bus or a train, or right, rule of sum. So I will take a bus or a train. How many ways do I have? 5 ways. To reach from X to Y, I have 5 ways. I can take either a train or a bus. Any 5 options. Okay. Similarly, from Y to Z, I have 4 plus 5, 9 options. 4 buses and 5 train, or again. Okay. Now it is a sequence. You have 2 tasks, right? Do X to Y and Y to Z. And right. So whenever you have and, rule of product. So you have 45 ways. So basically what you are doing, like what are these 45 ways? Take the first bus and the first bus here. Take the first bus and the second bus here. Similarly, like first bus and the 5th train, and so on. The last option will be the second train and the 5th train. So there are 45 different options in which you can achieve this. Here we are applying both rule of sum and product. Always remember, or we are applying rule of sum and we are applying rule of product. Okay. So now it's an interesting problem. It will apply everything we have learned so far. Firstly, let's try to do it like normally. How many divisors are there of 1000? Okay. So we know that 1 divides every whole number. 1 is a divisor of 1000. If you like keep going on, like counting like this will be very difficult, right? Again, like counting, it is a problem of counting. We have like 1000 numbers between 1 and 1000. How many of them actually divide 1000? So 1, 2, 4 and so on up to 1000. Okay. So counting like this might take a lot of time, right? But we can actually very intelligently apply the rule of sum and product. So I will explain the formula first and then we will solve this problem, okay? So like first try to understand this formula and then we will apply it on 1000. So whenever you want to count the number of divisors of any number, okay, there is standard way. So let's solve it using this example only. So try to do the prime factorization of 1000. What is prime factorization? Writing a number in powers of its prime factors. Writing the number in powers of its prime factors. So, okay, what is 1000? If you do it like you can do it like this also, but it's very easy. Like 1000 is easy. 1000 is actually 8 times 125. So it's 2 to the power 3 into 5 to the power 3. So again, like if you love math, this will be easier, right? So yeah, this is the prime factorization of 1000. Otherwise, you can do it this way. This is how we learned it, right? You divide it by 2. You keep dividing it by prime numbers and you'll get the prime factorization. Okay, let me do it for you. Just this once. So this is 1000. 2 divides it. So just go with the smallest prime number and see if it divides it. If it divides the number. So 2 again divides 500. So it will be 250. 2 divides 250. So again we will divide it by 2. 125. Now 2 is not dividing 125. So go to the next prime number 3. 3 is also not dividing 125. Go to the next prime number 5. 5 divides it. So 5. Then we will have 25. Again for 25 the smallest prime number will be 5. Again 5. 5. 1. So it is 2 cube into 5 cube. Okay, this is the prime factorization of 1000. So think about it. What is 1000? Okay, why am I doing all this? So there is a logic. 1000 is 2 cube into 5 cube. And any factor of 1000 will be what? It will divide 1000. So what is divisor? It will divide 1000. So this is 1000. 2 cube into 5 cube. Can 7 divide it? 7 cannot divide it. Why? Because 7 is not in the prime factors of 1000. The only numbers which can divide 1000 must have these prime factors, 2 and 5 only. And also you cannot have 4 2s. 2 to the power 4. This cannot divide 1000 because you only have 3 2s in 1000. So this is the capability of the number. Think of it this way. 1000 has 3 2s and 5 3s. So any number which is which has fewer than 3 2s and fewer than 3 5s can divide it. For example, a number like 2 square into 5 to the power 1. This can divide 1000. This will always divide 1000 because when you divide it, you will have 2 and here you will have 5 square. Right? You cannot have in the denominator you cannot have 2 to the power 4 or 5 to the power 4. So any number which can be represented in this form, 2 to the power something into 5 to the power something, will be a divisor of 1000. Now this something we know has to be between 0 and 3, and this something also has to be between 0 and 3, right? So if I just create a set like this, so just create a set for every prime number. This is a set for 2, power of 2. This is the set of power of 5. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 5 to the power 0, 5 to the power 1, 5 to the power 2, 5 to the power 3.
Excellent.
Yeah. Take any number from here, take any number from here and multiply them. That will be a divisor of 1000, right? Simple, right? So take 2 to the power 1 from here, 5 to the power 2 from here, multiply them. So 2 to the power 1 into 5 to the power 2 will be a divisor of 1000. So again, do the prime factorization, just keep them empty spaces. And any power smaller or less than or equal to this will be a factor. So how many options do I have for 2? 3 plus 1 actually, not 3. Because 2 to the power 0 is also an option. 0, 1, 2, 3. So we have 4 options for 2 and we have 4 options for 5. Again, why rule of product? I have to take a power of 2 and I have to take a power of 5 and rule of product. So I have 4 options here and I have 4 options here. So you have 16 divisors for 1000, right? So you can now actually calculate the number of divisors for any number from whatever we have learned. Cool. So this is the formula. Again, very easy to derive, whatever I did before. Let's say the prime factorization of a number n is p1 to the power e1. Sorry, here it should be p2 to the power e2, pk to the power ek, where pi are distinct prime numbers. This is how prime factorization looks like. Prime number to the power something, prime number to the power something, and so on. Then the number of different divisors of n will be e1 plus 1 into e2 plus 1 up to ek plus 1. Why? Again, same logic. This is first prime number, second prime number, and kth prime number. Here we have e1 plus 1 options. How? p1 to the power 0, p1 to the power 1 up to p1 to the power e1 plus e1. Okay, so these are all the options I have for the first prime number from 0 to e1. Again, for p2 I have how many options? E2 plus 1. How? I can take P2 to the power 0, P2 to the power 1 all the way up to P2 to the power E2. And for kth prime number, I have Pk to the power 0 up to Pk to the power Ek. So simple, take one element from each of these and we have an AND. Take an element from here and here and here and so on. So here I have E1 plus 1 options. Here I have E2 plus 1 options all the way up to Ek plus 1 options. Okay, so it is a standard problem for rule of product. Cool. Now a slightly more interesting problem comes up. What is the sum of all divisors? Sum of all the numbers which divide, let's say 1000. Okay. So think about it. We can actually do it from whatever we have learned so far. Okay. So this is the formula, very big formula, but we will derive it. Okay, it will be very simple. So let's do it on an example, then we will derive it. So again, let's take 1000. How did we calculate the number of divisors? Like we know that 1000 is what? 2 cube into 5 cube. We have to take a number from here and a number from here. So we have options for 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 5 to the power 0, 5 to the power 1, 5 to the power 2, 5 to the power 3. We know that there are 16 divisors. What are they? 2 to the power 0, 5 to the power 0. We take one number from here, one number from here, right? That's what we are doing. And what is the other number? 2 to the power 1, 2 to the power 0, 5 to the power 1. We can do this like 2 to the power 0, 5 to the power 1 and so on. The last number will be 2 cube into 5 cube. And we have to calculate the sum of all of these. Sum of all possible such divisors. So, yeah. So think about it. What we can do is we can simplify this equation. This sum is nothing but just add all these numbers. It will be very, very like beautiful. Like see 2 to the power 0 plus 2 to the power 1. Just sum all these numbers. 2 cube into, so we have one big bracket, sum of all these numbers multiplied by sum of all these numbers. 5 to the power 0, 5 to the power 1 plus 5 to the power 3. Why? Just expand the bracket, you will see. If you expand the bracket, you will have 2 to the power 0 into 5 to the power 0 plus this into this plus this into this plus this into this. This is actually the sum of all divisors, right? We said that these are all the divisors. Take one number from here, one number from here, one number from here, right? So even if you have more prime numbers, just make big brackets, sum of all the numbers in one of the brackets. And when you expand this entire thing, you will have sum of all the divisors. So yeah, this expanded is actually equal to sum of all the divisors. Sorry. Yeah, and this is what we wanted, right? So yeah, like now, but how to calculate the formula? Very simple. These are all geometric progressions. These are all geometric progressions. They start from 2 to the power 0 or any prime number to the power 0 and they go up to some prime number to the power k. Very easy. So sum of GP is what? So the sum of GP is A r to the power n minus 1 upon r minus 1. Right? So how? Like if you want to calculate the sum of A plus A into R plus AR square and so on up to n terms. This is the sum of GP. Very easy. Like we know this from like our childhood. So like yeah, just apply the formula and that's how we are here deriving this formula. So if you have a prime number like this, if you have any number and prime factorization is this, you have even options in P1. So what will happen for the first prime number? For the first prime number P1, you will go from P1 to the power 0 all the way up to P1 to the power E1. So let's first calculate the sum of this GP only, okay? What is the sum of this GP? P1 to the power 0 plus P2 to the power, P1 to the power 1 plus P1 to the power 2 up to p1 to the power e1. So it is a. A is what? The first element. First element is always p1 to the power 0 or any number. It will always be 1 because it will be prime number to the power 0. A is first element A. R is what? The number which we are multiplying every time, which is p1 here. Okay. So A R to the power n. How many elements do I have? E1 plus 1. I have E1 plus 1 elements. So A R to the power n minus 1 upon R minus 1. So this is the sum of the first bracket, which is written here. Similarly, the sum of the second bracket will be this, and so on. You just multiply all these, you'll get the sum of all divisors. So if you do it for 1000, it is like simple now. So let's apply it for 2. A is 1, so R to the power n. R is 2 here. 2 to the power 4 minus 1 upon R minus 1. And multiplied by for 5. R to the power n. N is also 4 here. We have 4 elements. Minus 1 upon R minus 1. We just calculate this. It will come out to be 2340. Okay. So I hope you got it. Okay. We are somehow applying rule of sum product here in all these cases, and these are standard problems. You can get these problems even in the aptitude section. Okay. So like counting is one subject which has common like thing with aptitude section as well. You will get these questions both in math and aptitude section for GATE CS and DA both. Hi everyone, welcome to GATE data science course. So this is our second lecture on counting. Here in this lecture we will discuss factorials. In the last lecture we discussed rule of sum and product, and like keep remembering all these. So like always follow the lectures in this order, because like we will be using all the concepts which we have learned so far in the coming videos. So like follow the order, it will be really helpful. So yeah, what is factorial? So factorial is defined to be this. Okay, like you cannot like derive it. Factorial n is defined to be the product of all whole numbers up to n. Okay, whole number is what? Numbers, natural numbers up to n. Okay, so starting from 1 into 2 into 3 into 4 up to n, this is what n factorial is. So factorial of a non-negative integer. So factorials are not defined for negative integers. We use the notion of factorial of negative integers. We will use that. Okay, later when I teach like binomial theorem and stuff like that, like we will use the notion of factorial of negative integers, but that's not how factorial is defined. We will just use it for sake, but factorial by definition is only defined for positive integers, and the factorial of n is denoted by n factorial. You write it like this or like this. Sometimes you will see this notation also. Okay, so you can write it like this, factorial of n plus 1. So this symbol is also for factorial, and like the exclamation mark is also for factorial. So it's the product of all positive integers less than or equal to n, as I told you. And what is the motivation behind it? Why do we use it? Because it is used in arrangements. Okay, in the coming few videos I will explain you what selection and arrangement means. So for now, like just know this thing, ki factorial came in picture when we wanted to count the number of ways to arrange things. And actually the number of ways to arrange n objects in a row is factorial. So how do we prove it? So firstly let's know like what arrangement is. So let's say like you had like school, right? Like you went to prayers and there are 30 students in your class, and generally there is an order in which students stand in prayer while doing prayers, right? Like I used to have that ascending order of height, right? So that like the student in the back can see. So generally that is the order. So this is what order is. Okay, like people like love order. Okay, that's why we have like government, everything. Like we want to have order. Okay, otherwise like it's all chaos. So if you have n objects put up randomly, it's very difficult to derive insights out of it. When we put them in some order, ascending order or something, it's easier to see certain properties of the data set. For example, if you want to find the middle element, which is called median, right? You have to arrange them in some fashion, right? Ascending order or descending order. So this is called order, like arranging elements in certain order. That is called an arrangement. And what is n factorial? The number of all possible ways in which we can arrange n elements. So for example, if we have, let's say, 4 elements, 1, 2, 3, 4. Or let's take 3 only, okay? So let's say we have 3 elements. So this is one order in which I have placed them. This can be one order, 2, 1, 3. And then you can have 1, 3, 2. Then you can have 3, 1, 2. Then you can have 3, 2, 1. Okay, and then you can have 2, 3, 1. So these are 6 possible orders in which I can arrange. These are arrangements, right? Order is always arrangement. So these are 6 possible ways in which I can arrange 3 numbers. So how did the formula for n factorial came in? So we know that n factorial is the number of ways in which we can arrange n elements in a row. So let's say, let's take the same example. Okay, so for 3 elements we saw that there are 6 ways. I'll just write them quickly here. So for 3 elements we saw there are 6 possible ways. Okay, now somebody now we will use the concept of recursion. Okay, so now let's say I want to find all the number of ways in which I can arrange 4 integers in a row. Okay, so now I have 1, 2, 3, 4. Okay, so by definition this is 3 factorial. We know that number of ways in which we can arrange n elements in a row is n factorial. For 3 we calculated it is 6. So this is 3 factorial, which is 6. Now let's say I want to arrange 4 elements. So I have 4 places to fill in. Right? Just see, okay. For the first place, how many options do I have? I can have 1 here, I can have 2 here, I can have 3 here, and I can have 4 here. Rule of product, how? So my task is what? Starting point. My task is what? To find the number of ways in which I can arrange 4 numbers in a row. That is my task. I break it into 2 parts. First task T1, then T2. Rule of product, very simple, okay? So first task is to fill the first place. Fill the first place. And so this I'm talking about 4 right now, okay? Arranging 4 elements. And the next task is fill the remaining 3 places. Fill the remaining places. That's it. I have to do task T1 and T2. First I will fill the first place and then I will fill the second place. So it's the rule of product. How many options do I have to fill the first place? I can put any element from these 4 elements in the first place. So I have 4 options to fill the first place. In how many ways can I fill the remaining 3 places? That is by definition 3 factorial. Right? So for the remaining 3 places, what do I have to do? I just have to arrange 3 elements in 3 places. So we already did that. This is 3 factorial. So for 4 elements, so by definition we told this previously, the number of ways to arrange 4 elements in a row is 4 factorial. So we proved that 4 factorial will be what? 4 times 3 factorial. In a similar way, we can prove that for any n, the factorial of n will be what? N times n minus 1 factorial. Okay, so this is the recursive equation for factorials. For any number n, the factorial of n is what? N times n minus 1 factorial. So, and when talking about recursions, we have a base case, so you can always have a base case. Let's say 1. What is the number of ways to arrange one object in a row? 1. Okay, you just have to write that object in that place. So 1 factorial will be 1. This is your base case. So that way you can now compute any numbers factorial, right? So yeah, this is how it is defined. So let's see a few examples. So also try to memorize a few factorials. Sometimes it speeds up your calculation. Anyways, when you do a lot of problems in counting, okay, trust me, you will tend to remember at least factorials up to 5 or 6. Okay, so 5 factorial is 120, 720, and I remember it up to 10. Okay, so 7, 8, 9, 10. But you won't need it. But trust me, when you do a lot of math, you will tend to remember factorials. In GATE, you will be given a calculator, but that is dummy. Okay, trust me. In 3 hours, you won't be using it. They don't ask you heavy mathematical questions at all. Okay, even in counting, if they ask questions, it will be faster when you solve it by hand, because you'll have to go to the UI, okay, and then like click on numbers. It will be like taking up a lot of time. So it's easier, like do practice like without calculator first. If it is like too math heavy, like use calculator, otherwise not. So yeah, so just remember a few factorials. So 1 is 1, 2 is 2, 3 is 6, 4 is 24, 5 is 120, 6 is 720, 7 is 5080. You won't need after 6 generally. Most of the questions will be, so like why I'm telling you this, most of the questions will be arranging 6 objects, or like let's say you want to count the number of arrangements of words or something. Most of them will be 6 or 7 words. So otherwise, like you can have 8 is 40320 and 9 is 362880. Okay, so like try to memorize a few of them. So the next question is, you have to find the number of factors. Remember, we have learned this in the last lecture. How do we count the number of factors? So in this question, you have to count the number of factors of 10 factorial. And the key to find the number of factors was what? To do prime factorization, right? So in factorial, remember, like don't calculate the entire number and do the prime factorization. Don't do that. It will take a lot of time, because 10 factorial will be 3628800. Doing its prime factorization will take 2-3 minutes. Don't do it that way. Use the property of factorial. We know the definition of 10 factorial, right? What it is. It's the product of all natural numbers up to 10, right? So try to write, like prime factorization is what? Remember, expressing the number as power of its prime factors, right? So what are the prime numbers less than 10? See, 10 factorial is what? 1 into 2 into 3 into 4 into 4, 5 into up to 10, right? So what prime numbers might come? 13 cannot come, right? Because 13 is greater than 10. In this entire factorial, 13 can never come. The only prime numbers which will come is 2, 3, 5 and 7. In 10 factorial, we will have these prime numbers. We cannot have 11, 13, 17, right? We will only have prime numbers less than 10. Now we need to calculate their powers. So just calculate their powers, okay, it's easy. So just see how many times 2 is coming. So 2 will come in 2. Okay, just go with every number. So 10 factorial is what? 1 into 2 into 3, 3 has come once, into 4. 4 is what? 2 twice. Okay, then 5, 6 is what? 2 into 3. 7 is what? 7. 8 is what? 2 cube. And then 9 is what? 3 square. And then 10 is what? 2 into 5. This is what prime factorization of 10 factorial is, okay, right? Like simple. So it is what? 2 to the power 1, 2, 3, 4, 5, 6, 7, 8, 3 to the power 4, 5 to the power 2, 7 to the power 1. Now it's easy. You just remember, like, what is the number of factors? Never memorize the formula. I told you, like, if you forget the formula, you can derive it straight away. Number of factors, how will you do it? You have how many options for 2? 8 plus 1, 9. Because you can take 2 to the power 0, 2 to the power 1 up to 2 to the power 8. You have 9 options for 2. You have 5 options for 3. You have 3 options for 5. You have 2 options for 7. That is your answer. Okay, it will be 270. And now again, very interesting problem. Okay, like when I tell you it's an interesting problem, try to pause the video and think about it on your own, and then try to see the solution. Okay, it will like help you a lot. Trust me, like it's not about just seeing the lectures and solving the problems like while seeing the lecture. I used to do this, like use this strategy. Always pause on the problem first and try to solve it on your own. And if you spend 30 minutes on a problem, it will be more beneficial, okay, than just watching a 1-minute video and like seeing the solution. Because when you spend those 30 minutes, you will know all the wrong ways to solve the problem, and that will save a lot of time later in the exam. Cool. Very interesting problem. What is the number of zeros at the end of 100 factorial? It is an aptitude question. It has been asked before, I guess in JEE mains, okay, and it can definitely be asked in GATE as well. It's an aptitude question, and it comes under counting. So, okay, I'll give you the solution now. So think about it. Okay, 100 factorial will be a very, very huge number. Okay, definitely you cannot calculate it. Okay, even your calculator won't in the portal. So, and it is specifically telling you need to find the number of zeros at the end. See, this question will never come like this. How many zeros are there? Because see, this is a number 504000. Okay, there are 3 zeros at the end. They will never ask you the total number of zeros. This you cannot calculate. For this, you need to calculate the entire number. But if you want to count the number of zeros at the end, that's a very simpler problem. Okay, how will I do that? So you can always write a number like this in this format: 504 into 1000. Whenever you want to count the number of zeros at the end, just split the number. Okay, all before zeros and all after zeros. So it is what? 504 into 10 to the power 3. And this is the number of zeros at the end. Whatever the power of 10 is, it is the number of zeros at the end of the number. And what is this? It is 504 into 2 cube into 5 cube. See, the prime factorization of 10 is 2 into 5. You can never make a 0 unless you don't have a 2 or 5. To make a 0 at the end, you need 1, 2 and 1, 5. And every 2 and every 5 will merge up and make a 10 and a 0 at the end basically. See, think about it. You have a very large prime factorization. Let's say 2 to the power 7 into 3 to the power 13 into 5 to the power, let's say 4 into 7 to the power 100 into whatever, blah blah blah. Whatever prime number you can have, okay, very large prime numbers. The capability of making 10 is only for only 2 and 5 have the capability of making a 0 at the end, right? Because the prime factorization of 10 is 2 into 5. No other prime number can make a 10 or a 0 at the end. So here in this, whatever number this is, how many zeros will you have at the end? See, 2 has capability of making 7 tens. 5, we have 4 5s. So you can at max make 4 tens. You use 4 of these 5s and 4 of the 2s. So whatever is the minimum of 2 and 5, whatever is the minimum of the power of 2 or 5, that will be the number of zeros at the end. So that's a formula I'm giving you now, a trick. The number of zeros at the end of any number, you just do prime factorization of the number. The minimum of the power of 2 and 5 will be the number of zeros at the end. So in this number, there will be 4 zeros at the end, right? So now the problem becomes simpler, right? You just need to calculate the minimum of the power of 2 and 5 in 100 factorial. Sorry. So again, the problem is not that simple. How will I calculate the power of 2 and the power of 5 in 100 factorial? Now, see, in any n factorial, the power of 5 will be lesser than power of 2, right? For example, when we see this particular thing, 5, the power of 5 was only 2, power of 2 was 8. You will have more 2s, right? 2 is a smaller prime number, it will divide a lot of numbers. So the power of 2 will be anyways larger. You just need to calculate the power of 5. Because I told you the minimum of the power of 2 and 5 will be the number of zeros at the end. So the problem just boils down to what is the power of 5 in the prime factorization of 100 factorial. Again, it's an interesting problem still. See, now what is 100 factorial? If you look closely, 1 into 2 into 3. I'm just writing a few numbers. Then you will have a 10. So where will you have 5? You will have 5 in all the multiples of 5. You will have 1 5 here. You will have 1 5 here in 10. You will have 1 5 in 15. You will have you will have 2 5s in 25. I will come to 2 5s later. So basically you will have at least 1 5 in all multiples of 5. And how many multiples of 5 will you have up to 100? 100 upon 5. Simple, right? You will have 20 multiples of 5 in 100 factorial. 5, 10, 15, 20 up to 100. You will have 20 multiples of 5. They will have at least 115. All of them will have at least 115. So you have at least 20 5s. Now some of them have 2 5s as well. And what are those numbers? those can be represented like this, 5 square into something. So basically all multiples of 25 will have 2 5s, right? So 25 will have 2 5s, 50 will have 2 5s, 75 will have 2 5s, and 100 will have 2 5s. All the multiples of 25 will have 2 5s. So we missed 4 5s. So 20 are for multiple of 5 and 4 we missed. Where? In 25, 50, 75 and 100. And no number can have 3 5s. For 3 5s to for you to come, the number should be at least 5 cube, which is 125. Since we are only going up to 100 factorial, you cannot have 3 5s, right? So this will be the power of 5, 24. I hope you got it, and you can check, like, take it as a homework, try to calculate the power of 2 as well. Power of 2 will be much higher, okay? You don't need to calculate the power of 2, always in such problems calculate the power of 5, that will be smaller, and that will be the number of zeros at the end. So the number of zeros at the end of 100 factorial becomes 24. Okay? So, like, now you can do it for any n factorial. It will not, so doing this problem without like breaking it down like this is impossible, okay? You just have to like think clearly, okay? How can you make 0 at the end? And yeah, that's how you can do it. Hi everyone, welcome to the GATE data science course. So this is lecture number 3 on counting, and in this lecture we will discuss permutation. Cool. So what is a permutation? Permutation is nothing. Permutation is permutation of a set is an arrangement of its members into a sequence or a linear order. Okay, as I told you in the last lecture, while discussing factorial also, then like permutation is nothing but in how many ways can you arrange objects. Okay, so by definition, if you want to permute n objects in n places, we already know the number of ways, it is n factorial, right? So permutation is what? Just arranging the members of a set into a sequence. Permutation without repetition. Okay, this is very important. We will discuss this a lot while solving questions, and read the question very carefully. Okay, whatever exam you're writing, like when aptitude questions come on counting, very carefully read it. Okay, I lost marks in GATE, I remember. Okay, but just because of this mistake, with repetition or without repetition. Okay, there is just one out which like you can miss very easily. Okay. So we will discuss it a lot. In a lot of problems, I will like emphasize this point, like is it with repetition or without repetition? What do I mean by repetition? So generally these problems, like how will they go? You have to, let's say, arrange n objects in r places. But you have to see very carefully. By default, if nothing is mentioned, you can assume without repetition. Okay? If nothing is mentioned, it is like you cannot repeat. If repetition is allowed, they will mention it specifically. You cannot, you have to repeat, you can repeat as well. Okay, so by default it is without repetition, you cannot repeat objects. So for example, if you have n objects, 1 2, let's say you have 3 objects and you have to arrange them in 2 places. So by default you cannot repeat them, so you put one of the objects here, put one of the objects here. Okay, you cannot repeat them, you cannot use 4 twice. That is without repetition. You are not repeating the elements. Okay. So where we consider the number of possible ways of arranging n items into n places. Okay. So permutation without repetition is we have to arrange n items into n places. The factorial has a special application. We already saw it in last lecture in defining the number of such permutations or arrangements in a set that does not include repetitions. There also we didn't repeat them. If I have to arrange n objects, I assumed that object is gone now. Now I have n-1 objects for n-1 places. Okay. So now the interesting thing is, why are we learning permutation? We already know factorial, right? If we have to arrange n objects in r places, if you have to arrange n objects in r places, and r will always be less than equal to n. Why? Very simple, right? You cannot arrange 4 objects in 5 places, right? You can never arrange 4 objects in 5 places. One will remain empty. So the number of ways in which you can arrange n objects in r places, okay, the number of arrangements of r items out of n objects is considered to be a partial permutation, and it's written as NPR. That's how we write it. Okay. And we read it n permute r. So basically arranging r objects out of n objects. So let's try to derive it. Okay, again, like we have, let's first try to take an example and derive it. So let's take 5 objects. I have 5 objects, n is equal to 5, and let's say I have 3 places. Okay, very simple, like as we did in factorial. How many options do I have for the first place? Again, like anyways, you can always break all these proofs using the rule of sum and product. Most of them are applying rule of product, right? You have a task. What is your end task? Think of it like this: start and end. What is your end task? You have to arrange 5 objects in 3 places. So break it this way: fill the first place, then fill the second place, and then fill the third place. This is your task. Fill the first place. How many options do I have? I have 5 different options. I can put any number in the first place. I have 5 options for the first task. And rule of product. So, and now I have to fill the second place. For the second place, let's say, for example, I put 4 here. Okay. For the second place, how many options do I have? Again, it is without repetition. So I cannot repeat 4. So how many options do I have? 1, 2, 3, and 4. I have 4 options for the second place. And then how many options do I have for the third place? Let's say 3 went here. Now I have 3 options, 1, 2, and 5. I can put any element. Let's say I put 1 here. So I have 3 options for the third place. So this is the number of ways in which I can arrange, right? Very simple. So like coming to derivation again, like we can do the same thing for n objects in r places. So let's say now you have n objects. So for a generic proof, let's say we have r places. For the first place, I will have n options. For the second place, I will have n minus 1 options because one object is already gone. For the third place, I will have n minus 2 options. And this is defined to be NPR, right? I already told you. This is defined to be NPR, the number of ways in which I can arrange n objects in r places. And so on. Now think about it. How many options will we have for the rth place? Pause the video and try to think on your own. Okay? Okay, now I'm giving you answer. So how many options will I have for this place? So this is like a standard problem. You will see it most of the times when doing counting problems. You have some idea, you know for the first thing, like first occurrence what is happening. For the second time what is happening. You have to just extrapolate that and what will happen at the rth place. So like I have a trick to do that. I use that. So always try to create a map. Otherwise you will make a mistake. For first place you had n options, which was n minus 0. For the second place you had n minus 1 options. For the third place you had n minus 2 options. You see a pattern? For any ith place you will have n minus I minus 1 options, right? If this is I, you are doing n minus I minus 1. This is I minus 1. For 1 it is 0, for 2 it is 1, for 3 it is 2. So for rth place, how many options will you have? N minus r minus 1. Don't forget to add this bracket. Okay, don't write it this way, n minus r minus 1. This is wrong. Okay, so if you expand this bracket, it will come out to be n minus r plus 1. I hope you got it, right? So for the rth place, just extrapolate, you will have n minus r plus 1 options. Okay, spend this time. Okay, people tend to like they are like sometimes being too fast is also bad. So if you're being too fast, you will make this mistake. You will write n minus r minus 1. Okay, spend time and see, for 1 it is 0, for 2 it is 1. So it is n minus I minus 1 in brackets. So that way this is NPR. That's all. Okay, this is the proof. Now we can use factorials to simplify this. So what we can do is, just we know that n factorial is the product of all the natural numbers from 1 to n. So why not make like complete it up to n? Let's try to complete it up to n. So the next number will be what? I'm multiplying some new numbers here and I'll divide by the same numbers. So I'll just divide by the same numbers. So what will be the next lower number? It will be n minus r. Right? Just subtract 1 from it. The next number will be n minus r. The next number will be n minus r minus 1. And so on up to 1. Okay? I just multiplied this thing in the numerator so that I can have all the numbers up to 1 in the numerator, and I will divide by the same numbers in the denominator. N minus r minus 1 all the way up to 1. Now see this very easily, like you can see, the numerator is what? N factorial, and the denominator is what? N minus r factorial. Right? It is n minus r factorial by definition. So this is what NPR is. So this is the proof. NPR is n factorial upon n minus r factorial. Okay? Cool. So again, but generally I don't tend to use the formula. See, it will be always easier to solve NPR. So let's say you want to calculate. I'm giving you some tips and tricks. Okay, in exam. Let's say you want to calculate 7p2. Okay, if you always remember the formula, you will do it this way: 7 factorial upon 5 factorial and n factorial upon n minus r factorial. That will take like more time. So when you solve a lot of problems, what happens is you get to remember the proof. Okay, try to remember the trick, not the formula. Like why? Again, whenever you see 7p2, p means permute. Permute means arrange. Quickly, like get that in your brain. P means arrange. So you have to arrange 7 objects in 2 places. So the number of ways will be 7 into 6. For the first place, you will have 7 options. For the second place, you will have 6 options. Right? Don't do this. This will take more time. Okay, quickly you can calculate this. Right? Similarly, let's say you want to calculate 8p3. Permuting 8 objects in 3 places, 8 into 7 into 6. That's all. Just keep multiplying them 3 times, like whatever number of places you have. That will be quicker. This is actually the same thing as like the formula, but this will be quicker. Cool. Now let's try to see some problems. So this is the first problem. What is the number of 3-letter words with or without meaning which can be formed from the word party where repetition is not allowed? Here, like it is explicitly said that repetition is not allowed. But by default, if it is not mentioned, repetition is not allowed. Okay. So try to solve this. Then I'll do it. Okay. So we have party. See, the most important thing to note here is all 5 objects are different. This is also one thing you need to note. Okay, in all the proofs which I did so far for permutations, I assumed that objects are different. We are not arranging objects like this. 1, 1, 3, 4. No, you don't have 2 ones. Right now the objects were different. Here also the objects are different. You have 5 different objects. P, A, R, T, Y. All are different. In the later questions, you will see the objects will repeat and I'll tell you how to solve that. But for now, objects are different. You have to arrange 5 objects in three places. You have to find 3-letter words, right? So you have to just arrange 5 letters in 3 places. Very easy, 5p3. Again, like instead of going with the formula, just do it like this. Like you have 5 options, 4 options, 3 options, 60. Okay. So next question. Now we have some common words. So in how many ways can the word beaker be arranged? Okay. Now this is this gets slightly trickier, and we will solve this. So what happens is here they have not said how many places. So if they are not mentioning the number of places, by default you assume the same number of places as the object, right? So you have to arrange the entire word beaker. So there are 6 words, 6 letters, and you have to arrange this 6 letters in 6 places. So we have 6 places. Okay. Now what happens is, let's say like whatever we have learned so far, what will be your answer? It would have been 6 factorial, right? If like forget about like we have 2 e's right now. If we didn't have 2 same e's, the answer would have been 6 factorial. The number of ways in which we can arrange the 6 letters of the word beaker is 6 factorial, right? But there is a problem here. There are 2 e's. So what will happen? See this. So why is this a problem? Firstly, let me tell you that. So let's say we have 3 letters A, B, C. we know that there are 6 ways in which we can arrange it, right? 3 factorial. What are those? ABC, ACB, BAC, BCA, CAB and CBA, right? Now consider this. Now let's say I make B as same as A. For now, let's assume B is also A. So if I apply the same formula, what are the words that I will be getting? I will be getting AAB, AAC, ACA, AAC, right? I'm replacing every B with A only. So now I'm trying to arrange all the letters of the word AAC, right? I'm replacing every B with A. So this is what the formula gives us. So this will become ACA, this will become CAA, this will become CAA, and this will become CAA. You see the problem, right? We are over counting. We have AAC twice, we have ACA twice, we have CAA twice. The problem was what? We cannot apply the direct formula here because we have 2 A's and the formula is for all distinct words. So you will have repetitions, right? So now how to solve this problem? So the trick is very easy. For now, assume that these 2 E's are different. Firstly, assume that these 2 E's are different. Let's call them E1 and E2. If I call them E1 and E2, then the number of ways will be 6 factorial. The number of ways in which I can arrange these 6 words, 6 letters in these 6 places will be 6 factorial. Now try to see what are we over counting. Now E1 and E2 are same. So here what happened? Since A and B were same, every permutation was counted twice. Why? Because every B was A only. So when you swap B and A, that will be different permutation, but if you consider B and A same, that will be the same permutation. So you are actually counting every permutation twice. So why? Because the number of ways in which we can arrange these 2 among themselves. Here also the same thing. The number of ways in which we can arrange A and B among themselves is 2 factorial. The number of ways in which we can arrange E1 and E2 among themselves is 2 factorial. So every permutation will be counted 2 factorial times. That will be repetition factor. So we have to divide this by 2 factorial. Similarly here, the actual number of ways was 3 factorial. But the number of ways in which we can arrange A and B among themselves when we have 2 A's is 2 factorial. So we have to divide by 2 factorial. So if I take a complicated example, let's say I have A, B, B. Okay, consider all of them different, then you will have 5 factorial ways. But now what is happening? The number of ways in which you can arrange only these 3 letters among themselves, keeping the other places same, will be 3 factorial. And all these 3 factorial places will have the same word. Think of it, right? Like let's say you have A1, A2, A3. A1, A2, A3, B1, B2. Keeping the position of everything same, if I just arrange these 3 among themselves, there will be 3 factorial or 6 ways. For example, A2, A1, A3, B1, B2. And you will have 6 ways. And all these 6 words will be same. So every permutation will be counted 3 factorial times. So you have to divide by 3 factorial. And same for B. The number of ways in which you can arrange B among themselves is 2 factorial. So you have to divide by that as well. This is the overcounting that we encountered and we solved it. So the number of ways in which we can arrange this will become this. So it's very simple, right? Just divide by the number of repetitions of every character. So here the answer will be 6 factorial by 2 factorial, which is 360. Okay. Okay, now more difficult problem. So again, pause the video and think about it. So the number of permutations of the word climate says that the vowels always occur together. Okay. Try to reduce the problem. Try to remember the rule of product. Try to reduce the problem and then solve it. So the number of permutations of the word climate says that vowels always occur together. First thing, there are 7 letters and all of them are different. So this is one good thing. Okay, and now how many vowels do we have? C is a consonant, L is a consonant, M is a consonant, T is a consonant, I is a vowel, A is a vowel, and E is a vowel. We have 4 consonants and we have 3 vowels. So if I forget about this statement such that the vowels come together, then the number of permutations is easy, 7 factorial, right? We have 7 letters, we can arrange them in 7 factorial ways. But now there is a specific request ki, like the vowels must come together, okay? They like each other, okay? So now I, A, E will always come together. You cannot have a word. So you will have a word like C, L, I. In all possible permutations, you will have a word like this. But this is not allowed because I, A and E have to come together. And they have not said ki what is the order of them. They can come in any order, but they should be together. So like observe this. C, L, M, T, I, A, E can be possible. And C, L, M, T, A, I, E is also possible. These are 2 different words. Here also vowels come together, here also vowels come together. Okay? So how to solve this? So try to break the problem again. There is a standard trick to solve this. Always see, when they say a certain group of people always come together, consider them as a group. Consider them as a single entity. Consider them as a single entity. Let's say this is a different word. Okay? IAE is a different word now. Okay, you can name it anything. Let's say it is K. I've named it like randomly, okay? So now what happens is I have made this group. This group comes together, okay? Like we should use group G. Okay, so this group always comes together. So in how many ways now can I arrange C, L, M, T and this group G? So again, like consider this as this task. You are starting. Your first task is to arrange C, L, M, T and G. Just arrange this. But here there will be some issues like this, right? Because IAE and AIE can again shuffle among themselves, right? So then I will do another task. Arrange letters in G among themselves. And that will be my end, right? So first I will just consider this IAE as a group G. Arrange all the words. Then I will see, like see I am undercounting. If I am just considering that as a G, like the number of ways will be 5 factorial, right? 1, 2, 3, 4 and 5. G is one entity now. So this can be done in 5 factorial. But this is not my answer. Why? Because these 2 are different. And so so keeping everything constant, only the letters in G can be shuffled among themselves. And in G we have 3 words. In G we have 3 words. So we can arrange the letters in G in 3 factorial ways. So I have to do this and this. So the number of ways in which we can arrange it is 5 factorial times 3 factorial. Okay. Consider that particular group as G. So I can take one more example here. So let's take it here. So this, if you count, like it will come out to be 720. Let's say AAA. No, we don't want repetition. So let's say ABC and DEF. And let's say I tell you कि AB will always come together and DEF will always come together. Okay, simple problem. Consider AB as a group G1, C is anyways alone, DEF consider it as another group G2. You have 3 tasks. Arrange first this 3. Arrange G1, C and G2. So this is your first task. Arrange G1, C, G2. Second task will be arrange all the elements among G1. And also you can arrange all the elements in G2. Right? So these 3 can be arranged in 3 factorial ways. All the elements in G1, there are 2 elements in G1. They can be arranged in 2 factorial ways. And all the elements in G2, there are 3 elements in G2. They can be arranged in 3 factorial ways. So for this example, the answer will be this. Okay. So, yep, this is one type of problem. Now adding everything, this is the most complicated problem that can come. The number of permutations of the word cheetah says that the vowels always come in odd places. So again, think about it, take some time, and so also observe, firstly observe the word. It contains 7 letters again, and it has 3 vowels and 4 consonants. Okay, so let's put all the consonants here, and we have 3 vowels. Okay, 4 consonants, 3 vowels, and the vowels are repeating also, so we will overcount. That's okay. Okay, now we know the trick of everything. Whatever we have learned so far, you can solve this problem. Okay, let's do that. So we have 7 places. Now the vowels always occur in odd places. Okay, they have a specific requirement. कि vowel can only come in this, or this place. ठीक है? So for now, let's assume these two are different. Whenever you have repetition, consider them different first. Solve the problem, and then you can always encounter the overcounting. You can just divide. So consider them different. Now these 3 vowels, E1, E2 and A, have to come in the odd places 1, 3, 5 and 7. Okay. So basically, what is the problem? You have to arrange these 3 words in these 4. They have to come in these 4 places, and the remaining 4 words, 4 letters can go anywhere, right? So like think about it. The number of ways in which, so basically it's like allocating. So for these 3 letters, E1, E2 and A, for these 3 letters, you have to allot a number between 1, 3, 5 and 7. Okay, so for E1 you have 4 options. You can allot 1, 3, 5 or 7. E1 can go in any one of these 4 places, 1, 3, 5 or 7. For E2, how many options will you have? Let's say 1 is gone, so you will have 3 options. And for the final A, how many options will you have? The remaining 2 options. So it's like allocating these 4 positions to these 3 words. We anyways knew it. It is 4p3. We anyways knew it. Okay, right? So basically allocating 4 positions to 3 characters. 4p3 is the number of ways. So this is my first task. First task T1 was just arrange all the vowels in the odd places. We have done that. This is the number of ways. Now what is the second task? Second task is arrange the consonants. So this was arranging vowels. Next is arranging consonants. Once we have arranged the vowels, the problem became simpler. How? Now we have 4 consonant and remaining 4 places. 4 consonant and remaining 4 places, whatever, they can be anything. So to arrange 4 consonant in 4 places, 4p4 or 4 factorial, you can write anything. Right? 4 consonant, 4 places, 4 factorial. And yeah, that's all. This is our end. Right now I have considered E1 and E2 to be different. So this is the number of ways in which I can arrange the letters of the word cheetah. Considering both the E is different, E1 and E2, it will be 4p3 into 4 factorial. Okay, but now again we are overcounting. What are we overcounting? E1 and E2 are not different, they are same. So in every such permutation in which E1 and E2 are different, we are counting it twice, because E1 and E2 can be arranged among themselves in 2 factorial ways. So yeah, we have to divide this number by 2 factorial. We have to divide this number by 2 factorial because E1 and E2 are same. We are overcounting every permutation twice because E1 and E2 can be rearranged among themselves in 2 factorial ways. So this is our answer. This will be what? 4p3 is 4 into 3 into 2 and 4 factorial is 4 into 3 into 2 into 1 upon 2. Okay. So you can just calculate it. It will come out to be 288. So this was the number of permutations. So this is like having everything what we have discussed so far. We have 7 letters. There were repetition and the vowels had to go in certain places. So it included permutation, the rule of product, and the concept of overcounting and undercounting. So that's how you do it. Okay, we will be doing more such problems. So whenever I have live sessions, when I do problem solving sessions, I'll come up with more such problems and we will solve them live. But for now, yeah, this is about permutations. Hi everyone, welcome to lecture number 4 of counting under GATE data science course. So in this lecture, we will learn about combination. So in the previous 3 sessions, we have seen rule of sum, rule of product, factorial, and the number of arrangements, which is permutation. So now we will see combination. So a combination is a mathematical technique that determines the number of possible arrangements in a collection of items where the order of selection does not matter. So, what do I mean by this? So very simple, in very simple terms, permutation is arrangement and combination is selection. So when you have to select R items out of n objects, it is combination. When you have to arrange them, it is permutation. So just selecting them, like let's say we have a 15 player squad for World Cup, right? But 11 players play a certain cricket match. So the selection committee for every match selects 11 player out of the 15 players to play a match. It doesn't matter, right? Actually, there is an order there as well, right? In which order they will bat or bowl. But right now, let's consider selection. Like I got selected for today's match or not. So it is a selection of 11 people out of 15 people to play a match. That is combination, right? So you can select the items in any order. So the number of ways to choose, we can also call this choose, right? We are choosing objects. We are selecting them. So that's why choose, n choose R. So the number of ways to choose R items from n objects is considered as a combination. It is written as NCR and is read as n choose R. N permute R before and now we have n choose R. Choose R objects out of n objects. So like how will we do it? Again, like let's say we have 5 objects. Okay, and I have to choose any 3 of them. Okay, so basically I can choose 1, 2, 3. I can choose 1, 2, 5. This is a different selection of people, right? I can choose 3, 4, 5. This is a different selection. But 1, 2, 3 and 1, 3, 2 are same. This is the difference between permutation and combination, right? Previously we saw that 1, 2, 3 is different and 1, 3, 2 is different because we want to arrange them as well. But now we are not arranging them. We are just selecting 3 items out of 5 items. That's all. Okay. So these two will become same. So in how many ways can we do it? So just use NPR, whatever we have learned so far. So let's say out of these 5 objects, I have to select 3 objects. So firstly, let's arrange them also. Let's say I arrange them also. Then I know that the number of ways is N5P3. This is the number of ways in which I can select 3 items and arrange them. Like 1, 2, 3, 1, 3, 2 and so on. And the last arrangement will be 3, 4, 5. Right? And 5, 4, 3 will also be a arrangement. So, but here again, whenever you overcount, we see there is an overcount, right? These two selections are same. 3, 4, 5 and 5, 4, 3 are same. We are overcounting. Whenever we are overcounting, we will divide. So how much are we overcounting? So very easy, right? Like it's same as we did before, where 2 vowels or 2 letters were repeating. So here also 1, 2, 3 is like a repetition, right? We cannot repeat it again and again. So for every such selection, for every selection of 3 objects, when we are actually permuting, we are repeating it 3 factorial times. So in every such permutation, what happens? What exactly is happening? So when we are selecting, let's say 1, 2, 3. In 5P3, we will have 1, 2, 3 also and 1, 3, 2 also. We will have 3, 1, 2 also. We will have 6 arrangements. And similarly for some other selection, let's say for 2, 3, 4, this is a different selection. I will again here also I will have 6 different permutations. 3, 2, 4 and so on. So for every selection, I am repeating every selection 3 factorial times. Because that is the number of ways I can arrange these 3 numbers. Right? So here we are overcounting every selection 3 factorial times. So I have to divide it by 3 factorial. Again, that same logic which we applied in the last lecture. Whenever you overcount, just see how many times are you repeating every occurrence and divide by that. So this is what the number of ways of selecting 3 items out of 5 items will be. So for any general n, NCR will be what? NPR upon R factorial, because while doing NPR, you are overcounting every selection R factorial times. That is the number of ways to arrange those R letters among themselves or R selections among themselves. You don't want to do that. So this will be the number of ways to choose R items out of n items. And if you want the complete formula, We know that NPR is what? N factorial upon n minus r factorial. And we have divided by r factorial also. So this will be the formula for NCR. Okay. And there are two notations to write NCR. Some people write it this way. Some people write it in the big bracket notation, which is like this. In big bracket, you write n and r. This is also NCR. This is also NCR. And this is the formula. N factorial upon n minus r factorial, r factorial. Cool. So again, like small trick, how to calculate. I told you, let's say if you want to calculate, let's say 7p3. It was what? 7 into 6 into 5. Right? It should be very quick. 7 into 6 into 5. You don't want to go into factorial also. If you want to calculate 7c3, always remember it is divided by this factorial also. So it will be 7 into 6 into 5 upon 3 factorial. Okay? That's all. But just divided by r factorial also. So that's how you calculate it. It will be very simple. Okay, once you learn this technique, the calculating NPR, NCR will be very simple, like very easy. It will be very fast. And also, I'm not sure if the calculator contains C or P symbols. They don't. So you will have to do this anyway. Okay. So yeah, like you have to do this. The calculator can help you in calculating this multiplication, but it won't calculate 7p3 for you, right? So you need to know the logic at least. Cool. So now there is a mathematical equation written here, and this is called this equation is famously called combination as recurrence. So if you are a computer engineer, you know the term recurrence, I'm assuming. But yeah, like shortly saying, like you want to break the problem into simpler problems and solve those problems and keep doing that. Okay, and we write recurrence equations in computer programming language in a form called recursion. Okay, so yeah, but yeah, you don't need to know all of this. It's just breaking NCR into problem of smaller size. How? This is n minus 1 CR and this is n minus 1 CR minus 1. So basically, choosing r items out of n items, the number of ways to choose r items out of n items is equal to the number of ways to choose r items out of n minus 1 items plus the number of ways in which we can choose r minus 1 items out of n minus 1 items. So firstly, logically, let's think why is it so? Okay, then we will go to the proof. So why is it so? Let's say we have n objects. Okay, let's take n equal to 6. And let's say r is equal to 3. I want to select 3 items out of 6 items. So now what happens is, consider the first element. Okay, and right now, like I know this is a math lecture, but I will go into computer science a little bit just to explain you the logic behind the recurrence. Okay, and any DP problem, okay, dynamic programming or like recurrence problems, generally like problems which involve recursion in algorithms. If you go into computer science, if you are a math student and just learning data like data science, you can ignore like the next 2 minutes. Okay, so when you involve dynamic programming, right? So you want to break the problem into smaller chunks, problems of smaller size, and they will be repeating in some sense. Okay, so this is the standard way to solve such problems. You have a large problem, you have 6 items, you have to select 3. Consider the first item. Okay, always go with the first item. Like consider the first item. What options do I have? Either I can take it or leave it. In the selection committee, okay, like this is KL Rahul. Okay, 15 players, either he will play or not play, right? So in the selection of 11 players, either the player will be present or not present. So there are 2 options. Either take one in the selection or leave one from the selection. Or either take one or leave one. Okay, you have 2 options. Or means what? Rule of sum. In how many ways can I choose 3 items out of 6 items in which I must take one? I have to take one. If I have to take one, basically, then I will have to choose 2 items out of remaining 5 items. Since I have already taken 1 item, now the problem reduces to I have to choose 2 items out of 5 items. And if I leave one, then how many options do I have? Again, I have 5 items, but now I have to take 3 items. Because since I have not taken one, still I have to make a team of 3 people, right? So I have to choose 3 items out of 5 people. This is what 6C3 is. Okay, for the first item you have 2 options. So that's how the recurrence came up. So NCR is n minus 1 CR minus 1 plus n minus 1 CR. You either take it or leave it. This is leave it, this is take it. Okay. So and now mathematically also you can, with the formula you can very easily prove it. So let's just expand the RHS. RHS is n minus 1 CR plus n minus 1 CR minus 1, which is formula wise it is n minus 1 factorial upon NCR. So just remember, like for you to remember, NCR formula was n factorial upon n minus r factorial r factorial. Okay, so it will be n minus 1 factorial upon n minus 1 minus r factorial plus this will become n minus 1 factorial upon, so this will become n minus 1 minus r minus 1 in brackets, minus r minus 1 in brackets, so it will become r plus 1, minus minus will become plus. Okay, you can do this easily, this minus this, so it will become n minus 1 minus r plus 1 times r minus 1 factorial. So you can just write it straight away, minus 1 plus 1 gets cancelled, this becomes n minus r factorial in the denominator. I'm just simplifying it, this becomes n minus r factorial. So now take common, whatever you can take common, just take it common. So in the numerator n minus 1 factorial directly comes as common. In the denominator what can come common? See, here we have r into r minus 1 factorial. R factorial is what? R into r minus 1 factorial. So this is larger. So we can only take r minus 1 factorial common. And here this is n minus r factorial is what? N minus r times n minus r minus 1 factorial. This is what n minus r factorial is, right? So this is what we have here. So I can take this thing as common. N minus r minus 1 factorial common. Okay. So what will it become here? This will become 1 upon r. This will become 1 upon r. Only r is remaining. And this will become 1 upon n minus r. Okay. So this becomes n minus 1 factorial upon r minus 1 factorial n minus r minus 1 factorial times, here you take the LCM, so r times n minus r, and above you will have n minus r plus r. So r and r got cancelled, this becomes n. So this n times n minus 1 factorial is what? N times n minus 1 factorial is n factorial. And in the denominator, r times r minus 1 factorial is r factorial. N minus r times n minus r minus 1 factorial is what? N minus r factorial, which is NCR, which is LHS. Okay. So mathematically you can prove it anyway, but this won't be required for exams. But yeah, you should know, like this is simple. Okay. But yeah, like just think of the logic. Why is it so? And why do we learn this? It has a huge implication in computer science. When you want to calculate, like when you have, let's say, lots of numbers, okay, and in a computer program you want to calculate NCR for many pair of n and r, you generally go with this way. Since it's like a DP table, right? You have already calculated NCR for all n equal to 5. Let's say for n equal to 5 you have calculated 5C1, 5C2, 5C3, 5C4, 5C5. Then for n equal to 6, you don't need to apply the factorial formula again and again. You can just use this. Use the DP table and populate n equal to 6 also. Okay, so I will not use computer science terms, but yeah, in constant time you will be able to fill this table, every element of the table. Okay, so for n and r, if you have the appropriate space, you can actually calculate NCR for every combination in n into r time. Okay, so yeah, like that's the application for this formula. Okay, now next axiom that we have in combinations, very simple, k selection is equal to k rejections. Why so? So again, like let's go to the cricket example. 15 people team, got registered for every country in World Cup. Every match, 11 people play. Right? The number of ways in which we can select a team of 11 people out of 15 people for one match is 15C11. We know that. Okay, number of selections. But actually, think about it. Every time when you are making a selection, you are also making a rejection. When you select 11 people, 4 people remain. So every selection of 11 people is equivalent to a rejection of 4 people. Right? So in simpler example, like let's say A, B, C, D, E, F. Let's say I want to select 4 people. N is equal to 4, N is equal to 6, R is equal to 4. I have to select 4 people. So let's say one such selection is A, B, E and F. Every selection of 4 people is equivalent to a rejection of 2 people. What 2 people got rejected? C and D. Right? Every selection will have a corresponding rejection, a unique rejection. So similarly here, 4 different people have to got rejected if 11 different people are getting selected. So that's why, think about it, there is a one-to-one mapping. Every selection will have a rejection. So, and if you're selecting R people, you are rejecting N minus R people every time. So that's why NCR will always be equal to NC N minus R. Right? This is rejecting R people, and this is selecting R people. Right? So N choose R will be equal to N choose N minus R. Mathematically very easy proof. So just write N choose N minus R. Like if you just write it, it is like very simple. It is N factorial upon N minus R factorial times R factorial. So here R is N minus R. So this is R, and N minus R will become N minus N minus R. So plus R. So this will become N factorial upon N and N will cancel. This will become R factorial. This will become N minus R factorial. This is what NCR. Okay. So K selection is equal to K rejections. So again, like an example from World Cup match. So how many matches are being played in Cricket World Cup 2023? These are some facts. There are 10 teams playing, and each team plays with each other team once in group stage. We should not call it group stage like we have, but like previously we had group stages, right? So yeah, and then we have 2 semifinals and a final. Very easy, very easy problem. Okay, IPL wala problem is slightly difficult. Like there you have, like they made a like huge thing, right? There are 2 pools. Teams in one pool play with like the same pool once and the other pool twice and something like that. So yeah, but here yeah, it's much simpler. So you can count that as well. Okay, just try to do the IPL problem as homework. So this is simpler. 10 teams. So in the league stage or group stage, like how many matches will be there? Every team plays with each other team once. So we have to count the number of pairs. India plays Australia, India plays Pakistan, every pair possibility basically. So in how many ways can I choose 2 teams out of 10 teams? 10 choose 2, 10 C2. This is the number of different pairings, okay, of teams which is possible. So this is the number of matches which will be played in group stages. Plus we have 2 semifinals and a final. So 3 more matches. So 10 C2 is what? Again, like always do it this way. 10 into 9 upon 2 factorial plus 3. So which is 45 plus 3. So 48 matches will be played. Okay. Cool. So here we have next problem. A question paper consists of 16 questions with 8 questions each in set A and set B. So we have 2 sets. Set A containing 8 problems. Set B containing 8 problems. So there are total 16 problems. Students have to answer 5 questions, selecting at least 2 questions from each set. In how many ways a student can select questions to answer? Okay, so I'll give you like just pause the video and try to solve it on your own. Cool, I'll solve it. So Basically, you have to select 5 questions out of these 16 questions. If there had been no such restriction, you have to select at least 2 questions from both the papers. The number of ways would have been 16C5. Selecting 5 questions out of 16 questions, right? But this is not the case here. Here we have to select at least 2 questions from set A and at least 2 questions from set B. So basically, either you can select 2 questions from set A and 3 questions from set B, or you can select 3 questions from set A and 2 questions from set B. This is the only 2 possible ways which you can accomplish this task, right? Again, everything is a task. So either you do task T1 or you do task T2. Or means what? Rule of sum plus. So you select 2 from set A, 3 from set B, or you select 3 from set A and 2 from set B. So in how many ways can we do this? Very simple. 8C2. So here now what happens? This task itself can be broken into 2 tasks. Select 2 questions from set A and select 3 questions from set B. Here we have an AND, right? Here we don't have an OR. We don't have an option. We have to select 2 from set A and we have to select 3 from set B. Similarly, here also we have an AND. 3 from set A and 2 from set B. So this task itself has a rule of product. AND means multiply. So 2 from set A means 8C2 into 8C3, and here 8C3 ways to select 3 questions out of 8 questions, and 8C2 ways to select 2 questions out of 8 questions. So this is your final answer. You have to add these 2. Okay, so it is basically 8C2 into 8C3 plus 8C3 into 8C2. Basically we multiply it by 2. Okay. So like quickly how to do it: 8C2 8 into 7 upon 2 factorial, 8C3 8 into 7 into 6 upon 3 factorial into 2. 6 6 2 2. It is 8 into 6 square, 56 square, whatever is it, 3136. Okay, cool. So now the last example, one of the most important examples of combination. What is the number of different diagonals that are present in an n-sided polygon? Okay. So let's say we have a polygon of side 5. Okay. How many diagonals can we have here? So this is one diagonal, 2, 3, 4, 5. For n equal to 5, we have 5 diagonals, right? So how to solve this? How to calculate it for any possible n? How to calculate it for any possible n? That's what we want to see. So let's see it. So think about it. Firstly, like there are 2 ways to solve this problem. Firstly, I will do the combination way. Okay, let's say there are n points in space: 1, 2, 3, 4, 5. Here we want to, in some sense, want to create a complete graph, right? See, if I create all possible diagonals, here I want to create all possible diagonals. It means basically I'm connecting every point to every point in that polygon, but not the adjacent points. See that if I connect this point to its adjacent point, this is basically the side of the polygon, not a diagonal. But let's forget about that for now. Let's say I have n points in this space. In how many ways can I connect one point to another point? So it's basically the number of pairings. In how many ways can I choose 2 points out of 5 points? 5C2. There are 5C2 ways in which I can choose 2 points out of 5 points, which is 5 into 2, 4 upon 2, 10. There are 10 such pairings. Let's connect everything. 1 with 2, 1 with 3, 1 with 4. These are 10 possible ways. 1 with 5, 2 with 1, 2 with 3, 2 with 4, 2 with 5. 3 with 1, 3 with 2, 3 with 3, 4, 3, 5, 4, 1, 4, 3 and 4, 5. Okay, so there are 10 possible combinations of two points out of 5 points. So these are 10 different lines which I draw. But out of these 10 lines, 5 lines belong to the side of the polygon, not the diagonals. Out of these 10 lines, 5 lines are actually side of the polygon. So in any such example of n, let's say you have n-sided polygon, you first connect everything, okay, everything with everything. So you will have nc2 possible different lines which can be drawn. But out of these nc2 lines, n lines will be from the side of the polygon itself. And the remaining are diagonals. For example, here, these 5 are sides and all remaining are diagonals. So here for n, nc2 is all possible pairings, but there are n sides. So this is the number of diagonals, okay. So, and there is another way to do this as well. Let's see that. Very simple, okay. Okay, so what is the other way to think about this problem? Okay. So let's take any vertex. I took this vertex 1. Okay. So how many? So I want to create a diagonal starting at vertex 1. I want to create a diagonal starting at vertex 1. I have more vertices 2, 3, 4 and 5. So basically, I want to connect one with some other vertex, then it will be a diagonal. So a diagonal is defined how? You can start at a vertex and end at any vertex which is not adjacent to, you can end at any vertex which is not adjacent to this particular vertex. So if you start at 1 and end at 2, it will not be a diagonal, it will be a side. So you can end at any other vertex which is not adjacent to it, like you cannot end at 2 or 5. So basically, you connect this vertex to how many options? How many options will you have? 3 and 4. Basically, you cannot connect it to 1 itself or 2 or 5. So you have to connect every vertex to n minus 3 other vertices. You have to connect every vertex to n minus 3 other vertices. Okay. So similarly, like if you have a large polygon, let's say you have a large polygon, very large. It has like, let's say 100 sides. So for this vertex, how many options, how many diagonals can you make? Starting at this vertex, you can connect it to every vertex except this one and this one. So you will have n minus 3 options. So for every vertex, you have to connect it with n minus 3 different vertices. And now if you think you are overcounting every diagonal twice. Starting at 1 and starting at 3. You are overcounting every diagonal twice. So it is like you have to divide by 2. Okay. So you can do it anyway, and there are 2 ways to think about the problem, and these are the 2 ways. So this is how you calculate the number of diagonals in an n-sided polygon. Cool. So this was a brief introduction about combination. We have learned permutations and combinations. So what are the major differences between these two? The first very basic difference, combination is arrangement. Permutation is arrangement. Permutation means arrangement. Okay, permute, the English term means arrange. So here you are arranging objects, and here you are only selecting objects. Okay, and here does order matter? In arrangements or in permutation, order does matter. Order matters. In combination, the order of selecting the items doesn't matter. You are just selecting them, okay? The order doesn't matter. So that's the main difference between permutation and combination. So there is a, like on a lighter note, so this is called a combination. This is called a combination lock, okay? You try all possible combination, but actually it should be called permutation lock because you are arranging the words, okay? So it is named wrong, and still we are using the same name. You are actually doing permutation in a combination lock. So yeah.
Hi everyone. So welcome to lecture number 5 of data science and AI course. So we were discussing counting, and we already have discussed permutations and combination. But whatever formulas we have discussed so far are permutation and combination without repetition. So when we pick an object, we assume that that object is gone, we cannot pick it again. For example, if you see the player example, the cricket match example, I told you the number of ways in which we can select a team of 11 players out of 15, right? So we were assuming that one player can be picked only once. So all the things which we have seen so far were permutation and combination without repetition. We were not repeating the objects. But now we are going into an interesting domain. We will be seeing combinations and permutations in which there is an infinite supply of objects, you can assume, or like some supply of objects will be given, and we can actually repeat objects. We have seen a few such examples. For example, when we saw the number of permutations of A, B, C. So there were two A's and there were one B and one C, right? So there were repetitions somehow. But now we are going to see generic formulas for those, like if we have n number of supplies for certain objects and we can pick them. So first thing which we're going to discuss is combination with repetition. Remember again the difference between combination and permutation. Permutation is arrangement. You need to select and arrange the objects, and combination is just selection. And how many ways can we select objects? So yeah, assume that we have a set A with n elements. Any selection of R objects from A. So again we are selecting R objects from A, where each object can be selected more than once. So this is our set A. It contains n objects, and we have to pick R items out of it. We know that if repetition was not allowed, the number of ways to select R objects out of n objects was NCR, right? But now repetition is allowed. We can actually select 2, let's say twice. Okay, so repetition is allowed. And so this is called combination of n objects taken R at a time with repetition. Okay, so generally speaking, when questions on this will come, they will explicitly mention in the question that you can assume that repetition is allowed. Okay, so for example, like consider this example: number of ways of selecting 3 letters from A, B, C, D. You have to select 3 letters from A, B, C, D with repetition allowed. So here we can actually select A 3 times. So if repetition was not allowed, what were the number of ways? If repetition was not allowed, we know that the number of ways was 4C3, which is 4. How did I do it so fast? 4C3 is equal to 4C1 and 4C1 is equal to 4. So there were 4 ways. What were they? A, B, C, A, B, D, A, C, D and B, C, D. These were 4 ways. But now repetition is allowed. So we can select any number of objects any number of times. So we can select A 3 times. We can select 2 A's and 1 B. We can select 2 A's and 1 C. We can select 2 A's and 1 D. And so on. So these are all the ways. So we have B selected 3 times. We have C selected 3 times. And D selected 3 times. And but again, like, don't make a mistake. We don't have to arrange them. It is just a selection still. So A, B and A, B, A will be same selection. This is same selection. We are actually selecting 2 A's and 1 B. So these two are same. You don't have to work on. This is a selection, but repetition is allowed. So this is written in the note as well. 2 combinations of repetition are considered identical if they have the same elements repeated the same number of times regardless of their order. Okay, so if you have the same number of elements repeated same number of times, this selection will be considered identical. So these two will be considered identical. Cool. Moving forward. So again, like this is an example. So let us say that there are 2 flavors of juices available in a juice shop. Okay, banana and chocolate. And 3 friends go to the juice shop. In how many variations of orders are possible? So here, like it is a slightly ambiguous question. So one thing is like if you consider these 3 people to be different. Let's say 3 people go to the juice shop. Let's call them A, B, and C. Okay. If we consider these 3 people different, then like the number of like how many options? Like A can order banana or chocolate. The B can order banana or chocolate. C can order banana or chocolate. So there are 8 possible options, right? That way. But this is not what they are asking. They are asking how many variations of orders are possible. So it means that they are asking from the perspective of shopkeeper. How many orders does the shopkeeper has to like make to fulfill all the requests of the 3 consumers. For example, like these are the possible choices. The orders which are possible are one order can be 3 chocolate juices, right? All the 3 people wanted a chocolate juice. One possible order can be 1 banana and 2 chocolate. Okay, one possible order is 2 banana and 1 chocolate, and one possible order is 3 banana juices, right? So these are the only 4 choices possible. So here, here ordering was important. So this was permutation with selection. Here we were selecting and then ordering as well. But here ordering is not important. So from the shopkeeper's perspective, what he has to do? The shopkeeper has to make juices, right? So the order might be 3 banana, 3 chocolate, 2 chocolate, 1 banana. That's how you ask when you go to a juice shop, right? So 3 friends go and I ask we want 2 banana and 1 chocolate juice, right? It doesn't matter which one is getting what, because the banana juice is same actually, right? So these are the 4 possible choices. But how do we calculate them? So here the problem was easy. Here it was given. Here it was given that there were only 2 possible juice options and there were only 3 friends. But let's say now, still there are 3 flavors of juices, but now 10 friends go to the juice shop. Now the problem becomes tougher, right? So let's say again, there are 3 flavors. Let's say the flavors are F1, F2, and F3. There are 3 possible flavors of juice, and now 10 friends go. So now we have to think about it. Okay, now the problem becomes difficult, and now we are seeing the motivation behind combination and repetition. So what is the problem here? Think about it. 10 friends are going. 3 possible flavors are there. What are the possible options that we have? We can order all 10 F1 flavored juices, right? This is one possible choice. All 10 F2 is also possible. All 10 F3 is also possible. There are many possibilities. Consider this. We can have 5 F1 flavors. We can have 3 F2 and 2 F3. This is one such possibility. Right? So there can be many such possibilities. So whenever a question from combinations repetitions come, there is a standard way to solve it. Just try to create a mathematical equation which symbolizes the question. So what is the mathematical equation? Think about it. So let's say you take x1 number of F1 flavored juices. I am taking x1 number of F1 flavored juices, and I am taking x2 number of F2 flavored juices, and I am taking x3 number of F3 flavored juices. Okay, see, juice shop, you always assume when you go and order, you assume that they have an infinite supply of juice, right? I can take 100, if they don't have, they will actually tell you. But in some sense, you are assuming that they have an infinite supply of juices. So you have many F1 flavored juice possible. You have many F2 flavored. You have many F3 flavored juices. Okay, you can take 10 glasses from here, 0 from here, and 0 from here. You can take 5 glasses from here, 3 from here, and 2 from here. That will be one combination. So you are actually picking x1 from f1, x2 from f2, and x3 from f3. The condition is what? That total number of juices you need should be equal to 10, because there are 10 friends going to the shop. So always when a question from combination repetition comes, try to map it to a mathematical equation which solves the same problem. So here we have to find the number of ways, the number of solutions to the equation x1 plus x2 plus x3 is equal to 10. Where what is the range of x1, x2 and x3? What is the domain actually? Sorry. So x1 can lie between 0 and 10, right? There is no condition mentioned. So they are asking for all possible variations. So basically x1 can be anything between 0 and 10. See, why am I adding 10? Because x1 cannot be greater than 10. But you cannot have 11 F1 flavored juices, right? So yeah, you can even skip this condition. The only condition is x1 has to be greater than or equal to 0. Right? It can be 0. Similarly, x2 should also be greater than or equal to 0 and less than or equal to 10, and x3 should also lie between 0 and 10. So this now becomes a system of linear equations. We have 4 equations, and we have to find how many such possible values of x1, x2, x3, the triplet x1, x2, x3 exist which solve this equation. So one such solution is 10, 0, 0. 10 plus 0 plus 0 is 10. It satisfies all the equations. One such solution is 5, 2, 3. And so on. There are many such solutions. And we have to find how many solutions exist. And the number of solutions to this equation is actually equal to the combination with repetition problem. Like in how many ways can this selection be done with repetition? Okay. So we will come to the exact solution. There are 66 such ways. I will prove it to you. Let's first try to derive the formula and then we will apply on this example. Okay. So before going to the formula, these three problem statements are equivalent. So I will read this out. So these three problem statements all denote combination with repetition. So first is the number of combinations of n objects taken r at a time with repetition allowed. So in the juice example, we had three objects, three flavored juices, F1, F2, F3. There were three objects and we had to take 10 at a time because 10 friends went to the shop. So we had to take 10 at a time. So in that example, there were three objects and we have to take 10 at a time with repetition allowed. Okay, repetition was allowed. You can take any number of F1 flavored juice. So this is one type of combination repetition problem. This is equivalent to say that. So also firstly let's see the mapping between this statement and this statement. This we have already done. So let's see the mapping between this and this. So this is let's say statement 1. This is let's say statement 2 and this is let's say statement 2. We already know that statement 1 and 3 are equivalent. Why? The number of combination of n objects. So we have n objects. Object 1, object 2, object n. And we have infinite supply of all these. We have to take r objects. So how do we do that? We assume that let's say we take x1 objects of type O1. We take x2 objects of type O2. And similarly we take xn objects of type On. So the number of solutions to this equation x1 plus x2 up to xn is equal to r will be equal to the number of ways in which we can solve this problem. We have seen this, okay? And the condition is the condition is mentioned here, the number of non-negative integral solutions of this equation. What does it mean? That all the values of x1, x2, x3 up to xn should be non-negative, which means x1, x2 up to xn should be greater than or equal to 0. All of them should be greater than or equal to 0. Right? I hope you got the mapping, right? Now there is another way to formulate the same problem, which is statement number 2. Let's see that. So the number of ways in which are identical objects. This is a slightly trickier way to formulate the same equation. The number of ways in which are identical objects can be distributed among n distinct containers. So this is different problem now. Think of it this way. Let's say you have r identical pens 1, 2, 3, n. Okay, this is first pen, second pen, third pen, and this is rth pen. You have r identical pens, okay, and you want to distribute r pens among let's say 5 students. So first student can get 6 pens, second student can get 5 pens, and so on, right? But the equation again becomes the same thing. So let's say there are 5 students. You want to distribute these r objects among 5 students, S1, S2. There are 5 different containers. There are 5 different containers. Okay, but are identical objects. So you want to distribute these among this, and there is no condition mentioned, which means that some container might be empty. So it might be possible that S1 is not getting any object, right? So the equation again becomes what? Let's say S1 gets x1 objects. The same equation, okay? S1 let's say gets x1 objects, S2 gets x2 objects, S3 gets x3 objects, and S5 gets x5 objects. Okay, I should draw this. This is the 4th student, it is getting x4 objects. So what is the condition? That the sum of all the number of objects which all of them are getting should be equal to r. Again, we are getting the same equation. So the number of different solutions to this equation is equal to the number of ways in which we can do this. So now see, it becomes tricky. These two statements are very different in some sense. Here we have n different objects, and we have to take r at a time with repetition. Okay, so this might get tricky. Okay, you have to read the problem statement very carefully. That's why I always tell you, never remember the statements. Okay, whenever a question from combination repetition comes, read the problem carefully and always map it to an equation. Logically, map it to an equation which you can solve. A mathematical equation for which the number of solutions you have to find. Okay, we still have not counted the number of solutions. We will do it in the next slide. But that's how you should do it. Any problem statement with repetition comes, map it to an equation which you can solve and then solve it. Okay. Otherwise, you get confused. Here you had n different objects in an array data. Here you had r identical objects, and you have to place them in n distinct containers. Okay. So, but mapping both of them to equation number 3 is easy, right? So always map them to equation number 3, and then we will solve it. So now let's solve this equation. So what we want to do? We want to find a number of possible solutions to this equation. x1 plus x2 plus xn is equal to r. We just have to find the number of solutions to this equation, where x1, x2 up to xn are all non-negative integers, which means they are all greater than or equal to 0. They can take all values from 0 to n. Okay. So how will we do that? So we shall derive this using an example. Okay. Let's try to find out this example. 10 friends go to a shop and there were 3 flavors of juices. So here the equation was x1, first friend was taking, so for flavor 1, there were x1 juices, for flavor 2, there were x2 juices, and for flavor 3, there were x3 juices, and we have to distribute it to 10 people. Okay, so we have to find a number of solutions to this equation. So how will we do that? And I already told you one such solution is 10, 0, 0. One such solution is 0, 10, 0. One such solution is 9, 1, 0. And so on. And one solution was 5, 2, 3. So there are many solutions. Okay, there are 66 solutions. How do I derive that? So there is a standard way to solve this problem. Every combination repetition problem will be mapped to an equation, and every equation will be mapped to that logic. So what is the logic? See, you have 3 unknowns in the equation, and their sum has to be equal to some value r. So draw 12 boxes. Why am I drawing 12 boxes? You will know soon, okay? So I have drawn 12 boxes. Now, what is 12? Here 12. So see, the equation was x1 plus x2 up to xn is equal to r. So you have to draw exactly n plus r minus n boxes. And I will tell you why, okay? Like there is a logic behind everything. So I draw 12 boxes. And I insert 2 sticks in any of these 12 boxes. You have to insert 2 sticks in any of the 12 boxes and you'll get a different solution to this equation. See how? Let's say I insert it here and here. If I insert 2 sticks here and here, this is a different solution to this equation. How? This is a solution like 3 plus 4 plus 3. You have 3 boxes here, 4 here and 3 here. You are sticking 2 sticks in these 12 boxes, right? So you will always have 10 boxes left, and they will represent a unique solution every time to this equation. So 3 plus 4 plus 3 is a different solution. For example, let's say you insert 2 sticks here and here. So what is the solution here? You have 0 boxes here, 0 boxes here, and 10 boxes here. So this is a different solution. 0 plus 0 plus 10. Similarly, you can insert here and here. This now becomes a different solution. How? This becomes 10 plus 0 plus 0. This is a different solution, right? So every time you insert 2 sticks, in these 12 boxes, you get a unique solution to this equation. I hope you agree. Try and find out. Okay, you insert 2 sticks anywhere, you will have a different combination. X1 number of boxes here, x2 number of boxes here, and xn number of boxes here. So, and like we already know how to do that. We already know how to count the number of ways in which we can pick 2 boxes up to 12 boxes and insert sticks, right? Like so, it is 12C2. We just have to select 2 boxes up to 12 boxes. So there are 12C2 ways in which we can select 2 boxes, and we will automatically have a partition 1, 2, 3. The number of boxes will be a solution to this equation. So there are 12C2 solutions to this equation. That number of solutions. The different variations in which we can write values of x1, x2 and x3 such that x1 plus x2 plus x3 is equal to 10. 12C2 is what? 66. Okay. So this is how you solve this question. Now let's solve the generic equation. Okay. Now let's solve the generic equation. So in a similar way, we will solve the generic equation as well. You have to solve this equation. You have to count the number of ways in like the number of possible solutions for this equation where x1, x2, xn are all non-negative. They can be 0 or any value like greater than equal to 0. So here similar way, create n plus r minus 1 boxes. Why n plus r minus 1? I already told you in the last example. When you had n equal to 3, when you had n equal to 3 and r equal to 10, you actually created 12 boxes and inserted 2 steps so that you get 3 partitions. See, this is the number of partitions that you want. This is the number of partitions that you want, right? So you will always insert n minus 1 sticks. If you insert n minus 1 sticks, you will get n partitions, right? So when you had like 12 boxes, let's say you have 5 boxes. If you insert 1 stick, you get 2 partitions. So if you want n partitions, you need n minus 1 sticks. So this is the number of sticks that you will insert n minus 1. And after inserting n minus 1 sticks, what do I want? I want total sum of boxes to be equal to r. Right? The total sum of boxes should be equal to r after inserting n minus 1 sticks. So the total number of boxes we need initially should be n minus 1 plus r. Right? That's how it comes. We need n plus r minus 1 boxes. In n plus r minus 1 boxes, and we need n minus 1 sticks. Insert n minus 1 sticks anywhere. So mathematically, you will have r boxes left. When you eliminate n minus 1 boxes out of these boxes, you will get r boxes left. Automatically, it will be r. So the total number of boxes left will be r. So total sum of all the elements will be equal to r. So you will have n separations and n separations, and the total sum of separations will be equal to r. So that will be a number of ways in which you can actually find the values of x1, x2 up to xn, such that it satisfies this equation. So how many ways you can do it? You have n plus r minus 1 boxes, and you have to choose any n minus 1 out of them. So n plus r minus 1, choose n minus 1. This is the number of ways in which we can actually select r objects out of n objects with repetition allowed. This is also the number of ways in which we can distribute r identical objects among n distinct containers, and this is also the number of ways, the number of solutions to this equation. Okay, where all x1, x2 up to xn are non-negative. So, and you can see the formula which we came up with was n plus r minus 1 cn minus 1, and we know that ncr is equal to ncn minus r. This is combination. This is k selection is equal to k rejections, right? So this will also become equal to n plus r minus 1 cr. Okay, these two are equal. So yeah, this is the formula that we have. The number of combinations of n objects taken r at a time with repetition is n plus r minus 1 cr, or n plus r minus 1 factorial, or r factorial n minus 1 factorial, where n is the number of things to choose from, and we choose r of them with repetition allowed, and order doesn't matter. Okay, the order doesn't matter, it is combination, just selection, not arrangement. And interestingly, we can use k rejection equal to k selection. So this formula is same as this formula. You will see sometimes n plus r minus 1 choose r, sometimes you will see n plus r minus 1 choose n minus 1. Okay, so like any of these two formulas, and they are both equal to this. So with examples, it will be more clear. Okay, never remember the formula. I never remember formulas while doing counting. Okay, always try to map a question to the equation, and solving the equation is very easy. Like draw boxes and mistakes. It will be very simple. So let's say this question: in how many ways can 50 be represented as a sum of? In how many ways can 50 be represented as a sum of 3 whole numbers? Whole number is what? Again, the same thing, right? Non-negative integers. Whole number is 0, 1, 2 up to anything. So again, like, this is a question, map it to the equation. In how many ways can 50 be represented as the sum of three whole numbers? Let's say that these three whole numbers are x, y, and z. So we want x plus y plus z is equal to 50. So in how many ways can we represent 50 as a sum of three whole numbers? So it is equal to the number of ways, number of solutions to this equation in which x, y, z are all greater than equal to 0. Okay, the stick method works only if they can be greater than equal to 0. Because that's how we did it. Like, so when we had 12 boxes and we inserted sticks here and here. So here the number of boxes left was 0, here also it was 0, and here it was right? Or 12. 10 boxes left, right? So 0 plus 0 plus 10 was also a solution. So the elements can be 0 also. So this method only works if x, y, z can be written equal to 0. So here, how will we do it? So here n is equal to 3, r is equal to 50. So always, like, never remember the formula. If you want to do 3 partitions, you will need 2 sticks. So just add the number of sticks to this number. So you will need 52 boxes here. In 52 boxes, you just insert 2 sticks anywhere. So you will be remaining with 50 boxes, and there will be 3 partitions. So always go with this. You need 3 partitions, so 2 plus 50, 52. So from 52 boxes, you need to choose 2 boxes where you will insert sticks. So this is the number of ways in which 50 can be represented as sum of three whole numbers. If you calculate this, it will come out to 52 into 51 upon 2, and you can solve it, it will come out to 1326. Okay, so this is the number of ways. Now there is a tricky question which you can try. We will discuss it in tomorrow's lecture. So in how many ways can 50 be represented as a sum of 3 natural numbers? We saw whole numbers. In whole numbers, the equation was this: x plus y plus z is equal to 50, where x, y, and z all were greater than equal to 0. But now we have to represent 50 as a sum of 3 natural numbers. So the equation becomes x plus y plus z is equal to 50. But now natural numbers are numbers greater than equal to 1. So they all have to be greater than equal to 1. So you can try this out. And so this was first part of combination repetition. We will solve a few more problems in the other lecture. So yeah, we will upload it tomorrow. Okay. Hi everyone. So welcome to lecture number 6 of counting. So we are doing data science and AI complete course, and we are discussing counting. And section number 6, and we will continue discussing combination with repetition. We started it in the last class, and we said that whenever we have n objects and we have to pick r at a time, and repetition is allowed, then it comes under the category of combination with repetition. Always remember combination with selection. So arrangement is not important, just the selection is. So always map it to like cricket example or something, like have a mapping. Okay. So, and if arrangement is there, we will see it later. It is permutation with repetition. Okay, we will see that as well. So, but permutation is repetition. With repetition will be very simple problem. We will solve it like in this lecture only. The more difficult problem to solve is combination with repetition, because always counting the number of selections is slightly difficult, because there we tend to overcount. Whenever arrangement is important, that problem can be solved like by making I spaces, and you will have options to choose. Okay, that is easier to solve. I will tell you in this lecture. Okay, but combination or selection problem is slightly trickier, and that's why like I emphasize more on combination repetition or selection. Okay, cool. So let's continue. We have already seen that the number of combinations of n objects taken r at a time. That this problem will be difficult. Always map it to an equation. So you have n objects taken r at a time. So you take x1 of first object, x2 of second object, x2 of second object, and so on to xn of nth object, and total number of objects you have to take is r. So number of non-integral solutions, non-negative integral solutions to this equation is equal to your draw n plus r minus 1 boxes, and you insert n minus 1 sticks. So you will get n separations, and total number of boxes left will be r. So this is the number of solutions to this equation. Okay, and this is also equal to n plus r minus 1 choose r. We know that by k selections for k rejections, and this formula comes out to be this. We have seen this. So now let's solve some examples. So the first example is, in how many ways can 100 identical candies be distributed among 7 children. Okay, so this is a different way of forming that equation. Okay, so always combination repetition might not be as it looks. So the standard way to write is like n objects and take at a time with repetition error. But the problem can be formulated in a different way like this. So that's why I told you not to remember formula. Always map it to equation. So you have to distribute 100 identical candies. So let's say this is a candy box and it has 100 candies, exactly 100 candies, and they are all the same, identical candies. And you have to distribute among 7 children. Now 7 children are different here. This is the first child, second, and you have 7 children. And you have to distribute these 100 identical candies to this. So you might be unfair. Some child might be you don't want to give any candies to them. That is okay. No condition is mentioned. So you can assume that some of the children might get 0 candies also. So it's the standard problem. So let's say first child gets C1 candies, C2 candies, and so on. The 7th child gets 7 candies. So you have to distribute total 100 candies, right? So you just have to find the number of solutions to this equation where all C1, C2, and C1 up to Cn can be greater than equal to 0. So we already know how to do this. Don't remember the formula. How do you do that? If you have to make 7 partitions, you have to insert 6 sticks. So you have to create 106 boxes and you have to insert 6 sticks in them, so that you will have 7 partitions. So the number of solutions to this equation is 106 C6. You can go to the formula as well. N is equal to 7, R is equal to 100, N plus R minus 1, choose N minus 1. So there are 106 C6 ways. It will be a large number. I'm not calculating it, but this is the answer. Okay. So now let's move to the next problem. In how many ways can we fill a bucket with 100 balls of 7 colors? Again, a really different way to solve it. Okay, form the problem. Previously, it was 100 identical candies, right? 100 identical candies and 7 different children. Here it is 100. Here there are 100 balls. Okay, so you have to fill a bucket. There is only one bucket. This is your bucket. And you have to fill it with 100 balls of 7 different colors. And here you can assume that all balls of one particular color are same, right? So you have ball with 7 colors, and here also nothing is mentioned. So you can assume there is an infinite supply of all the balls. Nothing is mentioned, so you will assume, right? You will assume that you have 100 balls of red color or any color. You have infinite supply. So basically, there are 7 colors. Let's say a red, green, and so on. Okay. So let's say with your anything, right? Let's say there are 7 colors: violet, indigo, blue, green, yellow, orange, and red. And you have to fill a bucket with 100 balls of these colors. So you will have a few white balls, you will have a few yellow balls, you will have balls with different colors. Okay. Okay. So you can have red balls or blue balls or green balls. You will have 100 balls but of different colors. Okay, in this. So basically, what you want to do, you can have all 100 violet balls. You can have all 100 red balls also, and you can have some combinations. Like you can have 20 violet balls plus 20 indigo balls, and so on, 5 red balls. But their sum should be equal to 100 because you have to fill 100 balls in this bucket. So what is it? So let's say you have x1 balls of the first color, x2 balls of the second color, and so on. You have x7 balls of the 7th color. You have x7 balls of the 7th color, and total number of balls you want is 100. Always map it to equation. It will be very simple. Okay, and you have to solve this equation, and you might pick 0 balls of any color, right? So again, you have to solve the problem. In the last problem, we also had the same equation. So the number of ways in which you can do it is 106 C6. Okay, or you can apply the formula as well. So this is what you get. Okay, let's move to the next example. This is a problem which I gave you as a homework, right, in the last lecture. In how many ways can 50 be represented as a sum of 3 natural numbers? We already solved it for 3 whole numbers. Whole number are greater than or equal to 0. That was simpler. So there the equation was x1 plus x2 plus x3 is equal to 50. And x1, x2, x3 were all 3 were greater than or equal to 0. This was the equation which we already solved, and the answer would be 52C2. But now the problem is slightly different. So you have to represent 50 as a sum of three natural numbers. Okay. So here the equation changes a little bit. Okay. So here the equation is this. But since natural numbers are greater than or equal to 1, so x1 has to be greater than or equal to 1, x2 has to be greater than or equal to 1, and x3 has to be greater than or equal to 1. Okay. So try to solve it. I'll give you the solution now. So whenever a question like this comes, try to map it to whole number problem. How? X1 can be greater than or equal to 1, right? So there is a standard trick to do it. I want to map it to a problem to a different space. I want to map it to a different space in which the variables are greater than or equal to 0, not greater than or equal to 1, because that I can solve. So why not write x1 as 1 plus a? I am writing x1 as 1 plus a. Basically what I am trying to do is, since x1 has to be greater than or equal to 1, I am giving one, like I am making sure that x1 will be at least 1. So I will basically write x1 as 1 plus a, and I will write x2 as 1 plus b, and I will write x3 as 1 plus c. Why? This way I am ensuring that x1 is at least 1. Now a can be greater than or equal to 0. So if a is 7, x1 will become 8. If a is 0, x1 will become 1. Right? So this way I am making sure that x1 is at least 1, x2 is at least 1, and x3 is at least 1. So basically I am writing x1 as 1 plus a, x2 is 1 plus b, and x3 is 1 plus c. This will work with any value. If x3 had been greater than or equal to 5, I will write x3 as 5 plus c. So what will this equation become? So write it this way. This equation will become 3 plus a plus b plus c. 1 is 3. A plus b plus c is equal to 50. And now consider this. So now this is magical, right? Now since x1 is greater than or equal to 1, and I am writing x1 as 1 plus a, so it becomes 1 plus a greater than or equal to 1. So it means a has to be greater than or equal to 0. This is what I wanted. So this equation is equivalent to this equation. A, B, and C have to be greater than or equal to 0. Right? And this equation I already know how to solve. Basically, I am giving 1, 1, 1 to x1, x2, x3 already. So now 50 becomes 47 only. Right? So this equation is nothing but a plus b plus c is equal to 47. And now ABC can be anything greater than or equal to 0. So this how to solve 47 and like 2 partitions, so 49 C2. If you create 49 boxes, insert 2 sticks, you will get like all the different ways in which you can solve this problem. Okay. So there are 49 C2 ways in which 50 can be represented as a sum of 3 natural numbers. How to solve it? Always combination. So like always go with combination first. 49 into 48 upon 2. This is 49 C2. It will be 1176 eventually. Okay. So coming to the next problem. So right now in these problems we assume that we had an infinite supply of objects. When I said that you have n objects and you take r at a time, I assume that I have infinite supply of all the objects. Infinite means like I don't want infinite. I need at max r. I will not take r plus 1 anyway. But I was assuming basically that I have what I will need. So when I said that I need the number of solutions to this equation x1 plus x2 plus x3 is equal to let's say 10. Right? I assume that x1 I have enough supply of x1. I have at least 10 x1s. I will not need more than 10. But that's what infinite means here, right? So sometimes it is possible that you are not given an infinite supply of x1 and x2. So it is restricted. So the only equation right now, the condition was x1 has to be greater than or equal to 0. Right? What if they add one more condition? The x1 should be less than or equal to 5. Right? x1 cannot go beyond 5. You don't have an infinite supply. Instead, you have a limited supply. You only have 5 x1s and so on. So that is a slightly trickier problem. And the most complicated versions of these problems can be solved only using inclusion and exclusion. So we will need both combination repetition and inclusion and exclusion. So we will see inclusion and exclusion in the later part of this course in the same playlist. But for now, this problem can be solved without inclusion and exclusion. That's why I did it here. Okay. More complicated decisions we will solve later. So right now this problem, let's see. A girl has choose 4 items from a bucket which contains 3 red, 3 green and 4 blue balls. It contained 3 red, 3 green and 4 blue balls. Okay? And we have to pick 4 items out of it, 4 balls out of it. Right? So had it been we had an infinite supply, this problem would have been simpler. Let's say you are taking R red balls and G green balls and B blue balls. So you have to take 4 balls total and we have an infinite supply. You just have to solve this problem where R, G, B can be written equal to 0. So then the number of solutions would have been 62. Right? But now this is not the problem. So here there is a constraint. The constraint is you only have 3 red balls, you only have 3 green balls, and you have 4 blue balls. So basically, here R can be anything between 0 and 3. R can be anything between 0 and 3. G can be anything between 0 and 3. B can be anything between 0 and 4. This is the constraint that we are adding. Okay? We are not having an infinite supply, we are having a limitation on total number of objects that we have. See, let's solve this problem first, assuming that we have an infinite supply. We know that there are 62 possible solutions to this equation, right? N plus R minus 1 choose N minus 1. So 62 becomes 6 into 5 upon 2, which is 15. There are 15 solutions, different solutions to this equation. But we cannot, so we have to eliminate all those choices which are exploiting these conditions, right? There are only 2 cases in which this condition is not satisfied. Think about it. Since we see blue balls, we already have 4. We don't care. We will not need more than 4 balls anyway, right? So if the solution is 0, 0, 4, 4 red, 4 green and 4 blue, it is allowed because we have 4 blue balls. But this solution is not allowed, 4, 0, 0. Why? Because we don't have 4 red balls. We only have 3 red balls. 4 red balls is not allowed, and this solution will be a part of these 15 solutions. So there are only 2 solutions which are prohibited. What are those? In which we are taking all 4 red balls and in which we are taking all 4 green balls. These 2 solutions are not allowed. Otherwise, everything is allowed if you see the conditions, right? More complex problems, see here it was easier. There are only 2 options to be eliminated. Sometimes it will be very large. So that we will solve using inclusion exclusion. That's a different principle. But for now, among these 15 choices, only 2 are prohibited. So we will remove those. So we have 13 possible ways or 13 possible solutions to this question. Okay. I hope you got it. Okay. Also write in the comment section if you have problems in any of these questions and read them and answer them in the comment section itself. And also I will be having live doubt solving and problem solving sessions. You can ask them there. Cool. So this was all about combination with repetition. So we were selecting objects, R objects out of N objects, where repetition was allowed. Only selection. The order was not important. In which order I am taking, that was not important. The only thing important was how many X1 items I am taking, how many X2 and so on. Right? But now we can have permutation with repetition as well. Okay. What is permutation with repetition? Again, we have an objects, we are taking R at a time, but order is important. Order is important. And now the problems become much easier. You will see. Okay. So what happens is you have n different type of objects. You have object 1, object 2, object 3. You have n different type of objects, and we have n choices each time. So basically, what we want to do is we have R places to fill. We have R places to fill, and the order is important. So basically, you can take any object for the first place. You can have, let's say, the 7th object here. You can have again the 7th object here. You can have the nth object here. You can have the first object here. You can have the second object here. So for every place, you have n options. Fill the first place and fill the second place, you have n options, and fill the third place, you have n options. Rule of product and. So it will become n to the power r. See, this was a very simpler problem because here the order was important. So basically, if you have, so like we saw the problem, right? In the previous lecture, you have A, B, C, D, and you have to fill 3 places. In the previous lecture, we saw it was combination with repetition. How many selections of 3 objects are possible from A, B, C, D? Only selection. So here A, B, and A, B, A were same, I told you, because both are 2 A's and 1 B. But in permutation, these two are different. So it becomes a very easier problem, because how do you solve it? You just take 3 options, like three places, and for every such place you have 4 different options: A, B, C, D, A, B, C, D, and A, B, C, D. Take any one of them; it will be different permutation. So it will be 4 3. So permutation with repetition is like very simple problem. If you have n objects and you have to fill r places, you have n options for everyone. So n to the power r. So it becomes n to the power r. Okay. In combination, it was n plus r minus 1. Choose n minus 1. Cool. So I hope you got it. In the next lecture, we will solve a few problems on permutation, basically whatever we have discussed: permutations, combinations, factorial, with repetition, without repetition, everything. Okay, so we will solve a few problems so that it will be more clear. Hi everyone. So welcome to lecture number 7 of the counting course that we are doing. It is a part of data science and AI course, complete lead course on YouTube. So in this lecture, we will solve a few problems on whatever we have discussed in the previous 6 lectures, like factorials, permutation, combination, with and without repetition. Okay, so I will try to take a generic example and try to explain like where to apply which thing, like combination with repetition, permutation with repetition, without repetition, combination, and so on. So we have discussed so many things, but like for what type of problem, what formula, or like what logic do we apply, that we will see in this lecture. Okay. So firstly, a quick recap. So for combination with repetition, the number of combinations of n objects taken r at a time when repetition is allowed was n plus r minus 1. Choose r. For permutation with repetition, like you have r places, n objects, it doesn't matter, like you have n options for every place, so you have n to the power r options. So just to summarize everything, if the order matters, see, like I told you, the difference between permutation and combination was what? In permutation, order matters, it is arrangement. In combination, order doesn't matter in which order we are picking, only the selection matters. So if order matters, it is permutation. If order doesn't matter, it is combination. And also the question might be like the repetition is allowed or not. So if order matters and repetition is not allowed, so basically you have n objects and you have r places. So you have n options for the first place. For the second, since repetition is not allowed, you will have n minus 1 options for the second place. And so on. You have n minus 2 options for the third place, and basically you will have n minus r minus 1 options for the last place. So the number of permutations was NPR. You already saw it, okay? NPR. The number of ways in which we can arrange r objects out of n objects. Now, if the order doesn't matter and you cannot repeat objects, it is just like selecting r objects out of n objects. So here we were overcounting. So we divided it by r factorial because we were overcounting every combination r factorial times. So it became NCR, the number of ways in which we can choose r objects out of n objects with no repetition allowed. Now, if permutation, if order is important, so you have to arrange, but repetition is allowed. So basically, for every place, since repetition is allowed, you have n options here and n options here and n options here and so on. So it becomes n to the power r. Permutation with repetition. And if order doesn't matter and repetition is allowed, so it is combination with repetition. That's the most complicated one. And here you have to map it to an equation x1 plus x2 up to xn equal to r. And the number of ways to solve that equation is n plus r minus 1. Choose r, which is this. So this is the summary of what the formulas which we have seen so far. Okay. So now let's solve some problems. So always like when solving problems, pause the video. I will like step aside and you can pause the video and then you can try to solve it on your own and then you just see the solution. Okay. So this is the first example. So in how many distinct non-negative integral solutions are there? Again, non-negative integral solutions. So basically x1, x2, x3 can be all greater than or equal to 0. So how many distinct non-negative integral solutions are there for the system of equations? This. So anyways, they are non-negative integral solutions because x1 is greater than or equal to 2, x2 is greater than or equal to 3, x3 is greater than or equal to 1. So it's a standard problem. We already saw how to solve it. So see, if x1, x2, x3 had been greater than or equal to 0, the problem would have been simpler, right? We already know it. If x1, x2, so if the problem was this, x1 plus x2 plus x3 is equal to 12, and x1, x2, x3 greater than or equal to 0. If the problem had been this, we already know how to solve it. Just create 12 plus, since we want 3 partitions, we will insert 2 sticks. So 12 plus 2 is n plus r minus 1 is 14. In 14 boxes, you insert 2 sticks and you will get a different solution every time. N plus r minus 1, choose n minus 1. So 14 C2 ways in which we can solve this problem. But here we have a constraint. x1 has to be greater than or equal to 2, x2 has to be greater than or equal to 3, and x3 has to be greater than or equal to 1. So what we will do, we will try to map this problem in some another space which we find easier. Since x1 has to be greater than or equal to 2, see here we will have a solution like this also, 0 plus 12. But this is not allowed. Since x1 has to be greater than or equal to 2 and x2 has to be greater than or equal to 3, this is not allowed. This has to be at least 2, this has to be at least 3. This is allowed. Okay? 2 plus 3 plus whatever, 7. Right? But this is not allowed. So we will map it to some other space. So basically we will give at least 2 to x1. We will give at least 3 to x2. We will give at least 1 to x3. So basically we will write x1 as 2 plus a. And we will write x2 as, since x2 has to be greater than or equal to 3, we will write x2 as 3 plus b. And since x3 is greater than or equal to 1, we will write x3 as 1 plus c is equal to 12. Okay, we are writing x1 as 2 plus a, x2 as 3 plus b, and x3 as 1 plus c. So this way the equation becomes this, and since x1 is greater than or equal to 2, and I am writing x1 as 1 plus a, 2 plus a, so this equation becomes this. So basically now the equation becomes a is greater than or equal to 0. That's what I wanted. Similarly for x2 also, I am writing it as 3 plus b, so it will become b is greater than or equal to 0 and c is greater than or equal to 0. So now this equation becomes this with a, b and c greater than or equal to 0. So this equation is nothing but a plus b plus c a plus b plus c is equal to what? 3 plus 2, 5 plus 1, 6. A plus b plus c is equal to 6. A, m, e and c greater than or equal to 0. You already know how to solve it. 6 plus 2, 8 C2 solutions. N plus r minus 1, choose n minus 1. So 8 C2 solutions are there to this equation, which is 8 into 7 by 2, 28. Okay, there are 28 solutions to this equation. Okay, now a different question with more complications. So now we will try to solve this. So just pause the video and try to solve it on your own. Cool. So this is the system of equations that we want to solve. Okay, x1 plus x2 plus x3 is equal to 12. x1 has to be between 2 and 10 inclusive. x2 and x3 can be anything between 0 and 12. So there are no restrictions on x2 and x3. Basically they can be anything between 0 and 12. So there is basically an infinite supply of x2 and x3, you can assume, right? Because anyways we will never have x2 as 15. Like that won't satisfy, right? So x2 and x3 we have infinite supply. We have 12 of them. There is a restriction on x1 alone. It has to be between 2 and 10. So this side wala inequality we already know how to solve. If x1 has to be greater than or equal to 2, that we already know. How to solve that? Just give at least 2 to x1. So write x1 as 2 plus 8. So at least, so we will do that first and then we will see how to solve the problem, okay? So, okay, firstly, like very basic thing, how to solve this problem, x1 plus x2 plus x3 is equal to 12, where x1, x2, x3 are all greater than or equal to 0. If only this was the restriction, we know that there are 14 C2 solutions. Okay, we'll apply the formula 12 plus 2 C2, okay? Now, forget about this, we have a new restriction, and that restriction is that, okay, I am not taking x2 and x3 in the picture because x2, x3 have no restrictions, okay? So now the question is, x1 has to be between 2 and 10, okay? For now, let's, okay, so how to solve this side of the formula, this side of the equation? Since x1 has to be greater than or equal to 2, I will write x1 as 2 plus a. So that x1 is now greater than or equal to 0. So now I will write x1 as 2 plus a. So this will become 2 plus a plus x2 plus x3 is equal to 12. 2 plus a. So now this equation will become what? Since x1 is 2 plus a, I will write it this way. 2 is less than or equal to 2 plus a is less than or equal to 10. Subtract 2 everywhere, it will become 0 is less than or equal to a is less than or equal to 8. Right? I have written x1 as 2 plus a. So x1 has to lie between 2 and 10. So now a has to lie between 0 and 8. Right? So now this equation is what? A plus x2 plus x3 is equal to 10. We don't have restrictions on x2 and x3. Basically, x2 and x3 are between they are still between 0 and 12. So they have to be just greater than or equal to 0 and less than or equal to 12. Less than or equal to 12 will always satisfy, right? Because the equation is only up to 10. So this will anyway satisfy. But the more difficult problem is a has to be between 0 and 8. So this side of problem is now okay. A has to be greater than or equal to 0. So if the problem had been only this, if this restriction had not been there, then the number of solutions would have been 12C2. If we remove this restriction, A has to be less than or equal to 8, then A, x2, x3 can be anything greater than or equal to 0. Then the number of solutions to this system of equations would be what? 12C2, n plus r minus 1, choose n minus 1. But among these 12C2 solutions, I told you, the more generic way to solve this problem is using inclusion and exclusion, right? But here we don't need inclusion exclusion. Here we are just overcounting a few solutions. What are we overcounting? See, A has to be less than or equal to 8. Which means that the only values which are not allowed in A are what? A cannot be equal to 9 and A cannot be equal to 10. Right? If we are solving this equation without this condition, we will have a few solutions, like we will have A equal to 9, x2 equal to 1 and x3 equal to 0. We will have one solution as A is equal to 9, x2 is equal to 0 and x3 is equal to 1. And we will have one solution A is equal to 10, x2 and x3 are 0. These three solutions are not allowed. I hope you got it, right? These three solutions are not allowed because A is less than or equal to 8, A cannot be equal to 9 or 10. These are the only three solutions in which A is exceeding 8. Right? So basically these are the three solutions which we are overcounting. So we have to reduce them. So there were 12C2 total solutions to this equation. 12C2 minus 3 is our answer. We have three solutions we are overcounting. So what it will become? 12 into 11 by 2 minus 3, which is 66 minus 3. 63. So there are 63 different solutions to this equation, system of equations, okay? So always like it will be a simple problem, solve this side of equation first and then this equation will reduce and you have to subtract what you are overcounting. Okay? So now let's move to the next problem. Your mother-in-law buys 1,000 small gifts. Buys 1,000 small gifts to give to relatives for Christmas. 1,000 gifts. Each of the 1,000 items are different. 1,000 different small items. Okay, I1, I2, up to I1000. There are 1,000 different items. There are 25 relatives to give these gifts to. There are 25 relatives. How many ways are there to distribute the gifts? Okay, so nothing is mentioned. So basically any relative can get any number of items and all the items are different. And since nothing is mentioned, you cannot repeat these items, right? By default, like if you read this problem statement, it is very clear that you cannot repeat the items. If you have given some gift to someone, you cannot give one gift to two people basically. There are exactly 1,000 different items, gifts, and you have to distribute to 25 people. That's all. So how will you do that? So basically for just create buckets. Let's say this is first relative. This is second relative. This is third relative. And this is 25th relative. And let's say I'll name gifts better. Let's say I have 1000 gifts, right? So I'll write it here. Let's say this is the first gift, G1, G2, G3, and so on. I have 1000 gifts. I have 1000 gifts. So how to solve it? Any relative can get any number of gifts. So solve it this way, okay? Rule of product. For the first gift, so basically solve it using the rule of product. Distribute gift first for the first gift, and then distribute the second gift, and then distribute the third gift, and so on, and then distribute the 1000 gift. So and okay, multiply. So in how many ways can I distribute the first gift? I have 25 relatives. I can give the first gift to anyone. I have 25 options for the first gift. I can give it to any relative. And I have 25 options for the second gift. I have 25 options for the third gift. And so on. I have 25 options for the 1000 gift. So basically I have 25 different options for any gift. So this is how I'm writing it. Let's say this is the first gift, second gift, and the 1000 gift. So basically, let's say I'm giving this gift to relative, third relative. This I'm giving it to 17th relative, and so on. Like this I'm giving it to the first relative. So this is one possible option way to do that. Or I can give all the gifts to the first relative only. That is also an option. Okay, and so on. So basically, I have 25 options for all the gift items. So the number of ways will become 25 to the power 1000. 25 into 25 into 25,000 times. 25 to the power 1000. Okay, this is the number of ways in which I can distribute these gifts. Now let's see another variation of the problem. So again, your mother-in-law buys 1000 small gifts to give to relatives for Christmas. Each of the 1000 gifts are again different. Again, there are 25 relatives to give these gifts to. But now, how many ways can these gifts be distributed so that each person gets 40 items? Now, previously there was no restriction on any gift. One gift can go to anyone. But now there is a restriction for every gift. Every person should get exactly 40 items. See, there are 25 relatives and if everyone gets 40 items, it is 1000. Basically, you are distributing every gift. But you are not doing partiality. You have 1000 different gifts, but you will give 40 gifts to everyone, every of the 25 relatives. So in how many ways can this distribution be done? So think of it now. So let's say this is the first item. This is the second gift. This is the third gift. And this is the 1000 gift. Okay. And this is the gift box. Like it contains all the 1000 gifts. Okay. And for every relative, let's say this is my first relative, this is my second relative, and this is my 25th relative. Now what happens here? See, it doesn't matter. Let's say the first relative is getting the first 25 gifts. The first 25 gifts. The second relative is getting the first 40 gifts. Okay, every relative is getting 40 gifts, right? Okay, so every relative is getting 40 gifts. So let's say this is my first relative. This is my second relative. So let's say the first relative is getting the first 40 gifts. And the second relative is getting the next 40 gifts. And so on. This is one possible option, right? But the order doesn't matter, right? The relative 1 doesn't care if the first relative is getting 1, 2, 3 up to 40 or 2, 1, 3 up to 40. The order doesn't matter. You just have to pick any 40 items out of this 1000 items and give it to first relative. Then from the remaining items, you take 40 items and give it to the second relative and so on. So if you have to break this problem down using the rule of product, how will you do it? So let's say you have 1000 gifts to give to. So let's say this is your first task T1. It is distribute. Not distribute. So I should write it this way. So this is my first task. Give 40 items. Give any 40 items. Give 40 items to the first relative. This is my first task. And then my second task will be to give 40 items to the second relative. Right? Because I have to distribute exactly 40 items to R2. Right? But here, when I am distributing to first relative, I have 1000 items. So out of 1000 items, I have to select 40 and give it to R1. Here, when I have already given 40 items, I am left with only 960 items. So from the remaining 960 items, I have to take 40 items and give it to R2. So from the remaining 960, this is my task T2. And the third task will be, now give 40 items to R3, the third relative, but now you are left with only 920 items. Since you have already consumed 80 items, 40 here and 40 here. So from the remaining 920, you give 40 to R3 and so on. For the last relative, the 25th relative, you will be left with 40 items only. So you have to give the remaining 40 items to this relative. Okay, there is only one way to do that. Just give the last 40 gifts to the 25th relative. So in this way, I am counting all possible options. Okay, and this problem can be solved using a very beautiful equation as well, which is called the multinomial equation or the multinomial theorem. We will see it in the next lecture. But there is another way to see this problem. Okay, by creating a multinomial equation. But I hope you are getting it. Okay, the formula here. So what we are doing here basically, from the first 1000 items. So what is the number of ways to do the first task? Choose any 25 items and give it to the first relative. This is my T1. And then from the remaining 960 items, choose 25 items and give it to the second relative. And then from the, not 25, we are selecting 40. Okay, so from 1000 we select 40, then from the remaining 960 we select 40, then from the remaining 920 we select 40, and so on all the way up to the 25th relative where we have 40 items and we select 40 and give it to that guy. Okay, so now how to solve this equation? You can expand it. So this 1000 C40 will become 1000 factorial upon 40 factorial times 960 factorial. N factorial upon R factorial, N minus R factorial. Similarly, the second one will become 960 factorial upon R factorial, N minus R factorial. 960 factorial upon 40 factorial, 920 factorial. Similarly, this will become 920 factorial upon 40 factorial, and 920 minus 40 is what? 880 factorial. And so on. The last one will become 40 factorial upon 40 factorial times 0 factorial. Okay, N minus R is 0. 0 factorial is 1, right? So what will this become? This will get cancelled, this will get cancelled, this will get cancelled, and so on. So all the numerators will get cancelled, and in the denominator we will have, so in the numerator we will only be left with 1000 factorial. And in the denominator, in each of these factors, we will only have 140 factorial left. We will have 140 factorial left. How many times? So there are 25 relatives, so 25 times. So in the denominator, we will have 40 factorial to the power 25. Okay. So this is your number of ways to do this. This is slightly complicated problem. This might not be asked in GATE, but a simpler version of it might. Okay. So even if you don't understand it completely, it's okay. Okay, this is like involving everything. And also by seeing the next lecture, binomial multinomial theorem, this problem will become much more clearer. Okay, it will become easier. We have not seen this type of problem before, like in PNC. So yeah, but yeah, this problem was easier. Okay, this you might have got. Like here it was much more simpler. Here because there were no restrictions. How many gifts are going to which guy? Cool. Now let's see the next variation of the same problem. So now the next year, what happened? Your mother-in-law buys 1000 identical pens to give to the family. Okay, now we don't have 1000 different items. Now we have 1000 identical items. We have 1000 identical items to give to the family, and they are giving pen. So now you start to wonder what is going on. Okay, so how many ways now these 1000 identical pens were distributed to the 25 family members. Okay. Now, see, amazingly, this problem became combination of repetition. You have 1,000 identical pens. It doesn't matter. Okay, the items are not distinct; they are identical. So first pen is same as second pen, and so on. And you have 25 relatives to give it to. First relative, second relative, and 25th relative. Since the pens are identical, the relatives don't care which pen they are getting. They only care about the count, how many they are getting. Right? You have 25 relatives. So the first relative doesn't care which pen among those 1,000 pens he is getting, right? They only care how many pens they are getting. So the number of ways will be what? You can either give all the 1,000 pens to the first relative, or you can give like some weird combination, like you can give 40 to each one of them. That is also a possible option. Or you can give all 1,000 to like 17th relative and so on. So it is just like, let's say the first relative gets x1 pens, second relative gets x2, and so on. The 25th relative gets x25 pens, and you have to distribute total 1,000 pens. So how many solutions are there to this equation? Where x1, x2 up to x25 can be greater than equal to 0, right? Any number of pens can be going to any relative. So just the number of different solutions to this equation will be the number of ways in which you can distribute. So this will be equal to how? What? N plus r minus 1. So this is n, this is r. So n plus r minus 1, choose n minus 1. So basically you create 1024 boxes. Since you need 25 partitions, you will need 1024 boxes and you will create 24 partitions, 24 sticks. So you will have 25 partitions and you will be remaining with 1,000 boxes. We already saw this. Apply the formula, okay? So this is the number of ways in which you can distribute 1,000 identical pens to 25 different relatives. Cool. Now the last variation of this problem. Again, the next year your mother-in-law buys 1,000 identical pens and you have to distribute it to 25 relatives, you can assume. But now, in how many ways can I distribute 1,000 identical pens to 25 relatives such that each person gets 40 pens? Now it is given that you have to distribute exactly 40 pens to every relative. So it is like you had 1,000 pens and you have 25 relatives. See, the pens are identical, they look exactly same. You have to give 40 here, 40 here, 40 here, exactly 40 here. It doesn't matter which pen you are giving to which relative, they are identical. And they are saying you have to give 40 to each one of them. So you don't have any option, you just have to take 40 and give to R1, 40 and give it to R2, and 40 and give it to R25. You are left with no pens, right? So there is, since the pens are identical and the count is also given, then you don't have any option. Okay, this is the only way in which this problem can be solved. There is only one way in which this distribution can be done. There is only one way in which this distribution can be done, and this is the way. Give 40 pens to R1, 40 to R2, and so on, give 40 pens to R25. So this is the only distribution possible, so there is only one way to solve this problem. Since the pens were identical and the count was also given. In the previous problem, we actually counted in how many ways this bifurcation can be done. But here this bifurcation is also given. You have to do it 40 plus 40 plus 40 up to like 40 up to 25. So there is only one way in which you can solve this problem. Just distribute it. Okay. Cool. So these were a few problems on permutation and combinations, and basically like with repetition, without repetition, whatever we have seen. So in the next lecture, like we will like continue like the journey of counting. Hi everyone. So welcome to lecture number 8 of counting. So we are doing GATE Data Science and Artificial Intelligence complete course, and we are discussing counting. Right now we have seen factorial, the motivation behind factorial, permutations, which means arrangements, and then combination, which means selection, then combination with repetition and permutation with repetition, and we have solved a few problems on that. Now we are going to a new topic, which is called the binomial and the multinomial theorem. Okay. Firstly, these two are mathematical theorems, and they have their own motivation, and like they are like completely into maths. Okay, why are we discussing them in counting? We will see it. What do multinomial and binomial theorem have to do with counting? We will see that. Okay, so yeah, let's start. Firstly, like what is binomial theorem and why are we discussing it? So what is binomial? A polynomial with two unknowns. So basically, let's say x plus y to the power 2. This is a binomial. Okay, we have two variables and there is some power. Okay, we are raising it to some power. So we already know that what is x plus y whole square? It is x square plus 2xy plus y square. This is the binomial theorem for power 2. What is the binomial theorem for power 3? What is x plus y whole cube? So basically you are multiplying x plus y with x plus y, and basically you are expanding this bracket. So what are you essentially doing? So let's say there are three containers, right? There are three containers. All three of the containers have one x and one y, right? So in how many ways can you take x and y? That is what binomial theorem is. That is why we are discussing it in counting, right? You are seeing that mapping, right? You have three containers, all of them have x and y. In how many ways can you have three x's? So you will have one, so in this expansion you will have one term for x cube. So either you can take three x's, or you can take two x's and one y, or you can take one x and two y's, or you can take all three y's. So in this expansion you will have all these three terms. So in how many ways can I take three x's? So you take one x from here, one x from here, and basically x from all three of them. So there is only one way. Plus, so in how many ways can you take two x's and one y? You can take x from here, and y from here. Or you can take x from here, y from here, and x from here. Or you can take y from here, x from here, and x from here. So there are three ways in which you can take two x's and one y. So there will be 3x square y. When you expand it, you will get this only, right? Similarly, there are three ways in which you can take one x and two y's. Like similarly, you can take x, y, y, x, y, x. X, y, 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 x, y, and y, y, x. So there are three ways in which you can take two y's and one x. And there is only one way in which you can take all three y's. You just take y from everywhere. Okay. So when you expand it, you will get 8 different terms. One of which will be x cube, one of which will be y cube, 3 of which will be x square y, and 3 of which will be xy square. So this is what binomial theorem is for power 3. Right? And this is how we get it connected to counting. You consider n containers. In how many ways can I pick two x's and one y? Right? So this is what binomial theorem is. So the generic expression for binomial theorem, if you create it this way. So let's try to derive it on our own. Okay, I will try to derive a generic expression for x plus y to the power n. So this is binomial theorem for power n. Okay. So here what we will have? Here we are multiplying x plus y with x plus y, then again x plus y, and so on. Basically, we are multiplying x plus y bracket n times. 1, 2, up to n times. Right? So basically, when we multiply, what will we get? So if we take x from everything, x into x into x, we can get x to the power n. So we will get different terms. Okay? But you will see a pattern. You will see one term will be x to the power n. You will have few terms of type this, x to the power n minus 1 and y. You will have a few terms of this type, x to the power n minus 2, y square. Similarly, and you will have one term like y to the power n. Basically, you will have many such terms, but the sum of coefficients of x and y will always be n. Here you have n x's and 0 y's. You can write it like this also. N x's and 0 y's. Or you can have n minus 1 x's and 1 y. Basically, again the same thing. You have n containers. Right? You have n containers. All of them contain 1 x and 1 y. You can either take an x or a y from every one of them. So basically at the end you will have some number of x's, some number of y's, but the total number of x and y will be always n. So the sum of coefficient, the sum of the powers of x and y, sorry, not coefficients, sum of the power of x and y will always be n. Right? Now, what will be the coefficient? So in how many ways can I pick n x's? and 0 y's. So basically, from all the n containers, you are picking x only. There is only one way. There is only one way you can do this. In how many ways can I select n minus 1 x's and 1 y? So basically, what you are doing is, from n minus 1 containers, you are choosing x, and from only one container, you are choosing y. So basically, you choose that one container from which you are taking y. See, the simpler problem to think about it is, in how many ways can I choose one container? And from that one container, I will take y, and from all other containers, I will take x's. So there are nc1 ways. There are nc1 ways in which I can choose that container from which I am taking y. Similarly here, in how many ways can I have n minus 2 x's and 2 y's? This can be said as, in how many ways can I pick two containers and I will take y from them, and from the remaining n minus 2 I will take x. So basically there are nc2 ways in which you can choose those two containers from which you are taking y, and from the remaining containers you will pick an x. So this is the coefficient of x to the power n minus 2 and y to the power 2. Similarly, at the end, for y to the power n, you will have ncn, or 1 again. So this will be the expansion. So here n1 can also be written as nc0, because we are taking 0, because actually you are taking no containers with y. So you are taking 0 containers. You are taking 0 containers from which you will take y. So this is the expansion of x plus y to the power n. Right? So you can also like write a compact notation for it, but yeah, like this is the generic equation for x plus y to the power n. So like this is the compact notation. How do you write it? So x plus y to the power n will be summation from k equal to 0 to n choose k. So n choose k is the coefficient. So k, here k is equal to 0. K is the, let's say k is the number of y's. K is the number of y's that you are taking. So you are taking n minus k x's. So pick any k out of n boxes. From those you will take a y, and from remaining you will take an x. So the coefficient will become n choose k, and the product will become x to the power. So basically you are picking k y's and n minus k x's. Sum of the power will always be n, and the coefficient will be n choose k. So and the sum goes from k equal to 0 to n. So this is what this expression is, right? And similarly, the same way you can also choose x also, right? Why only choose y? You can choose x also. Let's say first I am choosing 0 x's and all y's. Then I am choosing 1x and 0 y, 1x and n minus 1 y, and at the end I will choose n x's and 0 y's. You can also choose x's instead of y's, and the coefficient will remain same. Out of n, choose 0 boxes from which you will take x, and from remaining you will choose y. So and you can also derive this formula from this formula. You can just write NCR as NCn minus r. So this coefficient will become NCn, and this coefficient will become NCn minus 1. And at the end, this coefficient will become NC0. Okay, you can do k selection equal to k rejection. So also this formula becomes this formula. So the power of x can be k and y can be n minus k. Here you are selecting y, here you are selecting x. Doesn't matter, right? So it is symmetric in some sense. So what happens? Let's say I calculate x plus y to the power 5. Here I will have 6 different terms. X to the power 5, x to the power 4y, x cube y square, x square y cube, x y to the power 4, and y to the power 5. I will have 6 different terms, and the coefficient of x to the power 5 will be what? Since we are choosing 0 y's, so this coefficient will be 5c0. This coefficient will be 5c1, because I have to choose one y. This coefficient will be 5c2. This coefficient will be 5c3. And this coefficient will be 5c4. And this coefficient will be 5c5. Right? If you just write the values also, 5c0 is 1. So this will become x to the power 5. 5c1 is 5. So it will become 5x to the power 4y. 5c2 is what? 5 into 4 upon 2, which is 10. So 10 x cube y square Again 5c3 is equal to 5c2, so it will become 10 x square y cube. This is symmetric. 5c4 is 5, 5x y to the power 4, and this is 1. So the coefficient of x to the power 5 will be equal to coefficient of y to the power 5. The coefficient of x to the power 4 y will be equal to the coefficient of x y to the power 4. So basically the coefficient of x to the power n minus k y to the power k, the coefficient of this will be equal to the coefficient of x to the power k and y to the power n minus k. Right? Either you can select k y's or k x's, it doesn't matter. And both these coefficients will be nck. Right? So that's how you can do it. And there is an interesting observation. So if you see, I will come to the sum. Like there is an interesting observation. So this, if you just put all these coefficients in a fashion, actually you can create a beautiful triangle. So what is x plus y to the power 1? It is just x plus y, right? So here you are having just one coefficient. So what is x plus y whole square? It is x square plus 2xy plus y square. What is x plus y whole cube? It is x cube plus 3x square y plus 3xy square plus y cube. Similarly, what is x plus y to the power 4? It is x to the power 4 plus 4xy cube plus 6x square y square plus 4x to the power 3y plus y to the power 4. So if you see, we are actually creating a beautiful triangle here. And how is it created? If you just write the coefficients this way, 1 for x plus y, actually 1. For x plus y, the coefficients are 1. For x plus y whole square, the coefficients are 1, 2, 1. For x plus y whole cube, so this is binomial theorem for power 1, this is binomial theorem for power 2, binomial theorem for power 3 will be what? The coefficients are 1, 3, 3 and 1. For x plus y to the power 4, the binomial coefficients will be 1, 4, 6, 4 and 1. There is a symmetry, right? For 5, the coefficients are 1, 5, 10, 10, 5, 1 and so on. This is called the Pascal's triangle. And you can have x plus y to the power 0 as well. X plus y to the power 0 is just 1. Right? This is called the Pascal's triangle. Here, if you observe a fact, every term is the sum of these two terms. So here this term is sum of these two terms. This 10 is the sum of 4 and 6, or you can do 6 and 4, right? 4 and 6. This 10 is sum of 6 and 4. This theorem also we have seen. This we have seen in combination as recurrence, right? We saw that n choose r is n minus 1 choose r minus 1 plus n minus 1 choose r. Right? This theorem we have seen in combinations as recurrence. So this is what? This is 5c2. 5c2 will be 4c1 plus 4c2. This is 4c1, this is 4c2. Right? So if you see this triangle carefully, this will be 4c0, 4c1, 4c2, 4c3, 4c4. This will be 5c0, 5c1, 5c2, 5c3, 5c4, 5c5. So 5c2 will be 4c1 plus 4c2. Combination as recurrence. Yeah, so like you can just add the above two terms and you'll get the below term. So this is math, like if you are writing a computer program, that's how you generate the Pascal's triangle. Just sum the above two numbers. You'll get the number below. So like everything is connected, right? Like whatever we have seen so far. So everything is connected. Like this theorem is being applicable here, and this is a beautiful triangle called Pascal's triangle. And another property of Pascal's triangle is it is symmetric. Like this we already saw, right? This is symmetric along the horizontal line. It is symmetric because n choose r will be equal to n choose n minus r. That is also one thing. And the next interesting property is what is the sum of all binomial coefficients. So for n equal to 0, the sum is 1. For n equal to 1, the sum is 2. For n equal to 2, the sum is 2 plus 1 plus 1, which is 4. For n equal to 2, the sum is 1 plus 3 plus 3 plus 1. The sum becomes 8. For n equal to 4, the sum is 1 plus 4 plus 6 plus 4 plus 1, which is 16. 32. You see a pattern here? For n equal to n, the sum of all binomial coefficients is always 2 to the power n. For n equal to 0, it is 1. For n equal to 1, it is 2. 4, 8, 16, 32. So for any n, the sum of all binomial coefficients is always 2 to the power n. And we can actually have that interpretation here. How? Why is it always 2 to the power n? So let's see that. Okay. So this is what x plus y to the power n was. N choose 0, x to the power n. N choose 1, n choose 1, x to the power n minus 1 y. N choose 2, x to the power n minus 2 y square. N choose n, x to the power n, x to the power 0, y to the power n. This is binomial theorem. What is the sum of coefficient? Sum of coefficient is n choose 0 plus n choose 1 plus n choose 2 up to n choose n. How do you calculate it? Just put x and y as 1 here. Just put x and y equal to 1 here. If you put x equal to y equal to 1 here, you will get what? This will become 2 to the power n. This will become 2 to the power n, and this will become nc0. These terms will all become 1 to the power 1, 1 to the power n minus 1 into 1. So these will all become 1. So this will become 2 to the power n equal to n choose 0, n choose 1, n choose 2. So the sum of the coefficient you can calculate by putting x and y both as 1, and it will be equal to 2 to the power n. And you can also see it using the motivation that we saw in the last lecture. So in the last lecture we saw, in this lecture only, previously we saw that how is the binomial theorem actually even calculated? How are we actually representing the binomial theorem? So we say that x plus y to the power n is what? You are just multiplying x plus y n times. So you have n brackets, you have n containers. You can take an x or a y from each one of them. You can take an x or a y from each one of them. And what is the sum of all coefficients? See, I told you the coefficient of any term. The coefficient of any term is what? The coefficient of any term is what? Let's say x to the power k, y to the power n minus k. You are picking k x's and n minus k y's. You are actually picking k x's and n minus k y's. So basically, if you want to sum all the coefficients, the coefficient of this term is the number of ways in which I can pick k x's and n minus k y's. So what will be sum of all the coefficients? It is like the number of all possible ways, right? Either you are taking n x's and 0 y's. So you are taking 0 y's or 1 y or 2 y or 3 y. Basically, you are taking, like, the sum of coefficients will be all possible ways in which you can multiply this equation. Or basically you can take an x or y from each of the containers. So what is the number of all possible ways? You have two options for every container. You can take an x or y from here. You can take an x or y from the second container. And similarly, you can take either an x or a y from this container. You have two options for every container. So the total number of possible ways in which we can do this thing will become 2 to the power n. So combinatorically speaking, also, like container value ways, we are getting like the total number of ways will be 2 to the power n. Also from the formula of binomial theorem, we are getting the sum of coefficients as 2 to the power n. So this is the mapping. Like that's why we are discussing it here. This is the mapping of counting with the binomial theorem. Okay. So this was about binomial theorem. A more complicated version of binomial theorem is the multinomial theorem. But I should say that binomial theorem is actually a subset of the multinomial theorem. So we will discuss the multinomial theorem now. So in binomial theorem, there were two unknowns, x and y, x plus y to the power n. Or basically in every container, there were only two objects, x or y. You can pick an x or a y. In multinomial theorem, you have multiple number of objects in every container, that's it. So basically here also you have n containers. Previously in every container, you just had an x or y. But here, you will have m different options in every container. So previously you only had x and y. Let's say now you have x1, you can have x1, x2 up to xm. You have m different options in first container. Similarly, you have m different options in second container. x1, x2 up to xm. Similarly, you have m different options in nth container. That's what multinomial is, right? Like you don't have two options, you actually have m options in every container. So what you're trying to do is you're trying to expand x1 plus x2 plus xm to the power n. In binomial theorem, we had x plus y to the power n, only two like variables. Right here we have m variables. So x1 plus x2 plus x3 up to xm to the power n. So this is like multiplying x1 plus x2 plus xm. This is first bracket. This is second bracket. And this way we are multiplying them n times. So we have n containers, we are multiplying this bracket n times. So here how the coefficients will look like, you can either take an x1 from all the containers. So you will have a term like x1 to the power n. Or you can take, let's say, n minus 1 x1s and 1 x2. Or you can have n minus 1 x1s and 1 x3. There are many such terms. And like one of the terms will be, last term will be xm to the power n. Right? But again, see, how will one term look like? Any one of these terms will look like this. It will be x1 to the power, it will be x1 to the some power, let's say k1. Then x2 to the some power, let's say k2. And multiplied like this, xm to the power km. Every such term will look like this. And the sum of all these powers will be what? N. Sum of all these powers will always be n, because you are picking some object from every container. The total number of containers is n. So the total number of objects you will get will always be n. You will have some number of x1s, you will have some number of x2s, some number of xm's. So the sum of all these powers, k1 plus k2 up to km will always be n. Okay, so every such term will look like this. Every term will look like this. Now, only thing we need to do is find the coefficient of this term. Any generic term in multinomial theorem looks like this. You just have to find the coefficient of this term. And if you have seen my last video, we have already solved some like one such problem. So what do we want here? We just want to find the coefficient. Of. So we want to expand this and we want to find the coefficient of one generic term, any generic term. So let's say that term is x1 to the power k1, x2 to the power k2, xm, xm to the power km. We have to find the coefficient of this term. Will be what? Okay. So it is like the number of ways in which we are taking one object from first bucket, one object from second bucket, one object from nth bucket, and all the buckets have m items, right? x1, x2 up to xm, same items. So in such a way that we are taking k1 x1 items, k2 x2 items, k3 x3 and so on, km xm items. The sum of k1 k2 up to km will always be n. The sum of k1 k2 will always be n. So in how many ways can I do that? So basically like just do it like binomial theorem only, okay? So out of the n containers, pick any k1 containers. Out of the n containers, pick any k1 containers and pick an x1 out of them. So this will be much easier if I take an example. Okay, then I will do a generic version. So let me take an example. Let's say we want x1 plus x2 plus x3 to the power 7. And here I want to find, let's say I want to find the coefficient of x1 to the power 3, x2 to the power 2, x3 to the power 2. This is one such valid term in the expansion of this, right? The sum of the power will always be 7. 3 plus 2 plus 2, 7. This is one such term. And let's say in the expansion of this, I want to find the coefficient of this term. So how will I do that? Basically, I have 7 containers. Each one of them have one x1, x2 and x3. In how many ways can I pick 3 x1s, 2 x2s and 2 x3s? How will I do that? Out of the 7 containers, take any 3. I am using the rule of product. This is my first task. Pick 3 x1s. This is my first task. First task, pick any 3 x1s. So out of these 7 containers, pick any 3 containers. I will take x1 from them. Now from the remaining 4 containers, pick any 2 containers and take 2 x2s from those. And now from the remaining 2 containers, take both the containers and pick 2 x3s from there. So this is by rule of product. This is my answer. And the order doesn't matter. You can take first x1, then x2, then x3, or let's take x3. So for x3, let's say from the 7 containers, I am taking any 2 containers. From the 7 containers, I am taking any 2 containers, and I am taking the 2 x3s from here. The order doesn't matter, right? And then my second task is, let's say I first pick x3, then I pick 1 and then 2. So now from the remaining 5 containers, pick any 3 and take 3 x1s from there. Then from the remaining 2 containers, take both the containers and take the 2 x2s from there. These 2 products are same. It doesn't matter. How? If you expand it, it will come out to be 7 factorial upon 3 factorial, 4 factorial. The first term. The second term will be 4 factorial upon 2 factorial, 2 factorial. And the third term will be 2 factorial upon 2 factorial, 0 factorial. Right? So these will cancel. And you will have 7 factorial upon 3 factorial, 2 factorial, 2 factorial. It is just like 7 factorial upon 3 factorial, 2 factorial, 2 factorial. If you expand this also, you will get the same thing. The first term is what? 7 factorial upon 5 factorial, 2 factorial. The second term is what? 5 factorial upon 2 factorial, 3 factorial. Yep. And the third term will be what? 2 factorial upon 2 factorial, 0 factorial. You can cancel this and this, this and this. Here also you'll get 7 factorial upon 2 factorial, 3 factorial, 2 factorial. This and this are same. Actually, this is defined to be 7 choose 3 comma 2 comma 2. And this is also defined to be 7 choose 2 comma 3 comma 2. So the order doesn't matter. Okay, basically what you are doing, from 7 objects you are picking 3 objects, and then from the remaining objects you are picking 2 objects, and then from the remaining objects you are picking 2 objects. Here also you are doing from 7 you are picking 2, then 3, then 2. So the order doesn't matter, just the total number of objects you are picking is 7, and you are picking 3 and 2 and 2. Right, 3 x1s, 2 x2s and 2 x3s. So in which order you are picking, it doesn't matter. So firstly you pick 3, then 2 and then 2. So this is what 7 choose 3 comma 2 comma 2 is like. Okay, so this coefficient will be equal to 7 choose 3 comma 2 comma 2, which is 7 factorial upon 3 factorial, 2 factorial, 2 factorial. Similarly here, this coefficient of x1 to the power k1 will be what? Since the sum is n, it will be n choose from the n containers. Pick any k1 containers and choose x1 from them. Then from the remaining n minus k1 containers, choose any k2 and pick an x2 from them. Then from the remaining n minus k1 minus k2, choose any k3 containers and so on. This product, if you calculate it, it will always come out to be n factorial upon k1 factorial, k2 factorial, k3 factorial and so on up to km factorial. And this is called n choose k1, k2, km. Okay, this is the multinomial coefficient of x1 to the power k1, x2 to the power k2, xm to the power km in the expansion of x1 plus x2 up to xm to the power n. It is the number of ways of choosing k1 x1s, k2 x2, km xms in n containers, where every container contains one x1, x2 and xm. Okay, so this expansion you can do like this. Okay, things will cancel out and it will automatically come out to be this always. I can do it for you very simply, like very easily. So let's say like the coefficient was what? N choose k1 times n from the remaining n minus k1 you choose k2. Then from the remaining n minus k1 minus k2 which is k3 and so on. The last term will be n minus k1 minus k2 up to km minus 1. Okay, so this term let me finish it. So this choose km from the remaining terms you choose km. This is the last term. We know that the sum of k1, k2, km minus 1, km will always be equal to n. So this term will automatically become km at the end. This entire term. At the end you will only be remaining with km items only. From km you will choose km. So what will this product be? N factorial upon k1 factorial, n minus k1 factorial. This term will be what? N minus k1 factorial upon n minus k1 minus k2 factorial, k2 factorial and so on. At the end you will have km factorial upon km factorial, 0 factorial. Always these terms will cancel. So you will have n factorial upon k1 factorial, k2 factorial up to km factorial. Okay, so this is the coefficient and this is how it is defined. So this is how in compact notation we will write the multinomial theorem. x1, x2 plus xm to the power n is what? Summation of all such terms. Summation of all such terms in which k1 plus k2 plus km should be n. There are many such ways in which we can do this. Summation of all such terms in which k1, k2 up to km is equal to n and all these k's are greater than or equal to 0. This is my term. This is how my term looks like. x1 to the power k1 times x2 to the power k2, x2 to the power k3 multiplication. This is product. So this is my term. This expansion is what? x1 to the power k1 times x2 to the power k2 and so on, xm to the power km. This is my one such term. Okay, so for all such terms the coefficient is n choose k1 k2 up to km, where n choose k1 k2 up to km is this, n factorial upon k1 factorial, k2 factorial, km factorial. Okay, I hope you got it. So there are a couple of problems on multinomial theorem. So like one is, what is the sum of all multinomial coefficients? Very easily, like polynomial. How will you do it? Just write x1, x2, xm all 1. You will find the sum of coefficients. So you get 1 plus 1 plus 1 to the power n is equal to. So this term will become 1. If you put all x is equal to 1, this term will become 1, right? So you will get the sum of all possible coefficients. Just like binomial. So sum of all possible coefficients is what? This thing. So it is just 1 plus 1 plus 1 m times. So it is m to the power n. So in binomial theorem it was 2 to the power n. In multinomial theorem it is m to the power n. And what is the number of multinomial terms? What is the number of multinomial terms? So in how many ways? So see, right? How many such terms exist? That is the question. So in the expansion of, let's say, x1 plus x2 plus x3 to the power 7. I told you there will be many terms. x1 to the power 7, x1 to the power 6, x2. x1 to the power 6, x3, x1 to the power 3, x2 to the power 2, x3 to the power 2. There is one term. So how many such terms are there? So it is exactly like C. So the power of x1 is k1, so the power of x2 is k2, and the power of x3 is k3. And all the sum of all the powers have to be 7. So the number of solutions to this equation, where k1, k2, k3 has to be greater than or equal to 0, is the number of terms you will get. It is always equal to the number of terms that you will get. You already know how many solutions are there to this equation. This is 7 plus 2, 9c2. Right? So similarly, in a generic expression, what will happen? We have k1 plus k2 plus km is equal to n. How many solutions are there to this equation? It is n plus m minus 1. Choose m minus 1 or m plus n minus 1, choose n. You can write anyway, okay? Just the formula that we saw before. So this is the number of terms that we will have. So the sum of multiple coefficients is m choose n, m to the power n, and the number of terms is n plus m minus 1, choose n. Okay, see carefully, okay, don't get confused. It's not here r is n, right? So that's why, like, always convert it to an equation. Generally we have r here. So don't get confused. Convert it into equation and just apply the logic. Like, you want to make m partitions, so you will insert m minus 1 sticks. So that's the formula, okay? Cool. So this problem we already saw in the last lecture. Your mother-in-law has 1,000 small gifts to give to relatives, 1,000 different gifts, and there are 25 relatives in which to which you have to distribute these gifts to. In how many ways can these gifts be distributed so that each person gets 40 items? So again, we have 1,000 gifts, and now it will be more clear to you how to solve the problem. And you have 25 relatives. Each person should get 40 gifts. So it's like you choose any 40 gifts for R1. So it's like from the 1,000 gifts, you choose any 40 gifts and give to R1. Every person should get 40 items exactly. And the items are different. So you choose any 40 items, give it to R1. Then from the remaining 960 items, you choose 40 items, give it to R2, and so on. From the remaining 40 items, you choose 40 items and give it to this relative. And this is nothing but from the 1,000 items, we are choosing 40 items, then 40 items, then 40 items, up to like 25 times. This is also the multinomial coefficient of x1 to the power 40, x2 to the power 40, up to x25 to the power 40 in the expansion of x1 plus x2 plus x25 to the power 1,000. Right? So, like, if you want to see the combinatorial interpretation, think it like that. You have 1,000 items, right? For the first item, you can give it to any of the 25 relatives, x1, x2, or x25. The second item you can give to any of the relatives, the 25 relatives. The 1,000th item you can give to any of the 25 relatives. But now we want to find the coefficient of this only. Why? Because x1 should get 40 items, x2 should get 40 items, and the 25th relative should also get 40 items. Okay. So this is how we can do it. So if you want to see the final combinatorial interpretation, this is how you say it. This is like the multinomial theorem is nothing but the ways in which we put objects into bins. So the multinomial coefficient have a direct combinatorial interpretation as the number of ways of depositing n distinct objects into m distinct bins with k1 objects in the first bin, then k2 objects in the second bin, and so on. Okay. So we will see more problems on binomial and multinomial theorem. This was the theory part. This might be a little tricky, so just watch the video again. If you have any doubts, write in the comment section. I will answer them. And also, when we solve more practice problems, these theorems will become more clear. Okay. But yeah, like seeing the combinatorial interpretation of every theorem and then like writing the equation and solving it will help you. Don't jump directly to formulas. Try to see the mathematical way. Why is this problem being solved that way? Okay. Hi everyone. So welcome to lecture number 9 of counting course. We are doing as a part of GATE Data Sciences and Artificial Intelligence complete course. So in this lecture we will see the principle of inclusion and exclusion. It is very core and fundamental to like counting in general. So let's see this principle. Firstly, talking about the motivation. So the motivation of inclusion and exclusion comes from set theory. So let's say this is our universe, and I will use a few terms from set theory right now. Okay. So if you don't know set theory, it's okay. Like, but still you will understand the concept which I'm trying to say. Okay. So this is our universe. Let's say this is my set A and this is my set B. And set A contains n elements and set B contains m elements. Okay. Then the union of these two sets. Okay, the union of these two sets is called like how many elements are there in A or B. That is what union is. Like they can be in A or B. Okay, anyone. So the cardinality of A union B here is n plus m because A and B are disjoint. So A and B, since don't have any elements in common, the cardinality or the number of elements in A union B will become n plus m. Right? All the number of elements in A and m in B. But sometimes there might be a few elements common in A and B. So let's say this is my set A, this is my set B. And let's say there are a few elements, let's say that there are n elements in A, m elements in B, and there are k elements which are common in both A and B. The common part is called A intersection B. Okay, the common part is called A intersection B. So the cardinality of A intersection B right now, let's say, is k. Okay, there are k elements which are both in A and B. There are overall n elements in A and there are overall m elements in B. Okay, so in this case, the cardinality of A union B will be what? So it will be n plus m. N plus m is okay. Okay, n plus m is what? Counting all the elements in A and counting all the elements in B. But here, few elements we are overcounting. These k elements, if you see, these k elements, we are counting in both A and B both, right? So we are counting them twice. So since we are overcounting, we will subtract these k elements once. Since we counted these k elements two times, both in A and B, we have to subtract them once because like that's what we want. So for example, let's say in the same example, let's say A has here 1, 2, 3, 4, 5 elements and B has 3 elements, 1, 2, 3, 4, 5, and this is A, this is B. So here A has 5 elements, the dots, and here B has 3 elements. But there are 2 elements which are common in both A and B. So the total number of elements in A union B is what? We can count them. Like here there are 1, 2, 3, 4, 5, 6 elements. But from the formula we will have cardinality of A plus cardinality of B minus cardinality of A intersection B, which is 6. Okay. Since we were counting these 2 elements 2 times, both in A and B, we have to subtract it once. This is what the principle of inclusion exclusion is. Since we overcounted, we are excluding them. But so like if you are only excluding, why are we calling it inclusion exclusion? So that thing will become clear when we see like more sets. Let's say let us take 3 sets now. Okay. So if I take 3 sets, this is my set A. Okay. So here the cardinality of A union B union C will be what? Let's try to find out. It will be the cardinality of A, the number of elements in A, plus number of elements in B, plus number of elements in C. This is okay. But right now we are overcounting. So what we are doing essentially, so when we are adding all the elements in A, B and C, this particular area, which is in both A and B, this particular area which is in both A and B is counted in both A and B. So it is counted two times. So we have to subtract it once. So we will subtract it once. The area which is in both A and B. Since we counted it 2 times. Similarly, this particular area which is in both A and C. This is also counted 2 times. Right? So we have to subtract that as well. That is also counted 2 times. And also the area which is in both B and C. The area which is in both B and C, that is also counted 2 times in B and C both. So we have to subtract that also once. Okay. But now one thing happened. So what happened is, this particular small area, which is in all 3, this particular area is like present in all the 3 sets, A, B and C. So what happened to this area? Think about it. This was counted once in A, it was in A, it was in B also, it was in C also, right? So it was counted 3 times. In these 3, it was counted 3 times, this particular area, because it is present everywhere in A, B and C. It is also present in A intersection B. Here also in A intersection B also it is present. In A intersection C also it is present, and in B intersection C also it is present. So this area is added 3 times and subtracted 3 times. Right? So basically right now if the formula had been just this particular area is not present at all. It was added 3 times and subtracted 3 times. So we have to add it once. So this is what inclusion exclusion is. We include, we exclude, then we again include, and so on. If we have 4 sets, we will include, exclude, and so on. That's why inclusion exclusion. Right? So basically what we are doing, keep all the elements which take 1 at a time. Then we subtract the sets with 2 at a time. Then we add 3 at a time. Then we subtract 4 at a time, and so on. This is what inclusion exclusion is. Okay. So if you take an example like how many natural numbers less than 100 are non-multiples of 2 or 3. So let's say less than or equal to, okay, or we can do less than also, but like yeah, then 99 will be a bad number. Let's make it 101. Okay, how many natural numbers less than 101? So basically I want to include 100 so that the math will be simpler. Okay, so how many natural numbers between 1 and 100 are there which are non-multiples of 2 or 3? What do I mean by non-multiples? They should not be divisible by 2 and they should not be divisible by 3, both. So now very simple, okay? Use inclusion exclusion. So what do we want? So we want all the numbers which are not divisible by 2 and they should not be divisible by 3. So firstly, how many numbers do I have between 1 and 100? I have 100 numbers. These are all natural numbers. Okay. So I will subtract all the numbers which are divisible by 3, divisible by 2. Let's subtract all the numbers which are divisible by 2. So how many numbers will be divisible by 2? Floor of 100 by 2. So always when you have, like if you want to find how many natural numbers less than n are divisible by k, it will be floor of n by k. Why? See, the first number which will be divisible by k will be k itself, then 2k, then 3k. These are all divisible by k, right? And we have to reach n somewhere, right? So this will be divisible by k, this will be divisible by k, this will be divisible by k. So what will be the last number that will be divisible by k? So it will be somewhat, it might, if n is exactly divisible by k, it will become exactly n by k, right? If n is exactly divisible by k, this will n exactly will be my last number, and total number of numbers will be 1, 2, 3 and n by k, right? But it might be possible that n is exactly not divisible by k and a slightly smaller number somewhere here is divisible by k, and we have to stop there. So that particular number will be floor of n by k into k, always. So for example, like up to, let's say if I have numbers up to 10 and I want to find out what are the numbers which are less than 10 and are divisible by 3. So 3 will be divisible by 3, 6 will be divisible by 3, and 9 will be divisible by 2. And 10 will be here. Only these 3 are divisible by 3. So what is 9 actually? 9 is actually floor of 10 by 3 into 3. Because floor of 10 by 3 is the just less than number, like just less than 10, which will divide 3. Okay, so if I multiply it by 3, I'll get 9, which is the last number which is less than 10 and is divisible by 3. So if you want to find the number of natural numbers less than n and are divisible by k, it will be floor of n by k. So I subtracted all the numbers which are divisible by 2. There are 50 numbers which are divisible by 2. Now similarly, I will subtract all the numbers which are divisible by 3. So it will be 100 by 3 floor. Okay. Now again inclusion exclusion. I subtracted all the numbers divisible by 2 and I subtracted all the numbers divisible by 3. But actually I subtracted the numbers divisible by both 2 and 3 2 times. There will be few numbers which are divisible by both 2 and 3. For example, 6. So 6 is a number which is divisible by both 2 and 3. It is subtracted here also and here also. So I don't have to subtract them twice. So I will add them once. Include, exclude, again include. So I will include them. So I will include all the numbers which are divisible by both 2 and 3. So, okay. If you have to find out all the numbers which are divisible by, let's say, 10 and 12. I'm just giving you a different problem. Any number which will be divisible by both 10 and 12. Now I don't want to check two numbers, I want to get to one number. So, like I cannot say that all numbers which are divisible by 10 will always be divisible by 12 also, right? That is not right. And the general mistake which people do while solving this problem is they multiply both these numbers. So they say that all the numbers which are divisible by 120 will be divisible by both 10 and 12. It is correct, but it is not exactly correct. See, there is a one more number. Actually, 60 is also divisible by both 10 and 20. 10 and 12, right? 60 is also divisible by both 10 and 12. So if you have to find all the numbers which are divisible by both A and B, you should find out all the numbers which are divisible by LCM of A and B. Just find out the LCM of 10 and 12. The lowest common multiple of 10 and 12. So the lowest common multiple, like you just do the prime factorization 2 into 5, and here it is 2 into 3. So you just take the common elements out and it will become 2 into 5 into 2 into 3. So it is 60. So the LCM of 10 and 12 is 60. So if you have to find all the numbers which are divisible by both 10 and 12, then you just have to find out all the numbers which are divisible by 60. Okay? All such numbers 60, 120, 180 and so on will be divisible by both 10 and 12. So you just find out the LCM. So here also, if you have to find out all the numbers which are divisible by both 2 and 3, just take their LCM, it is 6. So all the numbers divisible by 6 will be divisible by both 2 and 3. So you just have to add them. So 100 by 6. So this will be your answer. So this is 100 minus 50 minus 33 plus 60. Okay. So you can just calculate it, it will come out to be 33. Cool. So there are 33 natural numbers which are non-multiples of 2 and 3. So similarly, we can solve one more problem using 3 sets, 2, 6 and 12. So now the number should not be divisible by 2 or 6 or 12. So again, we have 100 numbers minus those who are divisible by 2 minus those who are divisible by 6 minus those who are divisible by 12. So this is include, exclude. So this is divisible by 2, this is divisible by 6, this is divisible by 12. Now we have to add two at a time. Subtract one at a time, add two at a time. So you have to add all the elements which are divisible by both 2 and 6. So how many numbers which are divisible by both 2 and 6? The common mistake is you will divide by 12. It should not be 12. The LCM of 2 and 6. The number which are divisible by both 2 and 6 will be divisible by 6 only. Because LCM is 6. So it should be 100 by 6. Then you will add all the numbers which are divisible by both 2 and 12. So the LCM of 2 and 12 is again 12. So it should be 100 by 12. Then we will again add all the numbers which are divisible by both 6 and 12. Their LCM is also 12. So it should be 100 by 12. And now we will subtract. So minus 1 at a time, plus 2 at a time, minus all 3 at a time. So we'll subtract all the numbers which are divisible by all 3 of them, which means 2, 6 and 12. So their LCM is also 12 only, right? So we'll subtract 100 by 12. Okay. So if we do this, this will get cancelled, this will get cancelled, this will get cancelled, and we will just get 50. 100 minus 50 is 50. So it is intuitive also. It is intuitive also. See, all the numbers less than 100 which are not divisible by 2, 6 or 12. So basically all the odd numbers are not divisible by 2, 6 or 12, right? 1, 3, 5, 7. Since they are not divisible by 2, they will not be divisible by 6 or 12 also. So all the odd numbers are actually the answers. So like you can solve it that way or using inclusion exclusion. So there are 50 numbers. Cool. So in general form, the principle of inclusion exclusion states that for finite set A1, A2 up to AN, one has the identity. So this is like the general form. I will write it in a smaller way for you first, then we will see this formula. So basically, the cardinality of A1 union A2. Let's say we have n sets. So the cardinality of A1, A2 up to AN will be what? The cardinality of A1 plus cardinality of A2. So when we are doing this, we are overcounting 2 at a time. So we are overcounting A1 union A2, A1 intersection A2 2 times. In A1 and A2 both. So you have to subtract them. So subtract all pair wise. A1 intersection A2, A1 intersection A3, and so on. Subtract all the pair wise 2 at a time. So this is 1 at a time. These are sets taken 1 at a time, and then subtract 2 at a time. And then, so what happens? So consider the set A1 intersection A2 intersection A3. A1, A2, A3 all. So it is counted 3 times here and subtracted 3 times here. A1, A2, A1, A3 and A2, A3. So we have to add it once. So we'll add 3 at a time. We add all the sets taken 3 at a time. Okay, and we keep doing it that way, minus 4 at a time, plus 5 at a time, and so on. And at the end, we will have minus or plus, anything might be there. Then we will have all the elements at once, n at a time. See, when we had 1 at a time, we have a plus sign. When we have 2 at a time, we have a minus sign. When we have 3 at a time, we have plus sign again. So when we have n at a time, this is n at a time. What will be the sign plus or minus? So how to write it? Always write the sign in this form, minus 1 to the power something. So if I write minus 1 to the power n, what will happen? Minus 1 to the power n is not correct. Because for n equal to 1, it is plus. For n equal to 1, it is plus. For n equal to 2, it is minus. So it should be minus 1 to the power n minus 1. So this is like the multiplication factor right here. So the last term will be plus minus 1 to the power n minus 1. So this will like automatically adjust. Like if n is even, this will become a negative sign. If n is odd, it will become a positive sign. Okay, minus plus minus plus. So this is our last term. So this is the inclusion exclusion principle, and it is written beautifully here. So the cardinality of union of n sets A1 union A2 A union A3 is equal to sum of cardinalities of taken 1 at a time minus sum taken 2 at a time A intersection AJ for all IJ plus taken 3 at a time minus plus minus and so on and the last term is minus 1 to the power n minus 1, taken all at a time. Okay, we just saw it. So now let's solve a few problems. So how many integral solutions does the following system of equations have? So this is the system of equation which is given: x1 plus x2 plus x3 is equal to 10, and all the xi, so x1, x2, x3, all three of them are between 1 and 4. 0 and 4. See, if this condition was not there, less than equal to 4 value, if this condition had not been there, the problem would be much simpler. We already know how many solutions are there for x1 plus x2 plus x3 is equal to 10, where x1, x2, x3 are all greater than equal to 0. It is 12C2, right? Combination of repetition. So we just take 12 boxes, inside 2 sticks, 12 C2 solutions are there. Where there is no condition on x1, x2, x3, like this right hand side condition, only this condition is there. So, okay. But now we have a condition. So what is the condition? x1 should be between 0 and 4. x2 should be between 0 and 4. And x3 should be between 0 and 4. Okay. So let's forget this side of the condition. It doesn't matter, right? Let's say we already know the solution, right? x1, x2, x3 have to be greater than or equal to 0. That's the formula we already know. So I'm forgetting about this side of the condition for now. This is the condition that we are worried about. This is the condition that we are. Okay. Okay. Yeah. These are the conditions that I am worried about. x1, x2, x3 should not cross the value 4. See, I already told you there had been no condition. There are 12 C2 like possible ways in which you can do this. One such way is 10, 0, 0. Right? And this is not allowed because none of x1, x2, x3 can cross 4. So we are overcounting. So how will we deal with this with such a situation? So see, what is the counterpart of this? If I want to exploit this condition, if I don't want to care about this condition, then x1 has to be greater than 4. Then x1 has to be greater than 4. Or basically x1 has to be greater than or equal to 5. If x1 is greater than or equal to 5, then this condition is not taken care of. You agree? Similarly, if x2 is greater than or equal to 5, then this condition is not taken care of. Similarly, if x3 is greater than or equal to 5, this condition is not getting taken care of. So how do I do that? How do I solve this problem? So I know that the total number of solutions to this problem is 12C2. Right? Now I subtract all the possible combinations in which x1 is not in bounds. I subtract all the ways in which x1 is greater than or equal to 5. I will subtract all the ways in which x1 is greater than or equal to 5. It means that x1 is not following its bounds. Right? If x1 is greater than or equal to 5, we don't want such solutions. And this problem is easier to solve. So x2 and I don't care about x2, x3 right now. x2, x3 can be anything. Only x1 is not following their bounds. I only care about x1. So how many such values are there? Write x1 as 5 plus a. Write x1 as 5 plus a. So the equation will become x1 plus x2 plus x3 is equal to. So instead of x1, I am writing a. So a plus x1 plus x2 plus x3 plus 5 is equal to 10. So 5 will go there and become 5. So the equation becomes a plus x2 plus x3 is equal to 5. And now a x2, x3 can be anything. I am just solving for this. x1 has to be greater than or equal to 5. So I am writing x1 as 5 plus a. If you are not understanding this, watch my last video, combination repetition examples. I have solved this there, okay? So how many solutions are there to this equation? 7C2. So there are 7C2 ways in which x1 is greater than or equal to 5. Similarly, there will be 7C2 ways in which x2 is greater than or equal to 5. Right? Same way, like it's symmetry. Similarly, there will be 7C2 ways in which just x3 will be greater than or equal to 5. Right? Now, in how many ways? Now I will add. I will add all such cases in which both x1 and x2 are greater than or equal to 5. We have to add all such cases in which both x1 and x2 are greater than or equal to 5. So basically x1 also has to be greater than or equal to 5, x2 also has to be greater than or equal to 5. There is only one such way, right? 5, 5, 0. See, anyways, like if both of them have to be greater than or equal to 5, both of them have to be 5. Otherwise, it is not possible. The sum has to be 10. So there is only one such way in which both of them are greater than or equal to 5. Similarly, I will add that value in which both x1 and x3 are greater than or equal to 5. And similarly, I will add all the cases in which both x2 and x3 are greater than or equal to 5. Right? Standard inclusion exclusion. 0 at a time, 1 at a time, 2 at a time. And then I will subtract all the ways in which all three of them are greater than or equal to 5. Like see, all three of them cannot be greater than or equal to 5, right? x1, x2, x3 cannot all be greater than or equal to 5. Then the sum will not be 10. Because at least the sum will be 15, 5 plus 7 is 5. So this is not possible. So there are only 0 ways in which all x1, x2, x3 are greater than or equal to 5. Okay, so this is your answer. You can calculate it. So 12C2 is what? 12 into 11 by 2. It is 66. Minus 3 times 7C2. 7C2 is 7 into 6 upon 5. 7 into 6 upon 2. So 7 into 3 basically. And plus 1 plus 1 plus 1, 3. So this is 66 minus. Okay. 63 plus 3. So it is 3 plus 3, 6. So there are 6 solutions to this equation. There are 6 solutions to this system of equations. You can calculate it. And since there are only 6 solutions, we can also like write them down. x1, x2, x3. So since all of them have to be between 0 and 4, let's start with 4. So one such solution will be 4, 4 and 2. Then 4, 2, 4. Then 2, 4, 4. Then let's say I make x1 equal to 3 and x2 equal to 4 and then 3. Okay, so 4 plus 3 is also 10. So then 4, 3, 3. Then 3, 3, 4. So these are the only possible 6 solutions to this equation. Okay, you can check. You will not be able to get any more solutions. So there are 6 solutions. This is how inclusion and exclusion works with principle like the combination repetition. I told you there as well. To solve a generic question, you need inclusion and exclusion. Hi everyone. So welcome to lecture number 10 of counting. So we are doing data science and artificial intelligence complete GATE course. And this is lecture number 10. In the last lecture, we already saw how inclusion and exclusion principle works. In this lecture, we are going to see a few problems on inclusion and exclusion. So as to get used to the formula. And we will apply it with various techniques that we have seen so far, like combination repetition, repetition, and so on. So just to revise, in the general form, if we have n sets, then this is what the principle of inclusion exclusion looks like. So the cardinality of union of n sets, A1 union A2 union A3 up to an, is sum of the individual cardinalities taken one at a time minus sum of the cardinalities of intersection taken two at a time. Then plus the cardinalities of the sets, their intersection taken 3 at a time, and so on up to n at a time. So we will have like plus or minus sign whatever depending on the horizontal or n minus 1, and all taken all at a time. So this is what inclusion exclusion principle is. I have explained this in lecture number 9, so you can watch that video if you haven't. So let's see a few problems. So this is the first problem. Always try to solve the problem, pause the video and solve it on your own. So how many permutations of 26 small case English alphabets do we have that do not have cat, dog or mule as a substrate? See, there are various terms written in this problem. First is how many permutations of 26 small case English alphabets are there. So permutation means arrangements, we know. So we have 26 small case alphabets A, B, C up to Z. How many different permutations are there of 26 alphabets? 26 factorial. This goes way back to the first or second lecture, right? So we can arrange them in 26 factorial ways. For the first position, we will have 26 options. Then for the second position, we will have 25 options, and so on. That's how we derive factorial, right? There are 26 factorial total permutations of all the basically letters of English alphabet. Now we just want all such permutations which do not have cat, dog, or mule as substring. So, like, what is a string? Like, let's say this is a string, right? Like this is a string, right? And here, like, VAN is a substring of this string. So, substring means continuous string which is a part of this string. So, like, VAN is a substring of this string. So, like, when we create any permutation of all the letters from A to Z, when we create a permutation, let's say A, B, C, blah blah blah. Let's say you can have Q, R, S, T. This is also a permutation, like A to Z. You can write them in reversed order. Like, there can be many such permutations, but some of them will have C, A, T in that order, right? And you can have like other alphabets here. So this is one such string. It can have CAT in the middle somewhere, or it can start with CAT. It can have cat, and it can have cat and dog both as well as the substrate. Since C, cat, dog, CAT, DOG, and MULE, these are all animals and they don't have any character in common. Basically, you can have cat and dog both as a substring of a string. Right? You can have a string like this. You can have a string like CAT. It has a CAT. It has a dog, and it can also have mule in the same string. So you can have MULE as well, and you have remaining characters here and there. Blah blah blah. Okay, so this can be one such string. So it has like all three, cat, dog, and mule in it. Since they don't have anything in common, it is quite possible that you can have all three as the substring of the string as well. So what we want is now, so we will apply the principle of inclusion exclusion here. We know that there are 26 factorial total permutations. Right? So we'll subtract all those which have cat as a substring. So if you have to have cat as a substring, I already told you how to solve this problem. So consider CAT cat as a single word. Consider CAT cat as a single word and all other characters as different letters. So how many total letters now you have? So 26 minus 3, 23 we have here, plus 1, 24. Total 24 letters we will have, considering CAT as a single letter. Then we will have 24 letters and we can arrange them in 24 factorial ways. So there are 24 factorial ways in which cat will be present as a single letter. Similarly, we will subtract all those with dog as a substring. So all the permutations in this dog as a substring, again they will do 24 factorial, since dog is also of length 3, same way. And again we will subtract all those which have mule as a substring. So for mule to be a substring, consider mule to be a single letter and consider all other characters to be different letters. So how many we will have here? 22 we will have here and 23. So 23 factorial. So we subtract all those having cat as substring, dog as substring, and mule as substring. Then we will add all the combinations in which we have both cat and dog as substring. So both cat and dog as substring. So it means we have to consider cat as a single letter and you have to consider dog as a single letter, because cat and dog will always come together. And then how many letters are remaining? So 1, 2, 3, 4, 5, 6 are gone. So 20 more are there. 20 plus 1, 21 and plus 1, 22. 22 different letters are there, considering cat as one word and dog as one letter. So 22 factorial. Right? And then similarly we will add all those combinations in which we have cat and mule together. So for cat and mule to be together, so 7 are gone, 19 more are there, so 19 and then 21. Okay? And then again we will add all those combinations in which, all those permutations in which dog and mule are together. Again it will be 21 factorial, you can check. Okay? So this is taken like 0 at a time, then 1 at a time, then added 2 at a time. Then now we will subtract all 3 at a time. So from this, we will subtract all the permutations. From this, we will subtract all the permutations in which we have all 3, which means cat, dog, and mule, all 3 as a substring. So consider this as a single letter, consider this as a single letter, consider this as a single letter. Consider them G1, G2, G3. Then how many other alphabets are there? 10 are gone, so 16 are left. So 16 plus 1, 17, 18 and 19. So we have 19 factorial such combinations in which all the 3 come as a substring. So these many possibilities are there. You can take 19 factorial common and do some math, but it is not required. This is your answer, like 26 factorial minus 2 times 24 factorial minus 23 factorial and so on. Okay, this is your answer. Cool. Let's move to the next problem. So, yeah. In how many ways can the letters A, B, B, C, C, D, D be arranged such that no 2 consecutive characters are same? Okay. So firstly, we can see like in how many ways can we arrange these characters. There are 8 characters given, 2 A's, 2 B's, 2 C's and 2 D's. In how many ways can I arrange these characters? So it is like we have 8 different letters. So 8 factorial upon, I told you, like see since A and A are together, first consider them different, A1, A2. So how do I do that? If like since we are over counting every 8 twice, you have to divide by 2 factorial. Then for B also 2 factorial, for C also 2 factorial, for D also 2 factorial. Over counting every permutation these many times. So this is our answer if all the letters, like if there is no condition given. And this is the number of ways in which we can arrange A, B, B, C, C, D, D. Right? We already have seen this in previous videos. You can watch the video. And now we have a condition. So that condition is which makes this problem inclusion exclusion. So such that no 2 consecutive characters are same. It means that A and A cannot come together. Both A's cannot come together. See, in these permutations, it will be possible that they are coming together. So like it has to be something like this: A, B, C, A, D, C, D, B. It can be something like this. Here, no 2 consecutive characters are same, right? So basically, both A's, both B's, both C's, both D's cannot come together. So again, like let's apply inclusion exclusion. We know that the total number of possible permutations here are 8 factorial upon 2 factorial, 2 factorial, 2 factorial, 2 factorial. This is total number of arrangements of A, B, B, C, C, D, D. Okay. Now we have to subtract all the cases in which both the A's come together. So right now I'm only taking all the cases in which A's come together. Right. Similarly, we will have B's come together. So like it's a set. Like we have 4 sets here: A, B, C, and D. A come together, B come together, C come together, and D come together. Right? And there are a few cases in which all of them come together as well. So one such string is A, B, B, C, C, D, D. So here all the consecutive characters are coming together. Right? Like the same characters. So what we will do, we will subtract all the cases in which both the A's are together, which means we have to consider this as a single letter. So how many letters we have? 1, 2, 3, 4, 5, 6, 7. 7 letters are there, 7 factorial ways. And here there is some repetition. So B is coming twice, C is coming twice, and D is coming twice. Both A is a single letter anyway. So we will have 2 factorial, 2 factorial, 2 factorial for B, C, and D. So let me write it in a compact way. So the total number of initial ways was 8 factorial upon 2 factorial to the power 4. This is total permutations. I will subtract all those in which both the A's come together, which means 7 factorial upon 2 factorial cube. This is the total number of ways in which both the A's come together. And also similarly for both the B's, B, C and D, the number of ways will be same. You can consider both B's to be together, then the number of ways will be same only. So this will be subtracted 4 times. For A, either A's are coming together or B's or C's or D's. Basically the cardinality of A coming together, B, C and D are same. Right? So like this will be subtracted 4 times. Now we will add the cardinality of A intersection B, which means A is also coming together and B is also coming together. So it means A is considered as single letter, B is also considered as single letter. Then we have 2 C's and 2 D's. So total 6 letters are there, 6 factorial upon 2 factorial for C, 2 factorial for D. And these are individual letters. So these many 6 factorial upon 2 factorial, 2 factorial. Or I should write it in like this, 6 factorial upon 2 factorial square. This is the number of ways in which both A and B come together. Now we have to add this for all possible pairs. A and B, B and C, C and D, A and C, A and D, and C and D, right? So we have 4C2. We have 4C2 such combinations, which means like 2 at a time. From the 4 sets, if I want to take 2 at a time, we have 4C2 combinations. For all those 4C2 combinations, we are taking 2 at a time. And the number of cases is same, 6 factorial upon 2 factorial square. Right? So this is like taking 1 at a time. This is taking 2 at a time. Then we have to subtract all those in which we are taking 3 at a time. The number of such triplets will be 4C3. Which means A, B, C are coming together, A, B, D, B, C, D. So these are the 4 cases, right? A, B, C, A, B, D, A, C, D and B, C, D. So consider any one of them. So if A and B, A is considered a single letter, B is considered a single letter, C is considered a single letter. Total number of letters we have is 1, 2, 3, 4, 5. So 5 factorial upon 2 factorial. So this is 5 factorial upon 2 factorial. Then finally we will add that one case in which all of them come together. A, B, C and D. All of them come together. There is only one such case, 4C4. And how many ways can we do, can we arrange them? So like all of them are single letters. So there are 4 factorial ways. So this is the number of ways in which you can solve this. You can calculate it. Okay. It will come out to be 864. You can do the math. So there are 864 such permutations possible. Okay. So consider this next question. So what is the number of integral solutions to the following system of equations? X plus y plus z is 18. X has to be between 1 and 6. Y has to be between 2 and 5 and Z has to be between 3 and 7. So this includes all the concepts that we have seen so far. Okay, combination with repetition and inclusion exclusion. So how to solve this problem? So we have this equation x plus y plus z is equal to 18. Now the condition given is x has to be between 1 and 6. Y has to be between 2 and 5. And Z has to be between 3 and 7. Okay. So we know that how to handle the left hand side of the solution equation, right? If x has to be at least 1, we will give 1 to the x. If y has to be at least 2, we will give 2 to y. And if z is less than, has to be at least 3, we will give at least 3 to z. So basically we will write x as 1 plus a, and we will write y as 2 plus b, and we will write z as 3 plus c. Right? So what will happen? This equation will become a plus b plus c is equal to 12. And the condition here will become 0 is less than equal to a is less than equal to, so basically subtract 1 from all the sides. A has to be between 1 and 5. And b here has to be between 0 and, subtract 2 from both the sides. B has to be between 0 and 3. And c has to be between 0 and 4. Right? Now we know how to solve this equation. If right hand side condition is not there, so if a, b and c have to be greater than or equal to 0, we know that the number of solutions to this equation is 14C2 from combination with repetition, right? So let's forget about this equation now. We just have this equation. We already have merged this equation to this. Okay, we just have to solve this system of equations. Okay, we know that the total number of solutions to this equation is 14C2 if there are no conditions. Right? So we will subtract all the solutions in which one of the conditions is failing. One condition is failing. So let's take a condition. If this condition has to fail, a has to be greater than or equal to 6. If I don't care about b and c right now, a has to be greater than or equal to 6. So if only a is greater than or equal to 6, the total number of solutions will become what? Again, like write A as 6 plus P. Okay, it will become easier. Like once you like do more and more problems, write A as P plus 6. So this will become P plus B plus C is equal to 12 minus 6, which is 6. So there are 8 C2 ways in which A is greater than or equal to 6. Similarly, we have to subtract all the cases in which B is failing the condition. So now we don't care about A, we only care about B. So basically B is greater than or equal to 4. So there are 9 C2 such ways. Okay, so B is greater than or equal to 4. So write B as P plus 4. So write B as P plus 4. So the equation becomes A plus B plus C is equal to 8. And the number of solution is 8 plus 2, 10 C2. Here B is greater than or equal to 4. Okay. Similarly, we will subtract all the cases in which C is failing its case, which means C is greater than or equal to 5. Right? So if C is greater than or equal to 5, the equation becomes A plus B plus P is equal to 7. Right? So the number of solutions is 9 C2. C is greater than or equal to 5. Now we will add all the cases in which 2 of the conditions are failing. So let's say now we will add all the cases in which A is also greater than or equal to 6 and B is also greater than or equal to 4. Both the conditions are failing, which means I have to write A as P plus 6 and B as Q plus 4, which means P plus 6 plus Q plus 4 plus C is equal to 12, which means P plus Q plus C is equal to what? 2. And the number of solutions to this equation is what? 4C2, right? So we will add all the cases in which A is also failing its case and B is also failing its case. Right? Similarly, we will add all the cases in which A is also greater than or equal to 6 and C is also greater than or equal to 5. So this will become 3C2. And similarly, we will add all the cases in which B is greater than or equal to 4 and C is greater than or equal to 5. So we have 9 here, so it will become 5C2. And finally, we will subtract, see, inclusion, exclusion. We will subtract all the cases in which all the 3 conditions are failing, which means A is greater than or equal to 6 and B is greater than or equal to 4 and C is greater than or equal to 5. Is it even possible? It is not possible, right? If all the 3 conditions are failing, the sum cannot be 12. The least amount of sum is 15. So this becomes 0. There are no cases here. So you can try solving it and this will come out to be 1. Okay. There is only one solution to this equation. You can solve this. Okay. So this is lack of thinking clearly. If you directly jump to the problem, this might happen. But still you will get the answer. This will come out to be 1. Okay. But if you see the constraint really carefully, since x has to be less than or equal to 6 and y has to be less than or equal to 5 and z has to be less than or equal to 7, the only solution to this question is x equal to 6, y equal to 5 and z is equal to 7. Since their sum is 18. Right? So the only solution was 6, 5, 7. But yeah, if you apply the formula and apply inclusion exclusion, you'll get the same result. There is only one solution to this equation. Cool. And there is one more application to inclusion exclusion formula, which is the number of onto functions possible from set A to set B. Okay. So if you consider 2 sets A and B, A contains n elements and B contains m elements. So what is a function? It is a mapping from one element of A to one element of B. Okay. This is a function. So I will make a separate video on all possible questions on functions, like number of functions, number of unknown functions, onto functions, bijections, surjections. I'll make a separate video on it. And it involves counting as well, since it is all PNC. So I will make one separate video on all the questions on functions and how it is linked to PNC. But for now, if you have to count the number of onto functions from set A to set B, it involves inclusion and exclusion principle. How? What is an onto function? So just consider this. An onto function is a function in which there cannot be any element left in codomain. Basically, range has to be equal to codomain. So this element cannot be left. There should be at least one mapping. There should be at least one mapping for every element in set B to set A. So what does it mean? This is not allowed. This element cannot be left empty. So like one such thing is like we already know like m has to be less than equal to n. Then only this is possible. First thing, right? If m is greater than n, it is not even possible because you will have more elements here and some elements will remain empty. So there should be at least one pre-image of every element in B. That is what an onto function is. So again, you can use the inclusion exclusion formula to solve this. So if you have this as set A and this is set B, this contains m elements and this contains n elements. So the total number of functions from A to B is what? M to the power n. How? See, for every element in the first set, we have m options. For every element in the first set, we have m options. It can map to anything. Right now, we don't have any conditions. So total number of functions possible is m to the power n. For every element in the first set, you have m different options. It can map to anything. So you have m to the power n options. Minus all the cases in which one of the elements has no pre-image. If this element does not have any pre-image, then every element here has to map to the remaining m minus 1 elements. So every element will have only m minus 1 options. So m minus 1 to the power n. And how many such cases are there? MC1 such cases are there. There are MC1 cases in which like only one of the element remains empty. Similarly, we will add all the cases in which two of the elements don't have pre-image. So we choose two elements in MC2 such cases, and if two elements don't have any pre-image, all the elements have to map to the remaining m minus 2 elements, and so on. So we can apply the inclusion exclusion formula to calculate the number of onto functions from set A to set B, and this will be the formula. So these are the few use cases of inclusion exclusion principle. So we have seen permutation combination without repetition first, factorial, and then permutation combination with repetition, a few examples, binomial multinomial theorem and its motivation, like how it links with combinatorics. Then we saw inclusion exclusion formula and we solved a few problems. The few topics which are left in PNC are seating arrangement, circular arrangement and rearrangements, which we will see in future lectures. And also I will host a few practice problem sessions and doubt solving sessions. You can attend those and ask your doubts. Also do keep commenting your doubts on every lecture that you have. I'll keep responding to those. Thank you. Bye.
Hi everyone. Welcome to lecture number 11 of GATE data science course, and we are learning counting. So far we have learned so many things: inclusion, exclusion, binomial theorem, permutation, combination, with repetition, without repetition. But sometimes like questions might come where arrangement is not linear, where let's say n people are not sitting in a row. Okay. And those questions are slightly trickier than like normal arrangements, and we will see that in this lecture. We will see circular arrangements. Normal seating arrangement we have already seen. So what is the difference between normal seating arrangement and a circular seating arrangement? So like if let's say 3 people are sitting in a row, 1, 2, 3. So let's say there is a dinner table and it's a linear table, okay? And you have 3 places and you have 3 people to sit on these 3 places. So we already know in how many ways we can do that, right? It's very easy. Let's say the people are A, B and C. So they can sit in these 3 places in 3 factorial ways, okay? That's the basic notation of factorial that we have seen in the second video. So the number of ways in which n people can see in n places in a linear fashion is n factorial, that we have seen. But now what is circular arrangement? So now let's say there is a round dining table, okay? And let's say here we have 4 places. There is a dining table and there are 4 places, okay? And now 4 people want to sit, A, B, C, D. So generally speaking, when they say about circular arrangement, the seats in the table are not marked. So you have not marked these seats, okay? So let's say now A sits here, B, C, D. So what only matters is Ki who is sitting on one side of A and who is sitting on the other side of A. See, when you are sitting in a circular table, it doesn't matter where you are sitting. You are sitting here, here or here. It doesn't matter, okay? It just matters what is the order of people like on that particular circular table. So what happens is, these 4 people either sit in this way or, so let's say I'm creating another table and here let's say A is sitting here, B is sitting here, C is sitting here, D is sitting here. So when we talk about circular arrangements, these 2 arrangements become same. Why? Because the neighbors of A are same, B and D. Here also the neighbors of A are same, B and D. Here the neighbors of D are A and C. Here also the neighbors of D are A and C. So the neighbors of all the people are same in both the cases. You are just rotating the table, it doesn't matter, right? It's a circular table, you are rotating the table, it doesn't matter where people are sitting, just the neighbors matter. So these 2 arrangements become same. So that's why linear arrangement and circular arrangements are slightly different. So yeah, permutations when considered as arrangements are sometimes referred to as a linearly ordered arrangements. So by default, when nothing is mentioned, when the question is only about in how many ways can we permute or how many different permutations are possible, by default it is linear arrangement. You have to place objects in a row in a linear fashion. In these arrangements, there is a first element, there is a notion of first element in such cases, a second element and so on. Okay, but when people are sitting in a circular table, there is no first element, right? Think of it as circular linked list, right? There is no first element. Okay, we have a notion in linked list like of head, but in general, when you talk about circular lists, there is no first element, right? So if, however, the objects are arranged in a circular manner, this distinguished ordering no longer exists. There is no particular ordering and there is no first element in the arrangement. Any element can be considered as the start of the arrangement. So when n people are sitting in a circular fashion, any person can be considered as the first person basically, right? So these arrangements of objects in a circular manner are called circular permutations. And so this is very important. So this gives us the difference between linear and circular arrangements. 2 circular permutations are equivalent if one can be rotated into the other, that is cycled without changing the relative positions of the elements. So here the same thing happened. I just rotated the table 2 times and A comes here, B comes here, C comes here and D comes here, right? So I just rotated the circular table twice. So if one permutation can be rotated and other can be found, these 2 will be equivalent. So I'll give you one more example. So here what happens? The circular ordering is 1, 3, 2, 4. In this permutation also the circular ordering is 1, 3, 2, 4. Okay, so these 2 will be same. You can just rotate it once clockwise and you'll get this. But these 2 are not same. Why? There is no way you can rotate this and get this, right? Because one has the same position. Now see, the neighbors have changed, right? So for 1, 3 was sitting on left and 4 was sitting on right. But here for 1, 4 is sitting on left and 3 is sitting on right, right? So for one particular element, the neighbors on left and right changed. And this is not allowed. Basically, you cannot rotate it and get this. So these 2 circular arrangements are different, but these 2 are same. So now we want to count how many circular arrangements are possible, right? So for a set with n elements. So we want to arrange n elements. Let's say the elements are 1, 2, 3, 4, up to n. And we want to arrange them in a cyclic order, okay? So let's first solve it for, let's say, 4 elements, okay? 1, 2, 3, 4. How many linear arrangements are possible? Again, so there are 4 factorial linear arrangements, which is 24. There are 24 ways in which 4 people can set in 4 linear places, basically permutations, right? Now we want to do the cyclic thing. So I'll draw it here. So what I will do is, for now I will number these places, let's say. There is no actual numbering, I'm just numbering it for the sake of proof. So let's say these 4 places are 1, 2, 3, 4. Okay. Now these 4 people, we should name them A, B, C, D so that there is no confusion. So let's say there are 4 people, A, B, C and D. And they want to sit in these 4 places, 1, 2, 3, 4. Now, if I write all possible permutations first. So what I will do is, let's say this is position number 1, this is position number 2, this is position number 3, this is position number 4. Okay. So if I write all possible permutations, so one possible permutation will be A, B, D, C. And so on. So the last permutation will be D, C, B, A. Okay. So there are 24 such permutations and I have numbered them 1, 2, 3, 4. So what I am trying to say is like at position number 1, so the first permutation says that A is sitting at position number 1, B is sitting at position number 2, C is sitting at position number 3 and D is sitting at position number 4. So what happens is the first permutation looks like this. Right. So what happens is there will be one permutation, okay. In these 24 permutations, there will be one permutation like D, A, B, C. Okay, among these 24 permutations, there will be one permutation called D, A, B, C also. What will that denote? That will denote this. D, A, B, C. And I told you that these two circular permutations are same. They are same, right? Because you can rotate this once clockwise and you'll get this. Right? So actually, the number of circular permutations is not same as the number of linear permutations because we are overcounting. Again, overcounting is there, right? Since this permutation is same as this permutation. Right? But these two are different. Notice, these two are different because A, B, D, C will be what? A, B, D, C will be A, B, D, C in position number 1, 2, 3 and 4. You cannot rotate this and get this. Okay? You cannot do that. Because D and C have interchanged the side, so you cannot rotate it. So these two permutations, linear permutations are different when counting circular arrangements, but these two are same. So now we want to find how many times are we overcounting. So each permutation we are overcounting some number of times. We want to see that. So what happens is, just take the first permutation A, B, C, D. This is the first linear permutation. If I rotate it n times, I will get different permutations. So let's say I rotate it once. I will get B, C, D, A. And I again rotate it once. So basically I am shifting everything to left and rotating, right? So now C comes here. So C, D, B, A. C, D, A, B. Okay. And then again let's say I rotate it once. So I'll get D, A, B, C. If I rotate it again, I will get A, B, C, D again. So what happens is, these 4 permutations, they are different linear permutations. They all come in these 24. Okay. These 4 linear permutations denote the same cyclic permutation. See, A, B, C, D. That's what we are doing, right? Like we are just rotating it. So this is the first permutation at position number 1, 2, 3, 4. The second one is B, C, D, A. At 3, 1, 2, 3, 4. The third one is C, D, A, B. And the fourth one is D, A, B, C. Right? They all can be formed using one another by just rotation. See? Right? So these 4 linear permutations are same in circular permutation. Actually, we are overcounting every permutation 4 times. If you see it, why is it happening? Why is it happening? We are actually creating groups. See, this is a group. This is a group of 4 linear permutations which denote the same circular permutation. We can have another group. Let's take some other permutation, A, B, D, C. This is another linear permutation. You again rotate it 4 times. B, D, C, A, D, C, A, B, and C, A, B, D. These are different 4 permutations, linear permutation. They all come in a single group, and they all 4 denote the same circular permutation. So what happens is, every group of 4, so in these 24, there are groups of 4 which denote the same circular permutation. So how many different circular permutations will we have? 24 divided by 4. There will be 6 such groups. There will be 6 such groups of 4 each, and they will all denote as unique circular permutation. And why is it happening that way? Since the size of the linear list was 4. Since the size of the linear list was 4, you can rotate it 4 times and you will get a different permutation every time, right? And if you so basically when you rotate it the 4th time, you get the same permutation. So that's why you get 4 different linear permutations which denote the same circular permutation. That's why. Okay. So this is like the number of circular permutations of 4 objects. Similarly, like when you want to count the number of circular permutations for n objects, the same thing will happen. So if you have n objects, this is the linear permutation. We know there are n factorial linear combinations, right? Now, if I take any one of them and if I rotate it n times, so let's say 2, 3, 4, up to n, 3, 4, 5, sorry, up to n and 1, and here up to 2, and so on. So if you rotate it n times, you will get n different linear permutations, and they will all denote the same circular permutation because they can be rotated one after the other and you'll get the same circular permutation. So every permutation here will be repeating n times. We can rotate it n times. So every permutation we are overcounting n times. So the number of circular permutations will become n factorial upon n. Just like the 4 example, right? So what is this? We know that n factorial is n times n minus 1 factorial upon n. Okay, so the number of circular permutations of n objects is n minus 1 factorial, not n factorial. Okay, we are overcounting every permutation n times. Cool. So let's see a few examples. It will be more clear. There are 3 couples A, B, C, D, E, F. Basically, there are 6 people. A and B are a couple. C and D are a couple. E and F are a couple. So 3 couples, which is 6 people, are sitting on a table. By default, it will be a linear table, okay, if nothing is mentioned. How many total linear arrangements are possible? Very easy question. 6 people sitting in a row. How many linear arrangements are possible? 6 factorial, which is 720. Right? 6 people in a row. Now again, the same 6 people are sitting on a circular table instead of a linear table. How many circular arrangements are possible? We already saw the formula. The number of circular arrangements is n minus 1 factorial. So if 6 people want to sit, the number of circular permutations will be 6 minus 1, which is 5 factorial, which is 120. Okay, since we will be overcounting every permutation 6 times, so we have to divide by 6. 6 factorial upon 6 becomes 5 factorial, which is 120. Okay. Now, the next question is, again 6 people are sitting on a linear table. In how many ways A and B always sit together? In how many ways A and B always sit together? Okay, try to solve this. We have already done it in permutation lecture, right? These are 6 places. A and B always have to sit together. How do we handle this type of situations? Consider A and B as a single group G. Consider AB as a single group G. So how many elements will we have? G, C, D, E, F, 5. In how many ways can I arrange 5 elements in a row? 5 factorial. Basically, we are dividing the task into 2 tasks, T1 and T2. Consider A and B as a group. And then arrange AB among themselves. Okay, consider first AB as a group and then arrange AB among themselves, and rule of product, right? So if I consider AB as a group, how many arrangements are possible? 5 factorial. There are 5 factorial ways in which I can arrange 5 objects, G, C, D, E and F. And now G itself is AB. So we can arrange elements of G among themselves. A and B can go here and there, right? So this is one such permutation, and B, A, C, D, E, F. This is also another permutation. Here also A and B are sitting together, right? So 5 factorial into 2 factorial. This is the number of ways in which we can arrange A and B among themselves. 2 people in 2 places, right? So this is the number of ways. It is 120 into 2. 240. Okay. So this was linear arrangement, and now we have circular arrangement. So in circular arrangement, there is a interesting thing. Okay, if only two people in a circular table, let's say there are at least three people on a circular table. Okay, what I am talking about is there are at least three people. For now, assume that. So let's say there are four people sitting, A, B, C, D. So what happens is, in a circular arrangement, if only two people, any two of them, if only two people switch their sides, switch their seats basically. Let's say A and B switch their seats. B, A, C, D. If only two people will switch their seat, you will always have a different circular permutation. You will not get the same circular permutation, right? You cannot get. Since two people are only switching, the other people are remaining at the same place, you cannot rotate it then to get that particular, the other arrangement, right? Feel this thing, right? You can try to switch any two places. Then you will not be able to rotate and get the same permutation. So when you are switching, when only two people are switching sides, you will get a different circular arrangement. Okay. We will use this knowledge in this question. So now what happens is, again, six people are sitting on a circular table. In how many circular ways A and B always sit together? That's what we want to find. We know that how many circular arrangements are there? The number of circular arrangements for six people is 5 factorial. N minus 1 factorial, which is 120. Okay. Yep. So the number of circular arrangements of 5 people of 6 people is 120, 5 factorial. Now what we want is, there are 6 people, A, B, C, D, E, F. The constraint is A and B should always sit together. Okay, so we'll use the same logic as linear arrangement to solve this problem. If A and B always want to sit together, basically this cannot be a configuration. A, C, D, B, F, E. This is not allowed. Since A and B are not sitting together, right? There is C in between. So what we do is, we consider AB as a group G. Again, we consider AB as a group G. Now we want to, again, we can divide it in two tasks. Firstly, arrange G, C, D, E and F together. Firstly, arrange G, C, D, E and F on a circular table. In how many ways can I arrange 5 people in a circular table? 5 minus 1 factorial, which is 4 factorial. There are 4 factorial ways in which 5 people can sit on a circular table, right? Now, in every such permutation, A and B can also switch sides, right? So this is one permutation. Now A and B can switch sides. B, A, C, D, E, F. If I consider G here, in every such permutation, A and B can switch sides. So again, we can arrange A and B among themselves also. So again, into 2 factorial. It's same as linear 1 only, okay? We considered AB as a group. We first arranged G, C, D, E, F in a circular table, and then we arranged AB among themselves. So this is the number of ways in which we can arrange this. So it is 24 into 2, which is 48. Okay. Okay, now the most interesting question. You should try it on your own first. This will apply like most of the concepts that we have seen. So now 3 couples that like A, B, C, D, E, F are sitting on a circular table. In how many ways no couple sits together? That's an interesting question, right? No couple sits together, which means A and B should not sit together. They should not be adjacent to each other. C and D should not be adjacent to each other. E and F should not be adjacent to each other. Okay? Since none of them can be adjacent to each other, this is an interesting problem, right? Like you cannot easily solve it. You need inclusion exclusion to solve this. In inclusion exclusion, I told you, like this is the motivation of inclusion exclusion basically. Since we cannot solve the no problem, but we can solve the yes problem. See, we already know how to solve the yes problem. What is yes problem here? A and B sit together. We know how to solve the problem in which 2 people sit together. but we don't know how to solve the problem in which two people don't sit together, right? So what we do, we count the total number of ways and then we minus the number of ways in which they sit together, right? But now here there are three groups and none of them can sit together. We know how to solve the problem in which AB sit together, CD sit together, EF sit together. We know the solution to yes problem, but we don't know the solution to no problem. So that's where we apply inclusion exclusion, right? So let's say there are three sets. S1 is A and B sit together. S2 is C and D sit together. And S3 is E and F sit together. We want none of this to happen. Right? So if this is my entire set, Venn diagram wise, this is my set S1, S2, S3. Set S1 denotes, this is like the universe is all possible arrangements. All possible circular arrangements of 6 people. That's my universe. Set S1 denotes all the arrangements in which A and B are sitting together. S1 denotes all the arrangements in which A and B are sitting together. S2 denotes all the arrangements in which C and D are sitting together. And S3 denotes all the arrangements in which E and F are sitting together. Right? What we want is, we want this outside area. We want none of them to sit together. We want this outside area. So basically calculate this union and then subtract from the universe. That's what we want, right? So how do we do that? So what is the total number of circular permutation of 6 people? 5 factorial. Total arrangements. Minus. Now A and B cannot sit together. Okay, right? So we will subtract all the ways in which A and B are sitting together. Then we will subtract all the ways in which C and D are sitting together, and also subtract all the ways in which E and F are sitting together. Now since we subtracted all these 3 sets, we subtracted these middle area twice. The basic principle of inclusion exclusion, right? We subtracted this area twice. So we'll add that. So plus S12. These are all the ways in which A and B also sit together, C and D also sit together. Right? And similarly, we will add all the ways in which these two conditions happen. Then also we will add all the cases in which these two conditions happen together. Right? And then what will happen if we do this? This area will not be subtracted at all. We add it 3 times, we subtract it 3 times. So we'll have to subtract it again. Standard inclusion exclusion, right? 0 at a time, subtract 1 at a time. These are one condition at a time. These are 2 conditions at a time. And these are 3 conditions at a time. Right? This we have already seen. So the total number of arrangements is 5 factorial minus. Now since these 3 will be same, these are identical problems. We can solve any one of them. AB sit together or CD sit together or EF sit together, it doesn't matter, right? These are identical problems. These 3 will be same. So 3 times solve any one of them. In how many ways A and B sit together? Consider AB as a group. We already solved it, right? Consider AB as a group. Now you will have C, D, E, F. There are 5 people in a circular table. So our number of arrangements is 4 factorial times 2 factorial to arrange A and B among themselves. So times 2 factorial. Okay. Now plus these 3 again will be same. These are identical problems. Ki A and B are also sitting together. C and D are also sitting together. One of them is this. Other problem is C and D are sitting together. E and F are sitting together. They are identical problems, right? So you can calculate any one of them and it will be 3 times that. So let's solve the first problem. AB also sit together. C and D also sit together. So what will happen? Consider AB as a group G1, CD as a group G2, and then you have E and F. So you have 4 people. Number of circular arrangements is 3 factorial. Now A and B can arrange among themselves and C and D also can arrange among themselves. So you have to multiply by 2 factorial and 2 factorial. Right? So this is the number of ways in which AB also sit together and C and D also sit together. Okay? And now minus. all these three conditions happen, which means AB is a group, CD is a group, and EF is a group. Number of circular arrangements of 3 people is 2 factorial. And into AB can arrange among themselves, EF can arrange among themselves, and CD can arrange among themselves. So 2 factorial, 2 factorial, 2 factorial. Okay, so that's your equation. So you can calculate it. It will be 5 factorial is 120 minus 24 into 2, 48. Okay, so 24, it will become 24 into 6. 144 plus, what will this be? 6 into 4, 24 into 3. It will become 72. And minus, this is 2 to the power 4, 16. Okay, so you can calculate this. This will come out to be 32. Okay, there are 32 ways in which no couples sit together. Standard inclusion exclusion. Cool. So we have learned like the number of circular arrangements, and we have solved a few complicated problems here as well. You can create more such problems in how many ways all couples sit together and so on, right? There are many such problems, and we will solve them in like the problem solving sessions. I will have problem solving sessions live. So yeah, we will solve these type of questions there. Hi everyone. So this is lecture number 12 of counting, and we will learn de-arrangement in this lecture. Very important concept. Very few times GATE has asked this in GATE Computer Science, but yeah, like this might come. And now since like for GATE Data Science, they have less syllabus, so I'm expecting more questions from probability statistics and like in-depth questions from probability specifically, because probability is core to ML, right? So you can have deep questions from de-arrangements as well. So yeah, we will learn every concept which might come. So yeah, de-arrangement. What is de-arrangement first? We know what is arrangement. Very easy, right? Arrangement is permutation. Like in how many ways can we arrange n people in a row? Shuffle them basically. It's as the name suggests, de-arrangement is what? Not arrangement. Okay. So there should be some notation of what is not here, right? There is a beautiful notation. So let's say there are, the standard problem is letter boxes. Okay. So generally in like at your home, if you have a complex or like let's say 10 floors, so there will be numbered, like for your flat, for your particular home, you will have one letter box, right? And your flat number will be mentioned, let's say 1, 2, 3. Okay, let's say there are 3 people living in a certain society, there are 3 homes, and you have 3 letter boxes, 1, 2 and 3. And now 3 letters come. You have 3 letters, 1 for each person. This is for like house number 1, house number 2 and house number 3. So what is arrangement? What is so ideally what should happen? Like the letter number 1 should go in the box number 1. The letter number 2 should go in the box number 2, and letter number 3 should go in the box number 3. What is de-arrangement is, in how many ways can I put these 3 objects in these 3 boxes such that no object goes in the correct position. That's why de-arrangement, okay? Not an arrangement. What happens is, none of the object goes in at the correct place. Basically, 1 should not go in this 1. 2 should not go in box number 2. And 3 should not go in box number 3. Which means that you can have 2 here, 3 here and 1 here. This is okay. Right? Similarly, you can have 3 here, 1 here and 2 here. This is also okay. But let's say 2 here and 1 here and 3 here. This is not okay, because the letter number 3 is in the correct box. This is not allowed. Similarly, 1, 2, 3 is also not allowed, because all 3 are in the correct box. This is definitely not allowed, right? So this is the de-arrangement. In how many ways can we put n objects in n places such that no object is in its correct place? Right? And see, this is tricky. You don't know. We don't have a way to calculate this yet. We know a way, and that is using inclusion exclusion again. So in the last lecture I told you, when you don't know the answer to the no problem, see, no object can be going in the correct place. We don't know the answer to the no problem, but we know the answer to the yes problem. In how many ways can all three letters go in the correct place? One way. You put 1 here, 2 here and 3 here. In how many ways can letter 1 go in the correct place? There are 2 factorial ways, because 1 has to go here and 2 and 3 can go anywhere, right? We know the answer to the yes problem, but we don't know the answer to the no problem, right? So that's where we apply inclusion exclusion. So we will solve this. So this is the question. 3 letters numbered 1, 2 and 3 have to be placed in 3 covers numbered 1, 2 and 3. In how many ways can this be done if no letter goes in the same numbered cover? Okay, same problem. And we are also assuming that no cover remains empty. Okay, this is all based on the assumption that no cover can remain empty. You have to place 1 letter in every cover. So we will use inclusion exclusion to solve this. So we have 3 covers, 1, 2 and 3. And we have 3 letters, 1, 2 and 3. Okay, we have to place them here. So again, inclusion exclusion, let's say set S1 is what? Letter 1 goes in cover 1. Letter 1 goes in cover 1. Similarly, S2 is letter 2 goes in 2. And set S3 is 3 goes in 3. Okay. Again, it's a symmetrical problem. So, like, how many total arrangements are there? There are 3 factorial, which is 6 arrangements. There are 3 factorial total arrangements. And we will subtract S1, S2 and S3. Inclusion exclusion, right? We don't want the letter 1 to go in cover 1. So, we will subtract all the ways in which letter 1 actually goes in cover 1. Again, we will subtract all the ways in which letter 2 actually goes in cover 2. And again, we will subtract letter 3 going in cover 3. But when we subtract this, we are actually undercounting. So when both 1 goes in 1 and 2 goes in 2, we are subtracting it twice. We have to subtract it only once. So we have to add it once. Inclusion exclusion, right? Plus S12 plus S23 plus S31 minus S123. Okay. So what is this? This will become 3 factorial minus all these 3 will be same. This is a symmetrical problem. You like do any one of them, the answer will be same. So 3 times. Now letter 1 goes in cover 1. So in how many ways can we arrange the other 2? 2 factorial ways. Now plus 3 times. These 3 also will be symmetrical problems. So we can solve any one of them. Let's say 1 goes in cover 1 and also 2 goes in cover 2. Now if letter 1 is going in cover 1, letter 2 is going in cover 2, what happens to the third cover? There is only 1 letter left, right? You have to put it here. There is only one way to solve this. So 3 times 1 and minus all 3 of them are true, which means 1 goes in 1, 2 goes in 2 and 3 goes in 3. Again, there is one way to do this. 1. So it becomes 6 minus 3 times 2. 6 minus 3 times 2 is 6 plus 3 minus 1. So it becomes 2. Okay. There are only 2 ways, actually, it seems. And we actually have written it here. Right. So there are only 6 ways, right? I can actually enumerate all the 6 ways in which we can arrange 3 letters. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And the cover number are 1, 2, and 3. So this is definitely not allowed. 1 is in 1. This is not allowed. This is also not allowed. Letter 1 is in cover 1. Is this allowed? 2, 1, 3. This is allowed. No letter is in the correct letter. Okay, so this is also not allowed. 3 is in the correct position. This is also not allowed, right? 3 is in the correct cover. 2, 3, 1. This is allowed. 3, 1, 2. This is also allowed. 3, 2, 1. This is not allowed because letter number 2 is in the correct cover. So there are only 2 ways, which we have written here as well, right? Cool. So the number of this is called the number of D arrangements of 3 letters, or basically the number of D arrangements of a set of size 3. The number of D arrangements of a set of size 3 is 2. There are only 2 ways in which we can de-arrange 3 numbers, 3 words, whatever, right? So this is a standard combinatorial notation. We have a combinatorial notation for this as well. We know that the number of arrangements of n objects is factorial n. Then the number of D arrangements of n objects in a row is subfactorial n. denoted by this. We write the factorial symbol before. Okay, this is a standard notation. This is n factorial. This is subfactorial n, which means the number of d arrangements of n objects is subfactorial of n. So in combinatorial mathematics, a d arrangement is a permutation of the elements of a set such that no element appears in its original position. The number of d arrangements of a set of size n is known as the subfactorial of n, or the nth d arrangement number, or also the nth d Montemort number. This, no one will ask you this, but for the sake of completeness, it is also called the nth d Montemort number. Okay, it is denoted by dn, or the basically nth d factorial d arrangement number, or the subfactorial of n. Okay, so these are the notations. So now this is the formula. We will try to derive this formula. We already have derived it for 3. Okay, we have already derived it for 3 objects. We know that the answer is 2. Now we want to derive it for general n objects in n places, right? So let's say now we have four objects. So just to give you an idea, let's say we have 4 objects. Again, we will have 4 sets. This is like cover number 1, cover number 2, cover number 3, cover number 4, and we have 4 objects 1, 2, 3, 4. Set S1 is what? 1 goes in the correct cover. Set S2 is what? 2 goes in the correct cover. Set S3, 3 goes in the correct cover. And set S4, 4 goes in the correct cover. So permutation wise, like how we will solve this using inclusion exclusion, there are 4 factorial total ways. Minus S1 minus S2 minus S3 minus S4, all of them will be same. So 4 times the cardinality of any one of them, plus again, now what will happen, S1 S2, we will have to add S1 S2, S2 S3, S3 S4. So basically this becomes 4 factorial minus 4C1, because we have to make any one condition true, one at a time. So 4C1 times cardinality of any one of them, plus now we have to do 4C2 times, which means we are taking 2 at a time. S1 S2 are true, S1 S3 are true, S1 S4, S2 S3, S3 S4, so there are 6. So 4C2 times cardinality of 2 of them being true. Basically 1 goes in 1 and 2 goes in 2. So this is like cardinality of S12. You can write it S12 minus 4C3 times minus plus minus, inclusion exclusion, right? Now cardinality of 3 of them being true, and plus 4C4 times cardinality of all 4, right? So what it will be? 4 factorial minus 4C1 times, what is the cardinality of any one of them, which means that 1 goes in cover 1 and the other 3 can be arranged in 3 factorial ways. So 3 factorial plus 4C2 times, now 2 of them are true, which means 1 goes in 1 and 2 goes in 2, right? So other 2 can be arranged in 2 factorial ways, right? Minus 4C3 times, 3 conditions are true at a time, which means 1 goes in 1, 2 goes in 2 and 3 goes in 3. Now other 1 can be arranged in 1 factorial way, and plus 4C4 times, all the conditions are true, which means now we have to arrange 0 objects only, which means 0 factorial is also 1, only one way. So this is your answer, right? Okay, so I will try to expand it. Okay, I will try to expand it, that way it will be simpler. So we will try to pull out a few things. We want to get a closed compact notation. So I will try to get a compact notation for 4 first, then we will do it for n. So what this will become, 4 factorial minus, what is 4C1? N factorial upon n minus r factorial, 4 factorial upon 3 factorial, 1 factorial times 3 factorial, plus what is 4C2? I am just expanding NCR, n minus r factorial times 2 factorial, minus 4C3 is 4 factorial upon n minus r factorial times 1 factorial, plus what is 4C4? 4 factorial upon n minus r factorial times 0 factorial, right? So always this and this will cancel, this and this will cancel, this and this will cancel, this and this will cancel. 0 factorial is 1 only anyways. So what will this become? You can take 4 factorial out. If you take 4 factorial out, you will get 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. This is the expression, right? And this is the expression which is written here as well for n. I will solve it for n as well, but yeah, this is the expression. So 4 factorial times 1 minus 1, so this, okay? So yeah, you can calculate it as well. This will come out to be, so these two will cancel out, 1 minus 1. So this becomes 4 factorial upon 2, 24 upon 2 minus 24 upon 3 factorial, 3 factorial is 6 plus 24 upon 4 factorial, which is 24 only. So this will become 12 minus 4 plus 1, which is 9. Okay. So this is the fourth, this is subfactorial 4. By definition now this becomes subfactorial 4, which is 9. This expression entirely was subfactorial 4 only, right? We say that the fourth rearrangement number is subfactorial 4, which is 9. So we calculated subfactorial of 3 as 2 and subfactorial of 4 is 9. Okay, now how do we do it for n objects? Very simple, right? Again, use the inclusion exclusion, same way. Now we have n objects and n cover letters. So we will create n sets. 1 goes in 1, second is 2 goes in 2, and so on. Nth set is n goes in n. Nth letter goes in nth cover. So how many ways can we do this? Total number of ways is n factorial minus one of the condition is true, which means n conditions. nc 1 times one of the conditions is true. Let's say first is true. So 1 goes in cover 1. So the remaining n minus 1 can be arranged in n minus 1 factorial ways. Plus nc2 into, it will come out to be n minus 2 factorial, because 2 conditions are true, remaining n minus 2 can be arranged in these many ways. Plus minus so on. And the last term will be minus 1 to the power something ncn times 0 factorial, n minus n factorial. Right? All the conditions are true. So minus 1 to the power will be what? See, for 1 it is negative. I always told you like how to calculate the minus 1 to the power. Just see the pattern. For 1 it is minus. For 2 it is plus. So for I basically it is minus 1 to the power I. Right? So for n it will be minus 1 to the power n. Right? So plus minus 1 to the power n, ncn 0 factorial. Now we have to expand it. N factorial minus nc1 is what? N factorial upon n minus 1 factorial 1 factorial times n minus 1 factorial plus nc2 is what? N factorial upon n minus 2 factorial 2 factorial n minus 2 factorial minus so on plus minus 1 to the power n. ncn is what? N factorial upon 0 factorial n factorial times 0 factorial. Now this cancels, this cancels, this cancels, and we can take n factorial out. This is like, we are calculating subfactorial n only here, right? So we can take n factorial out. This will become 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on, plus minus 1 to the power n by n factorial. Okay, so it's like alternate terms, 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on up to n. Okay, and this entire expression, okay, I will get there. But yeah, this is subfactorial of n. This is subfactorial of n. This is the nth subfactorial number. Cool. You have to calculate it sometimes, like it might be tedious. There is no very compact notation. There is a long notation only. So let's say you have to calculate the subfactorial of 10. You have to do 10 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial up to 1 by 10 factorial. But there is an easy way to do that as well. I will tell you how. But yeah, this is the nth subfactorial number or the nth dearrangement number. Okay. This is the formula. Okay, this is the same formula. Okay, just written in summation notation. The same formula, but written in summation notation. So you can put I equal to 0. You will get this. I equal to 1, 2, 3. Okay. So this is the formula. Now, there is a quick observation. So what is the observation? Let's say I want to calculate subfactorial 10. It will be a very tedious process, right? What is subfactorial 10? The number of dearrangements of 10 numbers. It will be 10 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial and so on. Plus at the end we will have plus 1 by 10 factorial. Right? See, what happens is calculating this will be very difficult, right? Very huge numbers. So it will take a lot of time. But there is an easy way to do this. How? What we can do we can make it an infinite series. See, we have plus 1 by 10 factorial here. But it doesn't matter. We can actually have minus 1 by 11 factorial plus, if I add this, plus 1 by 12 factorial minus 1 by 13 factorial and so on up to infinity. Will it change it a lot? See, these terms, I have added this entire term. This term is very small. How? What is 1 by 11 factorial? Think about it. What is 1 by 11 factorial? It is a very small number, right? And think about it, like 11 factorial. 10 factorial is 3628800. This is 10 factorial. And 11 factorial is 11 times this. And you have 1 by 11 factorial. Right? It will be a very small number. And similarly, you subtract a very small number, you add a very small number and so on. This entire term will be a very small number. It doesn't matter, right? It won't even matter. So generally what happens is, after 6th or 7th dearrangement number, the terms after that will be very small, almost negligible. You can actually add it. It won't change the answer very much. So what we can say it, if I add this, the subfactorial of 10, I can basically say that the subfactorial of 10 is approximately very closely equal to this entire thing. I have not stopped here. Ideally I should have stopped here, but I am not stopping here. I am adding this entire term as well. Okay. Why? Because this entire term is very small. It won't change the answer very much. But why am I adding this? See, I am adding this because this entire series is nothing but 1 by e. Okay, this is the expansion of 1 by e. E is 2.7 something, right? Like, so this entire expression is 1 by e only. So that way I can solve it much easier, right? I just have to calculate 10 factorial upon e. And I am very sure that subfactorial of 10, see, this won't be the exact answer. Ideally, the answer will be an integer. This won't be an integer, right? E is an irrational number. How can this be this can never be a rational number. This will be an irrational number. Since like the numerator is rational and the denominator is irrational, right? This will be an irrational number, but it will be very closely equal to subfactorial of 10. See, we cannot do it for 3 subfactorial of 3. Because subfactorial of 3 will be factorial 3 times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. Right? I cannot add the other terms here. Because here the difference will be large. Because we are adding larger terms, 1 by 4 factorial. 1 by 4 factorial is very larger as compared to 1 by 10 factorial. Right? So here adding it will have a so you cannot say that subfactorial of 3 is approximately equal to 3 factorial upon e. It will be, but the difference will be large. But once you go to higher numbers, let's say you want to calculate the number of dearrangements of, basically after 5 or 6, this theorem will be okay. You can apply it. So if you have to calculate the 7th dearrangement number, you can just directly calculate 7 factorial upon e in your calculator. So you'll get a scientific calculator. Directly you can calculate 7 factorial upon E, and the 7th dearrangement number will be very close to that number. Okay. Even you can open the scientific calculator and do this. So like if you want to do practice always, like in the exam you will get. So what you can do is, while doing practice, you can search for TCS scientific calculator. Okay, this is the calculator that you get in your exam, right? So if you want to calculate subfactorial of 7, this is the exact calculator that you will get in exam, right? So you just do 7, they have everything. You just do 7 factorial, there is factorial as well. Yeah. 7 factorial upon E. There will be E as well. E. E is 2.71, okay. So you're getting 1854.112. Then definitely the subfactorial of 7 is 1854. Okay, it is very approximately equal to. Generally they won't ask you, like even if this question comes, they won't ask you, like the range of the numbers will be very like far away. So you can always select 1854. And actually like the subfactorial of 7 will be 1854. I can prove that. See, what is subfactorial of 7? It is 7 factorial times 7 factorial times 1 minus 1 factorial. We can cancel that term. 1 minus 1 factorial is 0. So now plus 1 by 2 factorial. So it will become 7 factorial upon 2 factorial minus 7 factorial upon 3 factorial plus 7 factorial upon 4 factorial, right? Plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial. So minus 7 factorial upon, so actually it is, it will take up all the space. I don't think you will be, yeah, it is there, okay. So plus factorial 7 upon 4 factorial minus 7 factorial upon 5 factorial plus 7 factorial upon 6 factorial. See, that way it is like a huge expression, right? Just to even write it. Plus this minus 7 factorial upon 7 factorial, which is minus 1 only. So I can do minus 1. 1854, okay? So the 7 factor, subfactorial 7 is 1854, which is like, that's what we get when we do 7 factorial upon E also. So that's an approximate value, okay? That's an approximate value of subfactorial of n. So for large n, I can write it for large n. Large means like above 7, above 6, 7. For large n, subfactorial of n is equal to n factorial upon e. That's all. That's what is mentioned here. If limit n tends to infinity, subfactorial upon n factorial becomes 1 by e. So what does it mean? What does it mean? What does this expression mean? It means that what we got? We got subfactorial of n is n factorial upon e, right? And 1 by e is approximately 0.367. 1 by e is approximately 0.367. It means that subfactorial of n for a large n is approximately equal to 0.367 times factorial n. This is the number of dearrangements. This is the number of arrangements. This is the number of dearrangements. This is the number of arrangements. It means that approximately 36.7% arrangements are dearrangements in general. This is a very small number, right? There are only 37% arrangements in which none of the objects are in the correct place. Think about it. In long term, let's say for 10 objects, there will be 3628800 permutations, right? Very huge. But approximately only 36% of them will be such that none of the objects are in the correct place. That's what this means, okay? So we can write this statement: approximately 36.8% arrangements are dearrangements for a bigger n, for n greater than 7, 8. Okay. Cool. So again, like very easy question, number of rearrangements of 1, 2, 3, 4. And this can be framed like this as well. Number of ways in which a teacher can give 4 students assignments if none of them gets to get their own assignment. Okay. Number of rearrangements of 4 is what? Subfactorial 4 is 4 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. We already calculated it, right? It was 9. It is 6 actually. Okay, so we might have made a little mistake. The value will come out to be 6. So let me do it again. Okay, so that 1 minus 1 factorial gets cancelled. It becomes 24 by 2 minus 24 by 6 plus 24 by 24. So it becomes 12 minus 4 plus 1. It's 9 only, right? It's 9 only. Okay, so here it is a mistake. Cool? Cool. So in how many ways can we arrange 1, 2, 3, 4, 5, 6 in such a way that no even integer is in its original position? See, now here this is not standard dearrangement. Here it is not standard dearrangement. Here what they are saying is there are 6 places, 1, 2, 3, 4, 5 and 6. And we have to arrange these 6 objects, 1, 2, 3, 4, 5, 6, such that only no even integer is in the correct position. So basically 2 should not go here, 4 should not go here and 6 should not go here. We don't care about other numbers, but only even integers should not go in the correct places. So here this is not standard dearrangement. We have to apply inclusion exclusion only. So let's say the set S1 is 2 goes in the cover 2, S2 is 4 goes in the cover 4 and S3 is 6 goes in the cover 6. That way we have to solve it. So what is the total number of arrangements? It is 6 factorial minus now 3 times any one of them is true, right? S1 minus S1 minus S2 minus S3, like all of them are symmetrical, so that's why 3 times. Let's say 2 goes in cover 2. So in how many ways can I arrange the remaining 5? 5 factorial. Plus, now two of the conditions are true, S1 and S2 both. So again S1, S2, S2, S3, S1, S3. So 3 times. Now 2 goes in 2 and 4 goes in 4. In how many ways can I arrange the remaining 4? 4 factorial. Minus, all the 3 conditions are true. If all the 3 conditions are true, the remaining 3 can be arranged in 3 factorial ways. So this is your answer, you can calculate it, okay? This will come out to be 426. Cool. So there are 426 ways. So now if such a question comes, you cannot apply the direct dearrangement formula because there is a specific demand. You have to apply the inclusion exclusion principle and solve it. Cool. So this is what dearrangements are. And this concludes all the basic elements of counting. Okay. So like whatever we have seen, inclusion exclusion, binomial, multinomial, theorem, cyclic arrangements, combination with repetition, very important, and dearrangement. There are a few advanced topics as well, like group polynomial and like there are a few advanced topics. They are like not exactly required for GATE syllabus, but later I will whenever we get time, I'll upload a few videos on that as well. If you have time, you can see them. But yeah, like for GATE syllabus, this is what we have discussed. This is enough, okay? And generally questions will come from here only. Cool. So now we will start in probability and statistics, counting is over. So we will start the elements of probability next. Hi everyone. So welcome to GATE Data Science course. We have finished counting and we will start probability. So in probability, statistics and GATE syllabus, there are various like modules, counting, probability. In the statistics, there are like random variables and stuff. So I will break down all the components, the entire subject into different modules, and this is the second module of called probability. Okay, and so this is lecture number 1, and we will discuss the basic elements of probability in this lecture, like sample event, sample space, and the different basic axioms of probability. If you have already learned it in you must have learned it in class 10th, 11th, 12th. Okay, so most of the concepts will be same, at least in this lecture. Okay, and then we will move to like advanced topics like Bayes theorem, multiplication theorem, and so on. Cool. So firstly, why probability? Why? Because we cannot be sure of certain of outcomes of certain events, right? So what is an event? So basically, whenever you call an event in terms of probability, you will have a universe. So basically, you will be doing an experiment. So the universe won't be the entire universe. For you, for that particular question, for that particular event, the universe will be very confined. For example, you are throwing a die. So when throwing a dice, this is an event, this is an experiment that you're performing. So your universe is confined only to that dice right now. Don't focus on any other thing. You have that universe. That's why we call it universe. Okay, for that experiment, we don't care about any other stuff happening. We just care about what happens when I roll a dice. Right? So what is the universe here? You can get a number, right? When you roll a die, it will land somewhere and you will get a number. That is your universe. Okay, so you can get only 6 different options because dice has 6 sides. You can only have 6 different outcomes: 1, 2, 3, 4, 5, and 6. Right? So for that experiment, this becomes your universe. You will get 1, 2, 3, 4, 5, or 6. Right? So this is the universe. And now what is an event? So for an experiment, you define certain events. Let's say for me, for this particular experiment, the event is I want to get a prime number when I roll a die. So getting a prime number now becomes an event. It can happen or it might not happen, right? You're not certain that it will happen. So basically that's where probability comes in. When you're rolling a die, you're not certain a prime number will come or not, right? So what are the prime numbers in 1, 2, 3, 4, 5, 6, 2 and 3, right? So if 2 and 3 comes, your event becomes successful. If 2 and 3 doesn't come, your event becomes a failure. So the notion of probability is how many times do I have to roll in general so that I get a prime number? Or what is basically the probability? That's what probability is, right? What is the probability of getting a prime number? It means that if you roll a die n number of times, infinite number of times, a very large number of times, let's say I roll the dice 1 million times. Generally speaking, I will get like 2 by 6 times of 1 million. That's the number. Like you will get that many times, you'll get a prime number. That's probability, right? So this is also called the frequency interpretation of probability. It means that in general, when you perform an experiment, if you perform an experiment very large number of times, the ratio of number of times your experiment becomes successful, the ratio of the number of times your experiment becomes successful is called the probability of the event. You don't have to roll it 1 or 2 times, right? If you only roll it 1 or 2 times, let's say you roll it only 1 time and you didn't get a prime number. You cannot say that the probability is 0, right? You will get in long term. That's what frequency interpretation says. In long term, if you perform the experiment on a very large sample or like a very large number of times, generally speaking, then the ratio, like let's say you performed the experiment 6,000 times and you got succeeded 2,000 times, right? In long term, then your probability becomes 2 by 6, right? Very large number of times. Generally speaking, it should be infinity, right? But we have to stop somewhere. So if you perform an experiment very large number of times, then the ratio of your success is called the probability of the event. So consider an experiment. Experiment is our universe whose outcome is not predictable. We don't know what will happen when performing an experiment. We don't know. It's not predictable with certainty in advance. Although the outcome of the experiment will not be known in advance. Okay? So what will happen, we don't know. The outcome is not known. Now let us suppose that the set of all possible outcomes is known. We will know the set of all possible outcomes. For example, when we roll a die, we know that the set of all possible outcomes is 1, 2, 3, 4, 5, 6. This is my universe. This is a set of all possible outcomes that can happen. Now, this set of all possible outcomes of an experiment is known as the sample space. This is called the sample space of the experiment. Okay? And is denoted by S. So, this is my sample space of the experiment. And this kind of experiment is called a random experiment. It is random in nature, right? We don't know what will happen. It is random. Now, any subset E of the sample space is known as an event. So, any subset, like for example, I told you prime numbers. It is a subset 2, 3. right? So any subset of the larger set or the sample space is called an event, and it is a set consisting of possible outcomes for the experiment. If the outcome of the experiment is contained in E, then we say that E has occurred. So basically when you do an experiment and the outcome is in E, then we say that event E has occurred, or the event E has resulted in success. Otherwise it is a failure. Okay, I hope you get this. Very basic concept. So like few examples like boy or girl, like generally speaking, the probability of getting a boy or girl is 0.5. So in a large population, this should happen, right? So like you don't know it will be random, and let's say you're having 3 kids, and like questions might come like if you're having 3 kids, what is the universe? So you can have 3 boys, 2 boys, 1 girl, and so on. This is your universe. So and the event can be one of them. Like what is the probability of getting all 3 girls, right? So that's what an event is, and you can calculate probability of that. And rolling a die we have already seen, and you can also roll 2 dice. So these are a few experiments that can be done like in probability, and we will see a lot of experiments during this course. Like we will see a lot more complicated events as well. Cool. Now we will see some elements of probability. Since everything is related to sets, right? This is a set. Everything is related to a set in probability. Like the entire universe is also a set, which is called the sample space. And an event is a subset of the sample space. So now there are a few notations of which are very common. Like these are very common notations known to union like set theory. Okay. So first one is union. For any 2 events E and F of a sample space S, we define the new event E union F. Now E is an event, F is an event, E union F is also an event, which will say that E or F is occurring. Either E or F or both. Anything can happen, right? So let's say again, like you have a sample space of rolling a die, 1, 2, 3, 4, 5, 6. Let's say E is the event of getting a prime number, and let's say F is the event of getting an odd number. Then E union F will be what? Getting a prime number or an odd number. So it's like 1, 2, 3 and 5. Okay. So the E union F is called the union of events E and F, and it consists of all outcomes that are either in E or in F or in both E and F. So that's what we did. Just take all the elements in E and F both. So now there is a notion of collectively exhaustive events. Exhaustive means what? So let's say there are 2 events E and F. In rolling a die, let's say one event is getting a even number or odd number. Okay, and another event is getting an even number. Now what happens is their union is actually the entire sample space. If you see, either you will get an odd number or an even number. So first event was odd, second event was even. If you take the union, you will get the entire sample space. In the union, you will get the entire sample space, right? So what happens? We say that these 2 events E and F are collectively exhaustive. Basically, they exhaust all possibilities which can happen in this experiment. Either one of this experiment will definitely happen. Okay, so their union must cover all the events within the entire sample space. So if E union F is S, we say that E and F are collectively exhaustive. Okay, the next concept is intersection. Very simple again. So like again, you can always create Venn diagram and see, right? This is the event E, this is the event F, this is E union F, and the middle region is E intersection F, right? Which is like E and F both. So for any 2 events E and F, we can also define the new event E intersection F, called the intersection of E and F, to consist of all outcomes that are in both E and F. So again, let's say like E is the event of getting a prime number, and F is the event of getting an odd number. Then E intersection F is what? there is only one element common, right? 3. Getting both prime and odd. Getting both. Okay, sorry, I made a mistake. 5 is also prime here. I should have written 5 as well. Okay, 2, 3 and 5 all are prime. So, yep. Here also you can do this. But here the union will remain same, so it doesn't matter. In union also you should write prime. Okay, 5 is also prime. Cool. So the union remains same, 1, 2, 3, 5. And in intersection, what will happen? Yep. So the event E is getting a prime number 2, 3 or 5. Event F is getting an odd number 1, 3 or 5. What is the intersection of these two? Getting either 3 or 5. Right? Because 3 and 5 are both odd and prime. So, yep, this is called intersection, and it is like saying that both events E and F occur simultaneously. Both are happening. Cool. Here also, like, you should add 5. I said that prime number, right? So in the first slide, okay, you can correct it. Cool. Now there is a notion of mutually exclusive events. We saw collectively exhaustive events. Now there is a notion of mutually exclusive events. What does it mean? Ki two events have nothing in common. That's what exclusive events are. Let's say the event E is getting an odd number. Again, right, see, these two events same. These two events were exhaustive and they are exclusive as well. So how? Let's say E is getting an odd number. F is getting an even number. Now what happens? What is the intersection of these two sets? What is the intersection of these two sets? Nothing. The empty set. There is nothing in common in both these sets, right? So the intersection is phi, or the empty set. So it implies that E and F cannot both occur simultaneously. They cannot occur simultaneously. Then E and F are said to be mutually exclusive events. Okay? Exhaustive, which means that it can be extended to 3-4 sets as well. Let's say 4 events A, B, C, D are exclusive if A intersection B intersection C intersection D is phi, and they are exhaustive if A union B union C union D is S, or the sample space. Cool. The next element is complement. So for any event E, we define the event E complement, and it is called the complement of E to consist of all the outcomes in the space that are not in E. So if this is the universe, 1, 2, 3, 4, 5, 6, and if E is your event getting a prime number 2, 3 or 5, then what will be E composite? It will be 1, 4 or 6. It is like getting the composite numbers. Okay, it is called the complement event. If you're not getting a prime, you're getting a composite number. So that this is what complement is. Then similarly, you have the concept of subsets. So for any two events E and F, if all the outcomes in E are also in F, if all the outcomes of E are also in F, so basically E is a subset of F, right? So what happens? For we can take an example here. Let's say the event E is getting 2 or 3. Let's say the event F is getting 2, 3 or 5. So here what happens? Event E is a subset of F. All the outcomes of E are in F as well. Okay, so we denote it as this, and it says that the occurrence of E necessarily implies that the occurrence of F. So what happens here? If E happens, what does it mean? If 2 or 3 are coming, like if you are either getting a 2 or 3 while rolling a die. So if E happens, F definitely happens, right? Because F says that you should get it 2, 3 or 5. If you're getting a 2 or 3, you are getting a 2, 3 or 5, right? So if E is subset of F, if E happens, F happens. And similarly, if E is a subset of, an event E is a subset of F, and F is also a subset of E, then it will mean that both the sets are actually equal. They are identical. These two events are identical. Okay. So this is like using the Venn diagram showing the same thing. So this is the shaded region here is E union F. Here the shaded region is E intersection F. E intersection F is sometimes written like this as well, EF. Okay, it is E intersection F only. And here the shaded region is E complement. If this is E, this is E complement. Okay. And then we have a few laws as well here. So first is commutative law. These laws are standard in set theory and probability. Okay. So E union F will be equal to F union E. So the union of two sets is commutative. You can do E union F or F union E. It doesn't matter. Then you have the associative law. It means that E union F union G is equal to E union F union G. So when you're doing union, you're anyways taking all the elements in all the sets, right? So it doesn't matter which two sets are you do union first, right? It doesn't matter. You can do E union F or you can do F union G. It doesn't matter. It is associative. And then we have the distributive law. It says that E union F intersection G is E intersection G union F intersection G. It is very easy to see using a Venn diagram. So let's say this is E, F and G. Now it is saying that E union F intersection G. See, E union F is this entire set. And we have to take whatever element which are present in G also. So this area basically. This area is in E union F and it is intersects with G as well. Right? And what is RHS? RHS is E intersection G union F intersection G. So what is E intersection G? E intersection G is this area and F intersection G is this area. And their union is the same area. Okay. So the distributive law also holds in probability, in set theory and in probability. Okay. Now we have a few more Venn diagrams. So here we have Venn diagrams of three sets. The shaded region here is common in E and G, so it is EG or E intersection G. Here the shaded region is F intersection G, and here the shaded region is. So it's like proving the same theorem, right? The distributive law which we saw. It's proving the distributive law only. It's drawing the same diagram. Now we have another axiom. What is the complement of E union F? What is the complement of E union F? So again we can draw the Venn diagram. This is E, this is F. The complement of E union F is all the outside area, right? This is E, this is F. The complement E union F is this area. And whatever outside it is E union F complement. So it will be E complement intersection F complement. Basically, whatever. So basically, like, see, you can tell it in English as well, right? E union F is what? E union F is E or F. Something is happening. The complement of it is what? Nothing is happening. Neither E nor F is happening. That's what it is. Neither E and nor F. So basically, E should not happen and F should not happen. Similarly here, what is E intersection F? E and F both happen. E and F both happen simultaneously. What is the complement of that? Ki E and F should not happen both simultaneously. Other than that, everything can happen, right? Only E can happen, only F can happen, none of them can happen. And what is this set? Either E doesn't happen or F doesn't happen, right? Which is correct. What I'm trying to say is, what is E intersection F complement? It is like E and F should not happen simultaneously. It means that either one of them should not happen. That's what RHS is. Either E is not happening or F is not happening, right? Using Venn diagram also you can prove it very easily. Cool. So now we have some axioms of probability. They are standard axioms. Probability of any event can always be between 0 and 1. If you're getting a probability of greater than 1, you are making a mistake. It is not possible. Probability is what, like the ratio I told you of in long term. If you perform an experiment million times, in how many times your event is successful? If you're performing an experiment million times, your experiment cannot be successful 2 million times, right? It can be between 0 and million. So the ratio can only be between 0 and 1. The probability of sample space is 1. You will always have the sample space. That's why it is called sample space. Sample space is what? The universe. Something within the sample space will always happen. So the probability of happening of sample space is 1, right? Now there is an axiom for any sequence of mutually exclusive events, even E2. Let's say we have a few events which are mutually exclusive. It means that all 2 of them are exclusive. They have nothing in common. It means that they are like this: E1, E2, E3, E4, En. They have nothing in common. They are exclusive events. So we have a sequence of exclusive events. So what will happen here? So the probability of happening of E1 union E2 union E3 union E4 union E5 will be nothing but the sum of individual probabilities. So probability of happening of E1. So basically you can firstly see it for 2 sets. It will be easier. If you have only 2 sets E and F, the probability of union will be probability of E plus probability of F, which is same as cardinality in sets, right? It is same as cardinality in sets. The cardinality of E union F will be cardinality of E plus cardinality of F. So same happens with probability as well. Okay. So there are a few propositions. Probability of E complement will be 1 minus probability of E. So why? Because we know that E complement is nothing but universe or the sample space, sample space minus E. So the probability of E complement will be probability of sample space minus probability of E, which is 1 minus probability of E. Okay. So basically the probability of getting a prime number when we throw a die is what? So the prime number event is what? 2, 3 and 5. This is getting a prime number. Okay, so the probability of E is what? There are 3 cases in which we succeed and there are total 6 cases, right? So the probability of event E is 3 by 6 or 1 by 2. Right, the probability of event E is what? The cardinality of E upon the cardinality of sample space, which is 3 by 6, which is 1 by 2. So in 50% cases your event will be true. So what is the probability of E complement? Probability of getting composite numbers. So it will become 1 minus 1 by 2, which is 1 by 2 again. Okay. And this is the most important law. Okay, this we have seen in, this is standard inclusion exclusion, right? So what happens? If you have 2 events, E and F, and they are not exclusive, they can have something in common. Then the probability of E union F, we have seen this in set theory as well, right? And also in counting, in counting when we did inclusion exclusion, we saw this. So the probability of E union F will be probability of E plus probability of F. So either E can happen or F can happen. But when we do this, we are overcounting these elements. We are counting them twice. So you have to subtract them once. So it is probability of E intersection F minus probability of E intersection F. Okay. Cool. So let's see an example. A total of 30% American males smoke cigarettes, 10% smoke cigars, and 5% smoke both cigars and cigarettes. What percentage of males smoke neither cigars nor cigarettes? Okay. So there are 2 types of population given. 30% smoke cigarettes. So let's say cigarette is a longer word. Let's say I call them set A and B. And 30% smoke cigarettes and 10% smoke cigars. Okay, and they have said that 5% smoke both. This area is 5%. What does it mean? So the A union B will become 30% plus 10% minus 5%. Okay, A plus B minus A intersection B. It means 45%. No, 35%. So there are 35% people who smoke cigarette or cigar. Union. Now what we want? Neither cigar nor cigarette. None of them, which means the outer set. Basically we want this outer set. So it is basically union, the sample space minus A union B. Sample space is 100% minus 35%. So that's our answer. So total of 65%. And total of 65% people won't smoke cigar or cigarettes. Cool. So there is another concept, a beautiful concept, I would say, in probability. It's called odds in favor and odds in against. These terms are generally used in betting. Like if you have seen it, what are odds in favor of happening of an event? Okay, that's a standard term. So odds in favor of a particular event is given by the number of favorable outcomes to the number of unfavorable outcomes. Very simple. Like see the formula. So the odds in favor of an event A, is defined to be probability of A upon probability of A complement. So again, like let's take an easy example. Let's say our sample space is 1, 2, 3, 4, 5, 6 dice, rolling a dice. And my event E is getting a 2 or a 3. We know that probability of happening of event E is what? Cardinality of E upon cardinality of S, which means there are 2 elements here upon 6 elements here, which is 1 by 3. The probability of event E is 1 by 3. Similarly, probability of E complement will be what? Probability of not happening of E, which means 2 and 3 don't come, which means 1, 4, 5 or 6 come, which means 4 by 6. Or you can directly use formula, it will be 1 minus 1 by 3, which is 2 by 3. Right? So we say that probability of E is 1 by 3, probability of not happening of E is 2 by 3, and odds in favor of E. Odds in favor of E is what? Probability of happening of E upon probability of not happening of E. Which is 1 by 2. So we generally denote it as 1:2, 1 by 2, right? So odds in favor of E is 1:2. It means that generally speaking, 1 times it passes and 2 times it fails. That's what odds in favor mean. In a long term, if 1 time if the event happens, 2 times it doesn't happen. That's what it means, right? Probability of E upon probability of not happening of E. So the odds in favor of E is 1:2. And similarly, the odds against is the reversal of it. Probability of A complement upon probability of A. So the odds against event E is what? Odds against E is the reversal of this, so it will become 2 by 1. 2:1. So odds against is what? Generally speaking, it fails 2 times and passes 1 time. So it's just the opposite. These are just common notations. So we can solve an example. Find the odds in favor and odds in against of throwing a die and getting 3 dots. So the sample space is 1, 2, 3, 4, 5, 6. And the event is getting just 3 dots. This is the event. So probability of E is 1 by 6. Probability of E complement is 5 by 6. The odds in favor of E is what? Probability of E upon probability of E complement, which is 1 by 6 upon 5 by 6, which is 1:5. Similarly, odds in against will be reversal. So odds in against of E is 5:1. So generally speaking, this experiment passes 1 time and fails 5 times. Okay. There is another question. If odds in favor of Rahul solving a problem are 4-3 and odds against Himanshu solving the problem is 2-6, then what is the probability of Rahul? Okay, so like the event is Rahul solving problem. Let's say the event E is Rahul solving the problem. And let's say the event F is Himanshu solving the problem. Okay, so what they have said that they have said ki odds in favor of Rahul solving a problem is 4-3, which means that odds in favor of E are given. Odds in favor of E is given to be 4:3. We know that this is probability of E upon probability of E complement. Right? And we know that probability of E complement is 1 minus probability of E. So this is like one equation in one unknown. We can solve it. So if we just pull this here, it will become 4 minus 4 times probability of E is equals 3 times probability of E. Right? I'm just taking 1 minus PE here and 3 here. So this becomes 7 times probability of E is 4. It means probability of happening of E is 4/7. So probability of Rahul solving the problem is 4/7. And the second part is the odds against Himanshu solving the problem. It means that probability of F complement upon probability of F, odds against, which means the reversal, is given to be 2-6. It means that, so you can bring 6 here. This is nothing but 1 minus PF. So it will become 6 minus 6 times PF equals 2 times probability of F. So it means that probability of F becomes 6/8, which is 3/4. So there are 75% chances that Himanshu can solve the problem. Okay. So I'm just using the standard formula and calculating the probabilities. Okay, there is this one question which has been asked in GATE Computer Science, actually 2013. So out of all the 2-digit integers between 1 and 100, out of all the 2-digit integers between 1 and 100, a 2-digit number has to be selected at random. What is the probability that the selected number is not divisible by 7? Okay, so how many 2-digit numbers are there between 1 and 100? They start from 11, 12, up to they go to 99. Okay, and so this is our sample space. Getting a number 11, 12. Okay, they start at 10 actually. They start at 10, right? 10 is also a 2-digit number. So our sample space is 10, 11, 12, up to 99. So how many numbers are there here? The cardinality of S is what? 99 minus 10 plus 1. Right? Whenever you have inclusive sets and continuous, the cardinality will become 99 minus 10 plus 1. 90. Okay, there are 90 elements, 10, 11, 12 up to 99. And the event E is, so let's say we want to find the probability of getting a number which is not divisible by 7. So the better event to consider will be to get an event which is divisible by 7. That is smaller event, right? So I'm calculating the probability of a smaller event because that's easier to calculate. So let's say the event E is the number will be divisible by 7. Then I will just take the complement. Divisible by 7. So how many numbers in this sample space are divisible by 7? They start at, so 7 is not there. So 14, 21, 28 and so on. Okay, so what will be the last number? 98 will be the last number. 98 is also divisible by 7, right? Okay. So what is the cardinality of this set? It's very easy to calculate. See, up to 100, the number of integers which are divisible by 7 will be 100 by 7 floor. So it will be 14. There are 14 integers from 1 to 100 which are divisible by 7. Because 14 times 7 is 98. And we have to remove 1. We have to remove 1 because 7 is not there. 7 is not in the sample space. So there are 13 numbers. So the cardinality of this set is 13. Okay. Now what we want, what is the probability that the selected number is not divisible by 7? So we see that probability of event E is 13 by 90. what we want? We want the reversal, like we want the complement. Probability of E complement will be 1 minus 13 by 90, which is 90 minus 13 is 77. 77 over 90. Okay. So this is it. So these are all the basic elements of probability. We saw what a sample space is, what event is, how to calculate the probability, odds in favor, odds in against, and a few axioms and union intersection. Okay, these are all basics in probability. And now we will discuss more complicated stuff like conditional probability, multiplication theorem, and so on. Hi everyone, welcome to lecture number 2 of probability. We are doing GATE Data Science and AI course. So in this lecture, we will see a new concept called conditional probability. In the last lecture, we have seen some basics of probability, axioms, how to calculate probability of a certain event. In this lecture, we will expand our knowledge to a slightly different concept, which is called conditional probability. Let's see. So we'll start with an example. Suppose that one rolls a pair of dice. Okay, if you're rolling a pair of dice, we know that the sample space consists of 36 outcomes. You can get 1 on both, 1 2, 1 3, and so on up to 6 6. Okay, so you have 36 possible outcomes. Okay, these are all 36 outcomes possible, right? So they can be written like this in set notation as well. All ordered pair I comma j, where I can be 1 2 3 4 5 6 and j can be 1 2 3 4 5 6. These are all possible 36 combinations or 36 possibilities we can have when we throw two dice together, right? This is our sample space or the universe. Now, what is the probability that the sum of the two dice equals 8? The sum is equal to 8. So you are given an event E. Sum is equal to 8. So what is the set? Okay, so you can have 2 comma 6. See, if you have 1 on the first die, you cannot have any number on the other, so that the sum is 8. 2 comma 6, 3 comma 5, 4 comma 4, 5 comma 3, and 6 comma 2. Right? These are the 5 possible cases which give you the sum as 8. So we know that the probability of event E will become cardinality of E upon cardinality of S. There are 5 outcomes out of 36, which gives you this. Okay, this we have seen. Now there is some other information given. This was standard probability. Okay. Now what makes a conditional probability is this. Suppose further that we observe that the first die lands on a side 3. This is a additional information given. The first die always lands on side 3, or not always, like for this experiment, they have said that the first die gave you 3. This is an additional information given. Now, given this information, what is the probability that the sum of the two dice equals 8? Now the problem becomes different, right? Previously, we have to solve the generic case in which we have thrown two dice. What is the probability that you will get a sum of 8? Now they have said that the first dice has given you a 3. This is a condition which is already given. So now, given this information, your sample space reduces. Always in conditional probability, when some condition is given, basically your sample space gets reduced. Given this information, what happens? Your sample space only becomes this: 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. Since the first dice has landed at 3, now your sample space is not the entire 36 elements, it's only this 6 elements. This is the updated sample space for your experiment now. Now what is the probability of getting a sum of 8? This is the only case which will give you a sum of 8, right? So the probability will become 1 by 6. See, observe that the probability is not 1 by 36. Since it is given that first die has landed in 3, your sample space is also reduced. The common mistake which people do here is, they say that the first die has given 3, so now the only combination possible is 3, 5. So they will do 1 by 36. You don't have 36 outcomes in sample space now. Since this observation is already given, that the first die landed in a 3, your sample space is now just 6 elements. And that's why the probability is only 1 by 6. Right? So given this information, the sample space reduced. So coming to notation, if we let E and F denote respectively the event that the sum of dice is 8 and the event that the first die is 3. So now we have a few events. E is the event that the sum is 8 and F is the event first die gives you a 3. First die lands in 3. Then the probability just obtained is called the conditional probability of E given F. The probability which we just calculated. The probability of getting a sum of 8 given that the first die landed in 3. It is called the conditional probability. Conditional probability of event E given that F has already happened. Conditional probability of event E given that event F has already happened. Right? It is denoted by P E by F. So if the event F occurs, it is sure that F has occurred. Then in order for E to occur, then is necessary that the actual occurrence be a point in both E and F. Firstly, there should be some intersection. Right? In E and F, there is some intersection. The element 3, 5 was an intersection. Otherwise, like if F happened and there was no intersection in E, then the probability will be 0. Right? And we know that this intersection is called E intersection F. This intersection is called E intersection F. All the elements which are both in E and F. This is called E intersection F. Or you can call it EF as well. Now, since we know that F has occurred, it follows that F becomes our new reduced sample space. And that's why this is the new probability. So that's how we calculated it. See. In event E, the event E was what? Sum is 8. We know that there were 5 elements here. 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. There were 5 elements in set E. Sum is 8. What was event F? That the first die gives you a 3. So what is the sample space? What is the set F? What is the event F? 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. 6 elements. Right? Now, since it is given that F has already occurred, it is given that F has happened. Now your universe becomes this. Since it is given that F has happened, your universe becomes this. Your sample space becomes this. What it means that all the elements in E which are not in F are of no matter. They cannot happen now. Since F has happened, all the elements in E which are not in F, they can never happen. Since it is given that 3 happened in the first die, you cannot have 2, 6 at all. Right? So all these elements are useless. Only the elements which are also in F, they are useful. That's why we calculate E intersection F. The elements which are in both E and F. These are the only elements which can happen and they satisfy our condition. What is E intersection F? The only element is 3, 5. Right? So this is the only element. Now this is our new event probability. This is the event that we want to happen. This is not, previously this was the event that we wanted to happen, that probability of getting a sum of 8. But now this is the event that we want to happen, 3, 5. Right? And now since the universe became F, I told you, like since F has already happened, our universe or sample space became F. So that's why this condition probability of E given F has already happened becomes probability of E intersection F upon probability of F. Right? So we divide by P of F because F has already happened. That's why like we divide by this probability. Like this is our sample space now. Okay? So this is how condition probability is defined. Probability of E given F has already happened is probability of E intersection F upon P of F. Okay? Let's try to solve a few examples. So on rolling a die, what is the probability of getting a prime number given that an odd number showed up? Okay, so we will solve both using directly formula and using our naive way. So let's say E is the event of getting a prime number. What is the set? 2, 3, 5. And let's say F is the event of getting an odd number. Which what is the set? 1, 3, 5. So firstly, generally speaking, what is the probability of event E? The probability of event E is 3 by 6. So this is our original sample space. When you roll a die, the sample space is 1, 2, 3, 4, 5, 6. Right? Now, the probability of just happening of event E is what? Getting a prime number. The cardinality of E, 3 elements out of 6 elements, so 3 by 6, which is 1 by 2. Probability of just happening of event F, of getting an odd number, is also 3 by 6, which is 1 by 2, since it has also 3 elements. Now, but they have changed the question. They have said ki, given that odd number showed up, now this becomes our universe. Given that odd number shows up, this becomes our universe. Now this becomes our sample set. So what we want now, given that F has happened, what is the probability of E? So firstly, we will calculate E intersection F. Since F has already happened, 2 is of no matter. You will never get a 2. Since odd number showed up, only 3 and 5 might come up. Right? So that's why probability of event E, given F has already happened, is, now this is your set, event, and this is your sample space. So it becomes 2 by 3. You have 3 elements in sample space and 2 elements in the event, right? And formula wise also, what is the probability of E intersection F? What is the probability of E intersection F? E intersection F contains 2 elements. So 2 by 6, which is 1 by 3. So the formula wise, probability of E given F has already happened is probability of E intersection F given probability upon probability of F, which is 1 by 3 over 1 by 2, which is 2 by 3. Okay. So that's how you solve conditional probability. Now let's see another question. The experiment is rolling 2 die together. So the sample space contains 36 outcomes, 1, 1, 2, 1, 6, 1, 1, 2, 6, 6. There are 36 outcomes. Okay. Now an event E is given that both die showed an odd number. Both die showed an odd number. So there, like, what is the, how many elements will be there in E? Think about it. Both die showed an odd number, which means that E will be what? You can have 1, 1, both are odd. You can have 1, 3, you can have 1, 5, and you can have 3, 1, and so on. At the end, you will have 5, 5. Both die should have an odd number. So you have 3 odd numbers. So 3 into 3, there will be 9 elements. Since initially when you have 6 elements, you had 36 cases. Now you have only 3 elements. Only 135 can be on the first place, 135 can be on the second place. So there are 9 elements in the event E. And the event F is given to be sum of the numbers showed is 6. Sum of the numbers showed is 6. So what is this case? 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. These are the only 5 cases, 5 elements. Okay. There are 5 elements in set F. Now we want to calculate probability of E given F has already happened. So given that the event F has already happened, which means that it is given that the sum of the elements was 6. So now this becomes our universe. So we can use the formula directly. Okay, let's calculate E intersection F. E intersection F will be what? The elements which are common in both of them. So basically both the numbers should be odd here. So 1, 5 is one such case, 3, 3 is one such case, and 5, 1. This is our intersection set, 3 elements. Okay. So now probability of E given F has already happened is what?
probability of E intersection F upon probability of F. Probability of E intersection F is what? There are just 3 elements out of 36. And probability of F is what? There are 5 elements out of 36. So this becomes 3 by 5. And similarly, probability of F given E has already happened will become probability of F intersection E upon probability of E. Since intersection is commutative, you can like P of E intersection F intersection E intersection F is same. So this will become 3 by 36 upon probability of E. E has 9 elements, so 9 by 36. So this becomes 3 by 9 or 1 by 3. Okay, logically also if you see what is probability of F given E has already happened. Given that both numbers are odd, so there are only 9 such cases. Out of these 9 cases, how many have sum as 6? How many of them have sum as 6? So only 3 have sum as 6. 1, 2 and 3 out of these 9 elements, right? So that's why 3 by 9 or 1 by 3. So like logically also you can see, or you can use the formula. So this becomes 3 by 5 and this becomes 1 by 3. Okay. So now let's solve a question. A bin contains 3 defective. A bin contains 3 defective that are immediately fail when put in use. There are 3 defective, 5 partially defective and 10 acceptable transistors. There is a bin which contains 3 defective, 5 partially defective and 10 acceptable transistors. So there are 18 total transistors in a bin. Now a transistor is chosen at random from the bin and put into use. If it does not immediately fail, what is the probability that it is acceptable? So let's say there are 2 events. Event E is one event is it immediately fails. Immediately fails is not defective. See, immediately fails is defective only, right? In brackets. So probability. So let's say event E is the transistor is defective. And the event F is, we have another event in this question that it is acceptable. So see, all the like in any question, just make events, then it will be easier. Event E is, so it says that it does not immediately fail. So you can ignore the not right now. While creating events, don't worry about not, because when solving the question after events are created, we will just use complement, right? So they said that if it does not immediately fail, so we made one event as the transistor immediately fails, which means it is defective. And the other event is, we want to find the probability that it is acceptable. So the other event that we will create is that the transistor is acceptable. We know that there are 3 transistors which are defective. And we know that there are 10 transistors which are acceptable. And the size of sample space is 18. So it's very easy to find the probability of E and F. Probability of E is what? 3 by 18. Probability of F is what? 10 by 18. But that's not what you want. What you want, now read the question very carefully. Once you've created the event, the question will become very simple. See, given that the transistor that we pulled out is not immediately failed, does not immediately fail, it means that E complement happened. It does not immediately fail. It means that E complement happened. It means that it was not defective. It was either partially defective or it was acceptable. E complement happened, right? It was either partially defective or it was acceptable. Given that E complement happened, what is the probability that it is acceptable? So what we want to find is, just if you create this equation correctly, then your answer will be good. This is what we want. Given that the transistor was not defective, what is the probability that it is acceptable? So what it will be? It will be probability of F intersection E complement upon probability of E complement. Right? Now what is the probability of F intersection E complement? What is this set? F intersection E complement means what? That it is acceptable and it is not defective, which means it is either this partially acceptable or acceptable, right? That's what intersection is. No, sorry, what is F? It is acceptable. What is E complement? E complement is partially acceptable or acceptable. So E complement is partially acceptable or acceptable. F is what? Acceptable. So what will be their intersection? What is the common element? Acceptable. Right? Their intersection is nothing but acceptable. So this is nothing but acceptable. And the probability of E intersection F intersection E complement will be what? 10 by 18. Right? So what is this probability? This will become 10 by 18 upon, what is the probability of E complement? The probability of E is 3 by 18. So the probability of E complement is what? 15 by 18. Given that E doesn't happen, which means either this happens or this happens, which means there are 15 cases, 15 by 18. So now this is our probability. It is 10 by 15 or 2 by 3. If you make this expression correct, then the rest question will be very simple. Okay. So read the question carefully, make the events very carefully. Or you can also make here, you can make the event E as the transistor is not defective. In that case, you will have to calculate F by E. Then the events change. So depending on your event, read the statement carefully and make the expression. Then it will be easy. So the probability is 2 by 3. Okay. Let's move to the next problem. So I'll read the question. Mrs. Perez figures that there is a 30% chance that her company will set up a branch office in Phoenix. If it does, she is 60% certain that she will be made manager of this new operation. What is the probability that Perez and Phoenix will be a Phoenix branch office manager? Okay, interesting question. So here also we will have to make events very carefully. There are a few events given. The first event given is that her company will set up a new branch in Phoenix. This is the first event given, and there are 30% chances of that. So the one event given is company sets up a new branch in Phoenix. Okay, and it is given that probability of this event is 30%. There are 30% chances. If it sets up a new branch, she is 60% certain that she will be made a manager of this branch. So it is like if E happens, then probability of her being a manager is given to be 60%. So the other event F should be what? F should not be if and like, see, this entire event is what? If the company sets up a new branch, then the probability is given. So it is like probability of something by E is given. Probability of her being a manager given a new branch is set up is given. Probability of her being a manager given that the new branch setup, given E happens, is given. So what is, let's say the event F is like she becomes office manager. She becomes office manager. This we don't know, but it is given that she will become a manager given that the company sets up a new branch. This is given to be 60%. I hope you got it. If the company sets up a new branch, she will become a manager with 60% chances. Now what they want, what is the probability that Perez will be the manager? So we want probability of F. P of E is given, P of F is to be calculated, and P of F by E is given. So it's a slightly different question. But yeah, we know the formula, P of F by E is P of F intersection E upon P of E. Right? Yup. So it means that P of F intersection E is 6 by 10 into probability of E, which is 3 by 10. Okay? Which is 18 by 100, which is 0.18. There are 18% chances. So this whatever we have calculated right now is P of F intersection E. What is F intersection E? F intersection E is company sets up a new branch in Phoenix and she becomes office manager. That's what we wanted also. We actually didn't want P of F. Read the question carefully. What is the probability that Perez will be a Phoenix branch office manager? It is not saying any manager. It is saying Perez will be Phoenix branch office manager. It means that both events happened. Company has set up a new branch in Phoenix and she became the manager. So actually we wanted this only. Right? And this is what we have calculated, 0.18. Okay, I hope you got it. So we didn't just want we just didn't want the probability of she being any manager. We want her to be the manager of Phoenix branch office, right? And that's what PF intersection E is. P of F intersection E is, right? Both the events are happening. So there are 18% chances that she will become the manager of this branch. Okay. Moving on to the next question. This question has been asked in GATE 2010 in computer science. So a box contains 4 white balls and 3 red balls in succession. 2 balls are randomly selected and removed from the box. Given that the first removed ball is white, the probability that the second removed ball is red is. Okay. So, like, see, generally speaking in probability, don't mug up the formulas. Condition probability, if you mug up P of E by F is P of intersection F upon P of F, and you keep mugging and then keep multiplying, nothing will happen. Okay, it will be very tedious for you to solve problems. Try to logically feel like how it is derived. What is condition probability? It's very obvious, right? Given this event has happened, what is the probability of this happening? Right? Now the sample space has reduced. So you can logically think about problems. And even in counting, when we discuss so many things, I gave you proof of almost every formula, inclusion, exclusion, how it works, dearrangement, how it works, right? Multinomial, binomial theorem and the relation of them with combinations. So try to see the connections and try to derive it on the spot. Okay, you won't be able to remember everything. See, this question can be solved using formula. It will take like writing a formula, generating events. It will be a lot of time. But see, very obvious question. If I forget about every formula, it's just very simple common sense, okay? A box contains 4 white balls and 3 red balls. This question just requires 30 seconds, trust me. 4 white balls, 3 red balls. In succession, 2 balls are randomly selected and removed from the box, one after the other. We select one ball and then we select another ball. So basically we are not replacing them. So given the first removed ball is white, it is given that the first removed ball is white. Okay, like the first removed ball is white. Now what happens? The bucket becomes 3 white and 3 red balls. Given that the first removed ball is white, now the bucket becomes 3 white and 3 red balls. Now what is the probability that the second removed ball is red? So now the box becomes this. So what is the probability that the second removed ball is red is 3 by 6. That's it. That's it, right? Logically thinking, this is the problem. But now, like if you want formula, so like you will have to generate events. Event E is what? First removed ball. Since we are drawing 2 balls, the sample space is what? Sample space is white, white. The original sample space. You can get both white. You can get first white and then red. You can get first red and then white, or you can get first red and then second red. This is the entire sample space. The event E is first removed ball is white. First ball is white, and the event F is second ball is red. Okay. and the event F is second removed ball is red. Now we want probability of F given E has already happened, which will be probability of F intersection E upon probability of E. So firstly let's calculate what is the probability of E. What is the probability that the first removed ball is white? What is the probability that the first removed ball is white? It is 4 by 7. Since there were 4 white balls and there were 7 total balls. The probability of first removed ball to be white is 4 by 7. Now what is the probability of F intersection E? It means that what is the probability of first removed ball to be white and second removed ball to be red? So this probability will be what? So first removed ball is white and second removed ball is red. First removed ball is white and then the second removed ball is red. So now this and this will cancel and you will get 1 by 2 only. Right? Formula wise, like if you do conditional probability, it will be tedious. But like if you just do logically, like first removed ball is white, so now the sample space becomes this, right? That's what happened here as well. Then the probability becomes 1 by 2. Okay? Hi everyone. Welcome to lecture number 3 of probability under GATE data science course. In this lecture, we will learn multiplication theorem. So in the last lecture, we have learned conditional probability, and multiplication theorem is just a derivative of that theorem. Okay, you can like just rearrange the theorem and get this, but it has beautiful applications. Okay, when we solve questions, like you can consider both of them as conditional probability questions in some sense. Cool. Let's see. Conditional probability, we have already seen that if we have two events E and F, and the probability of the first event given that other event has already happened, that is called conditional probability. Probability of E given F, or P of E by F, and its formula is probability of E intersection F upon probability of F. Probability of E given that F has already happened is the probability of E intersection F upon probability of F. Right? Now, what we can do is we can rearrange conditional probability to get the multiplication theorem. So let's say there are two events A and B. We know that probability of A given B has already happened is probability of A intersection B upon probability of B. So if I just take this PB and take it here, then probability of A intersection B, probability of A and B both happen. Probability of A and B both happen is probability of B happening times probability of A given B has already happened. It's very logical. See, what is the probability of two events both happening simultaneously? Probability of one of them happening into probability of the other happening given that the first has already happened. Right? It makes sense. Right? You just rearrange conditional probability and you'll get this. Similarly, you can write it as probability of A intersection B upon probability of B by A. If I write probability of B given A has already happened, so it will become probability of, in the denominator you will have probability of A. So this will tell you कि probability of A intersection B is also equal to probability of A happening times probability of B given A has already happened. Take any one of the event that happened first times probability of the other event given that the first event already happened. That is just the multiplication theorem. And here obviously PA and PB cannot be 0. If the denominator is 0, you cannot like just multiply it on both sides, right? That's like divide by 0 error, right? You cannot multiply it. So given that the denominator is not 0, this multiplication theorem holds true. And now there is an extension. There is an extension to this theorem as well. If you just extend it to n events, see, this is the multiplication theorem for two events. If there are n events, extension of the multiplication theorem, if a1, a2 up to an are n events associated with a random experiment, then probability of all of them happening, there are n events, probability of all of them happening is, take any of the events, it need not be the first event, take any event, let's say a1, probability of the first event times probability of the second event happening given that the first has already happened, times probability of the third event given that first and second both have happened, times probability of the fourth event given that the first three events have already happened times and so on probability of the last event given that all the other events have happened. Okay, very logical. First event happened times now what is the probability of second event given that the first has already happened times now the probability of third event given that the first two events already happened and so on. This is the extension of the multiplication theorem. Okay, so now let's solve a few problems and generally speaking, like when the question on multiplication theorem comes, by seeing the question you will know. Okay, you need not exactly know that it is multiplication theorem question. It might be conditional probability. Okay, it's just a rearrangement of conditional probability, right? So just think logically what is given and what is required and it will be done. So let's solve this question. A bag contains 3 red and 2 blue balls. Okay, there is a bag. It contains 3 red and 2 blue balls. And now you have to pick balls without replacement. So once you pick a ball, you don't replace it back. You just keep it and then you draw another ball. So what is the probability of getting the first red and then a blue ball? Getting a first red and then a blue ball. So it's like probability of getting red in the first attempt and then getting a blue in the second attempt. Probability of getting red in the first attempt and then blue in the second attempt. It will be equal to probability of getting red in the first attempt times probability of getting red in the times probability of getting a blue ball in the second event given that we already have a red ball in the first attempt. Right? Probability of getting a red ball in the first attempt times probability of getting a blue ball in the second attempt given that we already have a red ball in the first attempt. See, we could have written it in this way as well. Probability of getting a blue ball in the second attempt times probability of getting a red ball in the first attempt given that we have a blue ball in the second attempt. But this will be very difficult to solve, right? See, multiplication theorem can work two ways in two events. You can write it this way or this way. But you have to see logically. See, this is something that we are easily able to calculate. Probability of getting red in the first attempt, easy, right? Now, given that first attempt already had a red, we know that what will be the state of the bag. So now calculating the probability of getting a blue ball in the second attempt, given that the first attempt already had a red ball, this is also easy. But this expression is also correct, but this is difficult to calculate. Firstly, probability of getting a blue ball in the second attempt directly, that is difficult. What is the probability of getting a blue ball in the second attempt? That will require some other formula, okay, total probability, okay, we will see later. This is not like straightforward. And this is like not at all straightforward. Given that the second ball was blue, what is the probability that the first ball is red? So this is like tedious, right? So always be intelligent, like this is the way in which we will write it. You just have to like see what the problem is asking. Cool. So what is the probability of getting a red ball in the first attempt? In the first attempt, like there are 3 red and 2 blue balls, so 3 by 5. There are 3 red and 2 blue balls, so the probability of getting a red ball is 3 by 5 times. Now this probability, we will not use the formula. If you use the formula, you will get the same thing again. This is very easy to calculate. See, given that the first ball is red, you already have a red ball out. So now the bag contains 2 red and 2 blue balls. This is your sample space. Previously, this was your sample space. But now given that R1 has happened, this is your sample space. Now, what is the probability of getting a blue ball in the second attempt? There are 2 red and 2 blue balls. So now the probability becomes 2 by 4. So this becomes 3 by 10. Okay. Now, if how to solve the second problem? What is the probability of getting 3 consecutive red balls? It is like probability of getting red in the first attempt and getting red in the second attempt and red in the third attempt. Again, you can write this in 3 different ways. But the most intelligent way will be probability of getting red in the first attempt times probability of getting a red in the second, given red has happened in the first, times probability of getting a red in the third attempt, given that you have got red in first and in second. This is the right way to write it. You cannot write it in any other way. You won't be able to solve. So what is the probability of getting a red in the first attempt? 3 by 5 times. Now what is the probability that okay, so in the second attempt, this will be your universe. Since one red has already come, this is your universe now. Given that first is already red, this is your universe. What is the probability of getting a red ball again? It will be 2 by 4. Now, given that R1 and R2 had happened, which means that both the attempts gave you a red ball, which means now this is your sample space, 1 red and 2 blue balls. So now given this happened, what is the probability of getting a red ball again? It will be 1 by 3. That's all. So it's 1 by 10. Okay. So there are 10% chances that all the 3 balls will be red. Okay, I hope you got it. Moving on to the next problem. Suppose that each of 3 men at a party throws their heads at the center of the room. There are 3 men, 1, 2, 3. They throw their hats at the center of the room. Now the hats are mixed up and each one of them takes a hat from the floor. Okay, they are each taking one hat from the floor. What is the probability that all 3 of them select their own hats? See, what is the sample space? Okay, the first guy is picking the first hat, 1, 2, 3. Or the first guy can select the second hat. The second guy can select the first hat, 2, 1, 3. So there are 6 ways, right? So let's say the ordering is the first guy is getting what hat? Second, so 1, 2, 3, 2, 1, 3. Then 2, 3, 1. And then okay, 1, 3, 2. Then 3, 1, 2. And then 3, 2, 1. There are 6 possible ways, right? There are 6 possible ways in which they can get their hats back. This is your sample space. So what is the event is all 3 of them select their own hats. So this is the only event. The event is given to be all of 3 of them are getting their same hat. So what is the probability of this event? 1 by 6. There are 6 elements in the sample space, that's why. Now the second question is, no 3 of them select their own hats. No 3 of them get their own hat. Now this is an interesting and very standard problem which I told you in combinatorics. It is called dearrangement. In how many ways can 3 people, 3 letters can be distributed in 3 covers such that no letter goes in the correct letter, okay? The common mistake is people think that it will be 1 minus this, 5 by 6, no. It is not 1 minus this, because since none of them can get their correct hat. So among these 6 ways, in how many ways none of them are getting their correct hat? This is definitely not, because all 3 are getting the correct. This is also not, because third is getting its correct hat. This is 1, 2, 3, 1. In this, none of them are getting their correct hats. Is this one? No, because first one is getting the correct hat. Is this one? Yes. 3, 1, 2 is correct, right? None of them are getting their own hats. And is this one? No, because the second guy is getting the correct hat. So there are only 2 ways in which none of them are getting their correct hats. So the second event F has only 2 elements, 2, 3, 1 and 3, 1, 2. Okay, this was a question on general probability. So probability of event F is 2 by 6. And this is also the third dearrangement number, if you remember. The number of dearrangements of 3. It is what? 3 factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. You can calculate it this way as well. So this and this will cancel. So 6 by 2 minus 6 by 6. Okay. Okay, yeah, 6 by 2 is 3. So 3 minus 1 is 2. So there are only 2 dearrangements of 3 words. So you can do it that way as well. So I hope you got it, right? None of them got is dearrangement. Cool. And if you don't remember the dearrangement formula in exam, if you don't remember this, if the question is small, you can directly eliminate. Let's say now you had 10 people or 7 people, then you won't be able to enumerate all of them, right? Then if you forgot dearrangement formula in exam, it's very easy. You can directly use inclusion, exclusion there and then, okay? You're not supposed to remember every formula. You can use inclusion, exclusion directly. Just remember the basic concepts, okay? You'll be done. Cool. Now there is this other question. There is a lock and a bunch of 10 keys. If we try opening the lock with the keys one by one until we are able to open the lock, keys are chosen randomly without replacement. You're not stupid, okay? You are not using the same key again. That's what it is given. Then what is the probability that the lock opens in the 5th trial? What is the probability that the lock opens in the 5th trial? So what we want is probability of lock opening in the 5th trial. So think about it. It's like quite simple. Basically, it should not open in the 1st trial, and it should not open in the 2nd trial, and it should not open in the 3rd trial. So basically, what we want is we cannot directly calculate the probability of lock opening in the 5th trial. That's what we want. But this is not very easy to calculate, right? Because we don't know what is the state after 4 trials. See, the question involves the state of the previous 4 trials. If you want to go to the 5th trial, you need to know the state of what happened in the previous 4 trials. Right? So this is nothing but if you see carefully, this is nothing but probability of the lock not opening in the 1st trial, then lock not opening in the 2nd trial, and not opening in the 3rd trial, not opening in the 4th trial, and then the lock opening in the 5th trial. This is what it is, right? Which is what probability of lock, that the probability that the lock doesn't open in the 1st trial. I'm using multiplication theorem. What is the probability that the lock didn't open in the 1st trial? It is 9 by 10. Because there are 10 keys, one of them is correct. So 9 by 10 is the probability that the lock didn't open in the 1st trial. Times. Now in the 2nd trial also lock should not open. So given that the 1st key failed, now you have only 9 keys left. Given, so like if I expand this will become probability of n1 times probability of n2, given n1 has already happened, right? Which means that 1st trial the lock didn't open. Now what is the probability of the lock opening in the 2nd, not opening in the 2nd trial, times the probability of lock not opening in the 3rd trial, given that the lock didn't open in the 1st and 2nd trial, times and so on. So what is it? What is the probability of lock not opening in the 1st trial? 9 by 10. Now given that the 1 key has already gone away, there are 9 keys left. 8 of them didn't open the lock, don't open the lock. So probability of the lock not opening in the 2nd trial also will be 8 by 9. Right? The probability of lock not opening in the 2nd trial will be 8 by 9. Similarly, the probability of lock not opening in the 3rd trial will be 7 by 8, because now only 8 keys are left. And in the 4th trial, only 7 keys are left. So the probability of lock not opening in the 4th trial also will be 6 by 7. Now in the 5th attempt, there are only 6 keys left, out of which 1 is correct, and you want to use the correct key. So the probability is 1 by 6. So this and this cancels, this and this cancels, this and this cancels, this and this cancels. So the probability becomes 1 by 10. Okay. Actually, if you see, in some way, the probability of the lock opening in any trial will be 1 by 10 only. Right. The probability of lock opening in the 1st trial is 1 by 10. Now the probability of the lock getting opened in the 2nd trial is also 1 by 10. Using this formula, it will be like 9 by 10 into 1 by 9. Right. You keep using the formula. So actually the probability of the lock, see that is how it is supposed to be as well. There can only be at max 10 trials, right? There can be at max 10 trials. You don't need the 11th trial. Since there are only 10 keys and you are choosing them randomly without replacement. So what happens is, generally speaking, you will be at max be able to open it in the 10th trial. And the probability is, see, this is a random experiment. You can be able to open it in any trial. So ideally they should be equal as well. So logically thinking says that in any trial the probability should be same. Why should the first trial have the highest probability? No, right? There are 10 keys and they are random. So the first trial it is 10%. In the second trial also it will be 10%. And the formula also gives us the same thing. So it's beautiful, right? Think about it. Okay, this is an interesting question. It's asked in GATE Computer Science 2012. And since we don't have any GATE DA paper papers right now, we are using GATE Computer Science questions here as well. But once we have like a few data science papers like next year's, we will like add those questions as well in the videos, right? So yep, a fair coin is tossed till a head appears for the first time. A fair coin is tossed till the head appears for the first time. You keep tossing it. You keep tossing the fair coin until you get a head. The probability that the number of required tosses is odd is what? What does it mean? Then you will stop once you get an head. Okay, you will keep spinning the coin until you get a head. So it might be possible that you will keep getting tails. Okay, it is a random experiment. You might get tails. So let's say after 6 tails you get the 7th head. Right? So in the 7th attempt you got an head. That is okay. That's what you want. What is the probability that the number of attempts, total attempts is odd? So what are the cases? See, the sample space is what? Sample space is either the first attempt is head, or the first attempt is head and the second attempt is head, or the first 2 attempts are tail and the second. So this is a sample space. This is the universe. You require 1 attempt, 2 attempts, 3 attempts, 4 attempts, and so on. It has this is the first question that we are doing which has infinite sample space. It has infinite elements in the sample space. You can require infinite number of attempts as well, right? So these are the elements. But our event E is what? Our event E is what? The probability that the number of tosses required is odd. So in the first, either you can get it in the first attempt. This is not allowed. You cannot get a heads in the second attempt. The number of tosses should be odd. So either it should be tails, heads, or it should be tails, heads, and so on. Even the event is an infinite space. But the total number of events, numbers required should be odd only. So what is the probability? So probability, see, now here what happens, we want to find the probability of event E. So here what we can do is, see, observe the fact that these individual attempts, these individual events, either getting heads in the first attempt or in the third attempt or in the 5th attempt, they are all mutually exclusive. Either this will happen or this will happen or this will happen or that will happen, right? They are all mutually exclusive. So what we can see that if I break down it in smaller events, this is event E1, event E2, this is event E3, and so on. They are all mutually exclusive. One of them will happen, right? So probability of E is what? It is the probability of event of occurring of E1, E2, E3 or something. And now since they are all mutually exclusive, the probability of their union will be what? Probability of E1 plus probability of E2 plus probability of E3 and so on. So either this happens, either heads comes in the first attempt or the third attempt or the 5th attempt and so on. So it's like addition of all of these, right? So what is the probability of getting a head in the first attempt? It is 1 by 2. What is the probability of getting a head in the third attempt? So that is what? You have to get a tails in the first attempt, and then you have to get a tails in the second attempt, and then you have to get a heads in the third attempt. Probability of getting a tail head is 1 by 2 cube. Similarly, probability of getting a tail heads in the 5th attempt is what? 1 by 2 to the power 5 and so on. Next term will be 1 by 2 to the power 7 and so on up to infinity. Right? What is this? This is an infinite GP. The infinite GP AR square, AR cube up to infinity has a sum of, the sum of all these is A upon 1 minus R. So here the first term is 1 by 2 and the common difference is what? What is the common difference? It is 1 by 2 square. You are actually multiplying 1 by 2 square. every time. So in 1 by 2 you multiply 1 by 2 square, then in 1 by 2 cube you multiply 1 by 2 square, and so on. So the common difference is 1 by 2 square, or 1 by 4. So this becomes 1 by 2 upon 3 by 4, which is 4 by 6 or 2 by 3. Okay, so there are 2/3 chances that the number of tosses required will be odd. Okay, I hope you got it. And similarly, the number of the probability that the number of tosses required will be even will be 1 by 3. Cool. So these were a few questions on multiplication theorem and conditional probability. We will solve a lot more questions when we discuss like when we have problem solving and doubt solving sessions.
Hi everyone, welcome to lecture number 4 of probability in statistics under GATE DA. So we have seen conditional probability. What is the probability of an event A given that event B has already happened, and then which is equal to probability of A intersection B upon probability of B. And then we rearranged it to get probability of A intersection B, like probability of two events happening together is probability of any one event times probability of the other event given that the first event has already happened. That was called multiplication theorem. Now again, very similar, like going forward in conditional probability and multiplication theorem, we have a very beautiful notion of independent events. So we will see independent events in this and next lecture. So what are independent events? So let's see the definition first. Yep. So the case where probability of E given F has already happened is equal to probability of E. What does it mean? That it doesn't matter that F has happened or not. Probability of E remains same. So you have two events. So for example, throwing a dice. Okay. Let's say E is an event. Again, E is an event of getting a prime number. We know that it is 2, 3 and 5. And let's say F is an event of getting an odd number, which is 1, 3 and 5. Right. So here in this case, when we throw a dice, we know that what is the probability of just event E? It is 1 by 2, because we have 3 cases which are possible. You can get 2, 3 or 5, they are all prime. So probability of happening of event E is 1 by 2. Similarly, probability of happening of event F is also 1 by 2. There are also 3 cases here, 1, 3 and 5. But now, in this case, what is the probability of E given F has already happened? We saw this in last class, right, in conditional probability. So if we know that F has already happened, if we know that 1, 3, 5 was already there, it is sure that it is either 1, 3 or 5. Given that F has already happened, what can be the prime numbers? 3 or 5. Only 3 or 5 are possible. So the probability now, the new updated probability of event E happening, given that F has already happened, is 2 by 3. You can use the formula as well, you will get 2 by 3, right? So now here what happened, see, probability of E initially was what? 1 by 2. But probability of E given F has already happened increased a little bit. So it might increase or decrease depending on the events, right? But sometimes it can remain same also. So if the probability of E given F has already happened doesn't change, it is equal to probability of E only, then E and F are said to be independent. The very common mistake, or the common difficulty which people face in probability is they consider independent events and mutually exclusive events same. Mutually exclusive events are different, independent events are different. Mutually exclusive events don't have anything in common. Mutually exclusive events don't have anything in common. For example, getting an even number and an odd number. These two events have nothing in common. So their intersection is phi, or the empty set. But independent events are different. And we will later see in this lecture that they are actually very different. If two events are exclusive, they can never be independent, right? So we will see that. So they are different notion. Exclusive means they have nothing in common. Independent means happening of one event doesn't affect the probability of other event. Like this. Here, happening of F affects the probability of E. So that's why they are not independent. So if P of E by F is equal to P of E, which means that happening of F doesn't change the probability of E, then we say that E is independent of F. Okay, so we can also like rearrange terms. So what is probability of E by F? It is probability of E intersection F upon probability of F. We already know this. And it is if E and F are independent, if E and F are independent, we know that probability of E by F is nothing but the probability of E. Which means that two events are independent if the probability of their intersection, two events are independent if the probability of their intersection is nothing but the product of their individual probabilities. Okay, I just rearrange this. So two events are independent if probability of their intersection is product of their individual probabilities. See, it is different from mutually exclusive events. In mutually exclusive events, probability of intersection is 0. Right? If two events are mutually exclusive, their intersection has nothing in them, right? So probability of the intersection becomes 0. But here it is not 0, here it is a product of the individual probabilities. So E is independent of F if knowledge that F has occurred does not change the probability that E occurs. So in some cases it will be very obvious that two events are independent. When we see examples, I will tell you, right? So in few experiments or examples, it will be very clear. But just by seeing the problem, you will see that the events are independent. The happening of one event doesn't affect the probability of other. But sometimes it is not very obvious. Sometimes in some experiments, when you see the sample space and the events, it will be not very obvious that the events are independent. And in those cases, generally when you apply the formula and see if the probability of intersection is actually equal to the product of the individual probability, then they will be independent. Okay, so we'll see like both examples, like which are obvious and not obvious. Cool. So if two events E and F are said to two events E and F are said to be independent if this equation holds. Two events E and F that are not independent are also called dependent. Okay, so if they are not independent, they are called dependent. So let's see an example. Okay, so we are tossing two coins. Okay, so the experiment is we are tossing two coins. So we have two coins and we are tossing them. So what is the sample space? Sample space contains 4 outcomes. Either you can get head in both. You can get head in the first and tail in second. Tail in first, head in second. Or you can get tails in both. Right? This is your sample space. Now you are given two events. First event is getting a head on the first coin. First event is getting a heads on the first coin, which means this or this. Right? So the event E1 is what? Either heads heads or heads tails. Right? Event 2 is given as getting a head on the second coin, which means either this or this. Oh, sorry. Yep. Either this or this. Right? So what is event 2? You have to get in heads on the second coin, which means either you get heads heads or tails heads. This is your event 2. So question number 1, are these two events mutually exclusive? They are not mutually exclusive, right? They have something in common. This is common in both. They can happen together. Both these events, even in E2, can happen together. They are not mutually exclusive. But are they independent now? Let's see that. So what is probability of E1? Firstly, I will give you the formula notation, right? Like we will just use the formula to find out they're independent or not. Then I will give you the logical explanation as well. So what is probability of E1? There are two events which can happen, and there are total 4 events in sample space. So the probability of just event E1 happening is 1 by 2. Similarly, probability of happening of event E2 is also 1 by 2, since there are 2 elements in it in event E2. Now, what is the probability of E1 intersection E2? So what is E1 intersection E2? We already saw. There is one element which is common in both E1 and E2, which is heads heads. So the probability of E1 intersection E2 becomes 1 by 4. And here we can see that probability of E1 intersection E2 is indeed equal to the product of individual probabilities. Probability of E1 times probability of E2. Right? So hence they are independent. What does it mean? Ki the happening of second event
doesn't change the probability of first event. And similarly, happening of first event doesn't change the probability of second event. It's true both ways. So it is obvious as well. Like, think about it logically. If you think, getting a head on the first coin. Okay, so somebody is saying like you're tossing 2 coins. Let's say 2 individual people are tossing 2 coins, right? So first guy says that I got a head. Now what is the probability that you are getting head? It still remains half, right? So second guy is independently tossing the other coin, right? So it doesn't matter what happens on the first coin. Probability of getting a head on the second coin still remains half. At the beginning of experiment, what is the probability of getting a heads on the second coin? It's half, right? But if the first guy says that I got an heads, but still like the probability of second guy getting an heads still remains half, right? So it's very logical. Like, this was an obvious example. So generally, like, examples like this, where like you're tossing 2 or 3 coins, then like individual probability of these coins will be independent. Or sometimes when you have a bag, let's say, like that's a very standard problem in probability, right? A lot of times it is asked in GATE. So there is a bag which contains n number of red balls, blue balls, and black balls, and you take 1 ball out of it, and then you take second ball out of it. So if you take the first ball and then the second ball, if you don't replace the ball, generally, like, the difficult question is you are not replacing the ball again. When you take the first ball out, you place it somewhere else. Then you take the second ball out. In this case, the outcome of the first event, which means the outcome of the first time when you are grabbing a ball out of the bag, actually is dependent on what is happening in the second event, because you might get a red ball in the first event. Now the bag changes, right? So in this case, they are not independent. But sometimes it might be given that when you are pulling balls out of a bag, you are again replacing them back. So you take one ball out of the bag, you see the color, and then you again put it in the bag, and then you again pull out 1 ball. Now in this case, event E1 and E2 becomes independent, since the configuration of bag remains same. Okay, we will see with examples as well. So this was first experiment. This is second experiment. You are rolling a die. Now this example is not obvious. Okay, so you are rolling a die. So what is the sample space? It contains 6 possible events which are possible. You can get a 1, 2, 3, 4, 5 or 6. Okay. So basically, getting a 2 on the first die, getting a sum. So you're rolling 2 die actually. Like, there is a mistake here. Since in the events they are talking about 2 dice, so the experiment is rolling 2 dice. Okay. If you're rolling 2 dice, what is the sample space? It contains 36 possible outcomes. You can get 1 and 1, you can get 1 and 2, you can get 1 and 3, so on. You can get 6 and 6. Right? There are 36 possible outcomes, we know. Now event E1 is given to be getting a 2 on the first dice. So what is event E1? E1 will contain 6 events, right? Like 6 possible outcomes. You can have 2 1, 2 2, 2 3, 2 4, 2 5 or 2 6. This is event E1. You are definitely getting a 2 on the first dice. The event E2 is given to be getting a sum of 5. So what are the possible outcomes in this? How can you get a sum of 5? So you can get 1 on the first dice and 4 on the second. You can get 2 on the first dice, 3 on the second, 3 on the first dice, 2 on the second, and 4 on the first dice and 1 on the second. These are the full possible outcomes, which will give you sum of 5. And event E3 is given as getting a sum of 7. So what are the possible outcomes here? 1 6, 2 5, 3 4, 4 3, 5 2 and 6 1. Right? Okay. Now we will see pair wise, like what all events are independent of each other. So this is our sample space. It contains 36 possible outcomes. So what is the probability of event E1? E1 contains how many outcomes? 6 outcomes. So 6 by 36, which is 1 by 6. Probability of event E1 is 1 by 6. Probability of event E2 is what? Probability of event E2 is what? E2 contains 1, 2, 3, 4 items, 4 outcomes. So 4 by 36, 1 by 9. Right? Similarly, probability of E3 is what? E3 again contains 6 outcomes. So 6 by 36, 1 by 6 again. These are individual probability of these 3 events. Now let's calculate the probability of intersection as well. Like E1 intersection E2, E2 intersection E3 and E1 intersection E3. We want to see pairwise what all events are independent of each other. So what is the probability of E1 intersection E2? So how many elements are common in both E1 and E2? Which means you want a 2 on the first die and you want to get a sum of 5. So there is only one element which is common, 2, 3, right? There is only one element which is common. So the probability becomes 1 by 36. Right? Similarly, what is the probability of E1 intersection E3? Let's see the first and third events, which means getting a 2 on the first die and getting a sum of 7. So how many elements are common? So only one element is common, 2, 5. 2, 5 is common in this and this, right? Because you are getting a 2 on the first die and you are getting a sum of 7. So only one event. So again 1 by 36. And what is the probability of E2 intersection E3? Which means you are getting a sum of 5 and you are getting a sum of 7. It is not possible. Either you will get a sum of 5 or 7, right? You cannot get a sum of both 5 or 7. So there is nothing in common in these two. So the probability of E2 intersection E3 is 0. Right? So now which all events are independent? See, probability of E1 intersection E2. Let's see first and second event. Is it equal to probability of E1 into probability of E2? Probability of E1 into probability of E2 is what? 1 by 54, which is not equal to 1 by 36, right? So it is not equal to probability of E1 into probability of E2, which means that E1 and E2 are dependent. They are not independent. E1 and E2 are not independent. And let's see that as well. What is E1? And what is E2? So E1 says you get a, so E1 is getting a 2 on the first die. E2 is getting a sum of 5. We know that initially probability of event E2, which is probability of getting a sum of 5, is 4 by 36. There are only 4 cases, right? 1, 4, 2, 3, 3, 2 and 4, 1. So the probability initially was 4 by 36, well 1 by 9. See, there are no cases in E2, so you cannot get a 5 on the first dice. So if you get a 5 on the first dice, you cannot get a sum of 5 because you will get at least a 1 on the other die, right? That's why you don't have any 5 here. So basically what it means, first die can only have 1, 2, 3 or 4. Then only it is possible. So it is slightly biased, right? Event E2 is slightly biased. It only happens if both the die have numbers between 1 and 4. If any die gets a number 5 or 6, it doesn't happen. So event E2 is not uniform across any dice, right? Because it only happens if you get a 1, 2, 3 or 4. Now event E1 said that, event E1 was, it said that you get a 2 on the first die. You get a 2 on the first die. So initially when you were computing probability of E2, which means probability of getting a sum of 5, you were factoring in all possible cases. You can get 5 or 6 as well, right? That's why the probability was less. It was 1 by 9 only. It is very less, right? But now event E1 said that it is guaranteed that you get a 2 on the first die. Now since it is guaranteed to get a 2 on the first die, what happened? The probability of the probability of event E2 increased. Why? Because it is definite that you cannot get a 5 or 6 on the first die, right? And now like the probability of event E1 will increase. You can see that as well, right? So what is the probability of E1 given E2 given E1 has already happened? It is probability of E1 intersection E2, which is 1 by 36 upon probability of E1, which is 1 by 6. So it becomes 1 by 6 now. It increased. Initially it was 1 by 9, but now it increased to 1 by 6. Why?
because it is given that the first die is giving you a 2. So now the second dice only has to get a 3, because 2 comma 3 gets a sum of 5, right? So now out of the 6 possible outcomes, 2, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, one of them is favorable. Previously out of 36 outcomes, only 4 were favorable. But now out of 6 outcomes, 1 is favorable. So the probability increased. And that's why happening of event E1 increases the probability of event E2. And that's why they are dependent. They are not independent. And you get that from the formula as well, right? Similarly, let's see event E1 and E3. So is the probability of E1 intersection E3 equal to probability of E1 into probability of E3? What is probability of E1 and probability of E3? It is 1 by 6, 1 by 6. So product is 1 by 36. It is correct. They are independent. Events E1 and E3 are independent. E1 and E3 are independent. How? The formula gives us that. Because probability of E1 intersection E3 is probability of E1 into probability of E3. But now let's see that as well. Event E3 was getting a sum of 7. Right? Event E3 was getting a sum of 7. So out of all 36 sample space, 6 element passed that. Right? 6 of the outcomes had a sum of 7. So initially the probability was 1 by 6 of getting a sum of 7. Right? These were the 6 outcomes. Now event E1 is saying that you get a 2 on the first dice. You get a 2 on the first. So this is not very obvious. You don't by just seeing the problem, it's not very obvious ki E1 and E3 are independent. But if you think very logically, see what happens. Initially probability of event E3 or getting a sum of 7 is 1 by 6. And now event E1 is saying that you will get a 2 on the first die. So if you get a 2 on the first die, only 6 outcomes can happen. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5 and 2, 6. And out of these 6 outcomes, still only one has a sum of 7, which is 2, 5. So initially the probability was 1 by 6. Now if you get a 2 on the first die, still the probability is 1 by 6. Because out of the 6 outcomes, only one is favorable. Initially, out of 36 outcomes, 6 were favorable. So probability doesn't change. Even if event happens, probability of E3 remains same. Similarly, you can do vice versa as well. Probability of E1 given E3 has already happened. That will also be equal to probability of E1. Okay, independence works both ways. So yeah, E1 and E3 are independent. Now probability of E2 intersection E3 is what? 0. Is it equal to probability of E2 into probability of E3? No. Probability of E2 into probability of E3 is 1 by 54, which is not equal to 0. So they are not independent. Okay. E2 and E3 are not independent. Actually, E2 and E3 are mutually exclusive. They are exclusive. They don't have anything in common. You cannot get a sum of 5 and a sum of 7. E2 and E3 are mutually exclusive. We will see later that if there are 2 events with non-zero probability and if they are exclusive, they can never be independent. It's a proof as well, right? If they are mutually exclusive, their probability of intersection will be 0. And if the individual probability is not 0, they will never be independent, right? If 2 events have a non-zero probability and if they are mutually exclusive, they can never be independent, right? So E2 and E3 are exclusive, not independent, and E1 and E3 are independent. These are the 2 relations that we have. Okay. Cool. Let's move to an example. So an urn or a bag contains 3 green and 2 red balls. You take out 2 balls with replacement. So here this is important. By default, if nothing is mentioned in questions like these, you don't assume that you are replacing ball. Let's say someone is saying okay, there is a bag and you take 2 balls out of it. By default, if nothing is mentioned, you are not replacing the balls. You take 1 ball and then you take the second ball. You are not replacing. But if it is mentioned, and read it very carefully, okay? Read the problem in probability very carefully. I made this mistake in GATE as well, right? So, if very carefully with replacement, there is very small buffer, okay? I made it bold here. In the paper, it won't be bold. Okay. So read it very carefully. So it is mentioned that you're pulling 2 balls with replacement. What does it mean? You will take 1 ball out, then you will see the color, and then you'll again put it back. Again shuffle and again put 1 ball out. So the state of bag remains same after pulling 1 ball out. Okay. So you take 2 balls with replacement. So what is the probability of getting a green and then a red ball? So easy problem. So a bag contains 3 green and 2 red balls. Okay. So see here what happens. You take the first ball and then the second ball. It is very obvious that these events are independent. Okay. Like when you solve many problems, okay, when you solve a lot of probability problems, you won't even need to use the formula. You can use the formula here, but it is very obvious that getting a green ball, so let's say event E1 is this. Getting a green on the first ball, and event E2 is this. Getting a red in the second trial. Getting a green and then red. So it means that event E1 is getting a green on the first trial, and then E2 is getting a red on the second trial. Events E1 and E2 are independent of each other. It is very obvious, right? It doesn't matter what color happens in the first trial. Probability of getting a red ball in the second trial will still remain same because you are doing it with replacement. Because you are doing it with replacement. Since you're putting the ball again and you're shuffling it again, the bag remains same. It will still have 3 green and 2 red balls. So it doesn't matter what happens in the when you pull out the ball in the first time, right? Probability of getting a red ball in the second time still remains 2 by 5. So these 2 events are independent. So what do you want? You want probability of E1 intersection E2, right? You want a green ball in the first trial and then you want a red ball in the second trial. You want E1 intersection E2. So it will just be probability of E1 into probability of E2. Which is, what is the probability of getting a green ball in the first trial? It is 3 by 5. What is the probability of getting a red ball in the second trial? Again, the state of bag remains same. So it will become 2 by 5. Right? So this becomes 6 by 25. Okay. Now second case is getting both green balls. So it will still be the same. Let's say even is the event of getting a green in the first attempt and E2 is getting a green ball in the second attempt. So probability of E1 intersection E2 will be what? Probability of E1 into probability of E2. So in the first attempt it is 3 by 5. In the second attempt it is again 3 by 5. So it is 9 by 25. Right? Cool. So okay, we can solve these problems, both these problems without replacement as well. Let's say the question was without replacement. So now the events are not independent. So here in the first case, what will happen? What do you want? Getting a green in the first ball and then red in the second ball, second attempt. So what is the probability of E1 intersection E2 now? Since they are not independent, what we will do? Probability of getting a green ball in the first attempt times probability of getting a red ball in the second attempt, given that we got a green ball in the first attempt. We already saw this in last class, right? Multiplication theorem. Okay. So what is the probability of getting a green ball in the first attempt? It is 3 by 5. Now, if you have got a green ball on the first attempt, now the bag will have what? 2 green and two red balls, right? If you already got a green ball in the first attempt, now you will have 2 green and 2 red balls. So now what is the probability of getting a red ball given that even has already happened? It will be 2 by 4. Okay. So it will be 3 by 10. So had it been you were pulling out balls without replacement, this is the probability. If you're doing it with replacement, this is the probability. Cool. So we have another question. There are 3 bags containing 3 red, 2 green, 3 red, 5 green and 1 red, 4 green balls. If you draw 1 ball from each bag, what is the probability of getting a green, red and green ball from first, second and third respectively? Again, so this, let's say event E1 is getting a green from the first bag, E2 is getting a red ball from the second bag, and E3 is getting a green ball in the third bag. Now it became very obvious. These 3 events are independent of each other.
It doesn't matter what ball you're getting from the first bag. Probability of getting a red ball from the second bag doesn't change. Right? They are independent. Three independent workers are working on these three problems. Again, see, there is a difference. These events are not exclusive. Exclusive events means what? Ki these three events cannot happen together. They can happen together. You can get a green from the first bag, red from the second bag, and green from the third bag. So they are not exclusive. They are independent. Which means that it doesn't matter what ball you get in the first bag, the probability of getting a red ball in the second bag remains same. It remains same, right? So what is the configuration given? The first bag contains 3 red, 2 green balls. Second bag contains 3 red, 5 green balls. And the third bag contains 1 red and 4 green balls. So now you want green from the first bag. So the probability is 2 by 5 times red from the second bag. Probability is 3 by 8. There are 3 red balls and total 8 balls. So probability is 3 by 8 times probability of getting a green ball from the third bag. So there are 4 green balls and total 5 balls. So 4 by 5. Okay. So it's 3 by 25. I hope you got it right. Probability of E1 intersection E2 intersection E3 is what? Probability of E1 into probability of E2 into probability of E3. Okay. Now second problem is slightly tricky. It says that what is the probability of getting 2 green and 1 red ball? It is not saying, this problem is not saying that which color ball is getting pulled from which bag. It is just saying what is the probability of getting 2 green and 1 red ball. That's all. You can get it from any bag. So here you have to remember the rule of sum, which is like the very first lecture of counting. Okay. So again, what is the configuration? Like we have 3 bags. Bag 1 contains 3 red, 2 green balls. Bag 2 contains 3 red, 5 green balls. And bag 3 contains 1 red, 4 green balls. This is bag 1. Bag 2. This is bag 3. Now you want 2 green and 1 red ball. So either you can get green from here, red from here, or you can get a green from here, red from here, and green from here, or you can get a red from here, green from here, green from here. So the total task T is doing task T1 or T2 or T3. Whenever you have or, it is rule of sum. So either you get this or this or this. Your condition satisfies. So what is the probability of green, green, red? We already know. It is 2 by 5. Probability of getting a green from the first bag. It is 2 by 5. Probability of getting a green from the second bag. It is 5 by 8. Right? 5 green balls, total 8 balls. What is the probability of getting a red from the third bag? 1 by 5. Plus, since it is an OR, plus, what is, again, like you can do this now, right? Like it's very simple. Like probability of getting green from the first bag, 2 by 5. Probability of getting a red from the second bag, it's 3 by 8. Probability of getting a green from the third bag is 4 by 5. Plus, probability of getting a red from the first bag is 3 by 5. Probability of getting a green from the second bag is 5 by 8. Probability of getting a green from the third bag is 4 by 5. So you can just calculate this. This will be our answer, okay? So I hope you got it, right? Like here the configuration was not given. So we just applied the rule of sum. And here like we are applying the independence rule many number of times, 3 times. Since we know that getting different balls from these 3 bags is independent of each other, we are just directly multiplying the probability. Cool. Let's see another example on independent events. So a card is selected at random from an ordinary deck of 52 playing cards. If A is the event that the selected card is an ace and H is the event that it is heart, are A and H independent? Okay. So one card is selected randomly from the deck of 52 playing cards and A event is given as getting an ace. See, generally, in JEE, in all exams, where aptitude questions are asked, like GATE, GRE, okay, and CAT. It is assumed that you have basic knowledge of a few things like rolling a die, coin. They won't explain what can happen if you roll a die. The most tricky part is remembering the shuffle deck of cards. Okay, generally people don't remember that. If you have not played cards very often in childhood, it will be difficult for you, right? Then you have to remember, and they will assume that you have this knowledge. So whenever before going to exam, just know there are 4 suits in a standard deck of cards, and there are 13 playing cards of each suit. The 4 suits are clubs, diamonds, spades, and hearts. There are 13 cards numbered from ace, 2, 3 up to 10, and then jack, queen, king, right? Jack, queen, and king are called face cards. So just a quick refresher. So there are 4 suits: diamonds, hearts, clubs, and spades. Okay, and diamonds, hearts, clubs, spades. Clubs and spades are black in color. Diamonds and hearts are red in color. Okay, and in each of the 4 suits there will be 13 cards each. Ace, 2, 3 up to 10. So 10 cards are like this, and then jack, king, and queen. Jack, queen, and king. Similarly, you will have the same configuration for hearts, clubs, and spades as well. So 13 into 4, 52 cards, right? And these 3 are called face cards: jack, queen, and king, because they will have a face on them. Jack will have a jack face, queen and king. Okay, these 3 are face cards, remaining are normal cards, and this is what happens. Okay, so they will assume that you have this basic knowledge. Okay, just a refresher. So event A is getting an ace, event H is getting hearts. Cool. So what is the probability of getting an ace? What is the probability of getting an ace? There are 4 aces, right? There will be an ace of diamonds, ace of hearts, ace of clubs, ace of spades. There are 4 aces, so 4 by 52. There are 52 cards, you can get any one of them. There are 4 aces, so probability is 1 by 13. Right? What is the probability of event H? H is what? Getting hearts. How many hearts are there? 13. There are 13 hearts, right? So out of 13, you can pick out any one of them. So probability of getting a hearts is 1 by 4. And now what is the probability of A intersection H? A intersection H is what? You are getting an ace and hearts, which means there is only one card which is both ace and hearts. It is ace of hearts. Okay, there will be a card called ace of hearts. So you can get only that card that is both ace and hearts. So that one card you have to get. So 1 by 52. So is probability of A intersection H equal to probability of A into probability of H? Yes, it is. It is 1 by 4 into 1 by 13. It is equal to probability of A into probability of H. So yes, A and H are independent. So you see that as well, okay. Logically as well, it is correct. Event A was getting an ace. Event H was getting hearts. So what is the probability of getting an ace initially? It was 1 by 13 because there were only 4 ace cards. It was 1 by 13. Now event H said that it is definite that you are getting hearts. So it doesn't matter if you are getting hearts, then also probability of getting an ace is 1 by 13. Since now you have reduced the sample size to 13 cards. Initially it was 52 cards and 4 were aces. But now it is 13 cards and only 1 is ace. So probability doesn't change. It is still 1 by 13, right? So probability of H, A given H has already happened, won't change. Similarly, probability of H given A has already happened, won't change. That's why they are independent, okay? Cool. So there are a few axioms. If A and B are independent, prove that these events are also independent. Okay, these are very important actually. These are very important, we will see. If A and B are independent, then A and B complement are also independent. Basically, you take complement anywhere, they will still be independent. A and B complement, A complement and B, A complement and B complement, all of these will be independent. This is a very important theorem. Okay, they can ask you this in multiple correct type questions, or GATE doesn't have that, then you'll get a very beautiful MCQ on this. Okay, and these type of questions are most tricky questions, trust me, because formula you can apply anytime. They are not directly formula based. You have to prove it. If A and B are independent, are A and B complement independent? Okay, and their proofs are also not very trivial. So we will see that. Given that A and B are independent, what does it mean? Probability of A intersection B is equal to probability of A into probability of B, since A and B are independent. Okay, now what does it mean? This is the Venn diagram. A and B. So probability of A intersection B is probability of A into probability of B. This is given. Now you want A and B complement. So this is the set that you want. So basically you want this set, A intersection B complement. It is A intersection B complement. So these are the elements, white shaded area are the elements which are in A but are not in B. Right? A and B complement are in A but are not in B. So how will you get this set? See, one thing is very clear, that this white area plus yellow area is entire A. White area plus yellow area is A. White area and yellow area are mutually exclusive, and their sum is equal to probability of A. So we can use that. Probability of A is what? Probability of A is probability of A intersection B complement plus probability of A intersection B. You have to agree on this. Right? Since A intersection B complement is this area, A intersection B is this area, probability of A is what? Probability of A intersection B complement plus probability of A intersection B. So, what does it mean? Probability of A is probability of A intersection B complement plus probability of A intersection B is probability of A into probability of B. So here, if you take this to LHS and this to RHS, you will get probability of A intersection B is what? A intersection B complement is what? Probability of A you can take out. It will become probability of... Okay, here you will have to shift this side. Okay, so it will become... Okay, yeah. 1 minus probability of B. Okay, you can rearrange. It will be very easy. You have to take this entire term this side. So what does it mean? Probability of A intersection B complement is probability of A times probability of B complement. We know that 1 minus probability of B is probability of B complement. So hence proved. Since probability of A intersection B complement is probability of A times probability of B complement, A and B complement are also independent of each other. Okay, and similarly, these two problems are symmetrical to each other. Instead of this area, if you take this area, B intersection A complement, you will get this theorem as well. Okay, consider this homework. Okay, if you take this area, this will also be proved. This is slightly tricky. So here you want A complement and B complement. So how will you prove this? So here the Venn diagram looks like this. A, B. You are given this area, but you are interested in some other area. You are interested in A complement and B complement, which means the elements which are not in A and they are not in B, which means this area. These are not in A and not in B. So how will you get this? So it is very obvious that probability of A complement intersection B complement is what? See, the set A complement intersection B complement is nothing but A union B complement. Right? It's a form of De Morgan's law, right? This is A union B. A union B is all this area. Whatever is not in A union B is not in A and not in B. So this is true. So probability of A intersection A complement intersection B complement is probability of A union B complement, which is what? 1 minus probability of A union B. Okay, and we know that what is probability of A union B? You just expanded, it is probability of A plus probability of B minus probability of A intersection B. We know this, okay, inclusion, exclusion. So this is what it is, okay. So what do we want? Okay, we want to expand this only. We want this to be proven to be probability of A complement into probability of B complement. So what is this? It is 1 minus PA minus PB minus P A intersection B plus P A intersection B. And P A intersection B is nothing but PA plus PB. So plus PA into PB. So this entire term is nothing but 1 minus PA into 1 minus PB. Right, if you multiply these, you will get these 4 terms. So this is nothing but P of A complement into P of B complement. So hence proved. Since probability of A complement intersection B complement is probability of A complement into probability of B complement, A complement and B complement are also independent of each other. They will all be independent, okay? Cool. These type of these exams will be useful in these type of examples. So if two people A and B are interviewing for a job and the probability of their selection is this. So probability of selection of A is half, probability of selection of B is 1/3. So what is the probability that? What is the probability that both of them are selected? So we are given that probability of selection of A is 1/2 and probability of selection of B is 1/3. Okay, obviously they are independent of each other. Given that A is, nothing is mentioned, right? So it is just said that probability, so here you have to assume nothing is given. So definitely they are independent of each other, right? Probability of selection of first guy is half, 50%. Probability of selection of other guy is 1/3. If first guy gets selected, it doesn't matter, like it doesn't matter, right? The probability of still getting selection of second guy is still 1/3. So they are independent of each other. So what is the probability that both of them are selected? It means probability of, so let's say event E1 is, okay, we are already given events A and B. So if, what is the probability that both of them are selected? It is like probability of A intersection B. A is selected and B is selected. So it is probability of A into probability of B, 1/2 into 1/3, 1/6. Exactly one of them is selected. Exactly one of them is selected. It means that A gets selected and B is not selected. Or B is selected, A is not selected. A is selected, B is not selected. Exactly one of them. Or, so again we have an OR, rule of sum. So we already know that if A and B are independent, A and B complement will also be independent. Right? See, it is very logically interpretable as well. If happening of B doesn't, basically what does it mean when we say A and B are independent? Ki if B happens or not, probability of A will remain same. So that's what it is, right? If B happens, probability of A will remain same. If B doesn't happen, then also probability of A remains same, right? So A and B are independent, then A and B complement are also independent. B happens or not happens, doesn't matter, probability of A remains same. So these two are also independent. So what is the probability of A getting selected and B is not selected? It is probability of A into B complement is 2/3. Or means plus B is selected 1/3 and A is not selected, it is 1/2. Okay. So it becomes 3/6 or 1/2. Exactly one of them gets selected. And third is, at least one of them is selected. At least one of them is selected. What does it mean? Either A is selected or B is selected or both are selected. So there will be 3 cases. Better is you just do 1 minus none of them selected. There are 4 cases, okay? Both are not selected, A is selected, B is selected and both are selected, right? Here you want at least one of them to be selected. So it is nothing but 1 minus, none of them are selected, which means 1 minus A is also not getting selected, B is also not getting selected. So it is nothing but 1 minus, what is probability of A not getting selected? 1 by 2. What is probability of B not getting selected? 2 by 3. So 1 minus 1 by 3, it is 2 by 3. So 2 by 3 is this, 2 by 3, 1 by 2 and 1 by 6. Okay. Cool. So this concludes this slide. We will have one more lecture on independent events. We will see independence of 3 events and a few axioms on that and a few examples which are already asked in GATE. Independent events is a big topic. Most of the questions in probability comes from conditional probability and independent events. That's why we're taking a long time in learning this. So we'll solve a lot of examples in the next class and we will see a few more theorems. Hi everyone. Welcome to lecture number 5 of GATE DA course under probability and statistics. So in last lecture we saw independent events, and 2 events A and B are independent if probability of any one event doesn't affect, or basically happening of any one event doesn't affect the probability of other event, which means the probability of A given B has already happened is probability of A, and similarly probability of B given A has already happened is probability of B only. And if we rearrange terms, probability of A intersection B, which means probability of happening of both events, is just the product of individual probabilities, or PA into PB. And we saw a few axioms on it as well, like if A and B are independent, then A complement and B will be independent, and A and B complement will be independent, and similarly A complement and B complement will also be independent. They are very important and we will see a few questions on that as well in this lecture. So this was the notion, if 2 events are independent if this condition holds. So now let's see an axiom. Okay, prove that an event A is independent of any event if probability of A is 1 and also probability of A is 0. So which means that when is probability of A 1? Probability of an event A is 1 if probability A is like A is the sample space itself. It means it is just saying that sample space is independent of any event. So it is given that probability of A is 1 and it is saying that it will be independent of any event B. So let's say there is an event B. It can have a probability of PB. So it doesn't matter what event B is, event A will be independent with any event. Okay. So what does it mean? So in Venn diagram, this is A. Basically A is the entire universe. There is nothing which is not A. Actually I should draw it like this. If this is the universe is equal to A also, right? Because there is nothing which is outside A. Probability of A is 1 and B will be somewhere here, right? So what will be probability of A intersection B? See, what will be probability of A intersection B? Since probability of A is 1, A always happens. So probability of B is just probability of B only. A intersection B is what? It is B only. Since B is inside A intersection B is only B only, right? So probability of A intersection B is nothing but P, or probability of B. And we can always multiply 1. So it is also probability of B into probability of A. We are just multiplying it by 1. Probability of A is 1. So that's why if probability of A is 1, A will be independent with any event. Similarly, an event which can never happen. See, it is just like saying that an event which always happens will be independent of any event. It is like saying that, let's say you are throwing a die, right? And what is the probability of getting an odd number? It is 1 by 2. And now someone is saying that another event happened in which you got a number between 1 and 6. It is sure that you got a number between 1 and 6. We already knew we will get a number between 1 and 6. The probability won't change, right? So if someone is saying that universe happened, universe always happens, right? Like sample space will happen. So that's why it will be independent with any event. Similarly, second statement saying that nothing happened. It is like this is slightly like illogical. Like it is saying that an event which can never happen will be independent of any event, right? So what does it mean? In second case, probability of A is 0. So A can never happen. In this case, how the Venn diagram looks? This is universe, this is A. Basically, like A is nothing. A is nowhere. A is an empty set. And this is B. So since A is an empty set, A intersection B will also be an empty set. There is nothing in common. So probability of A intersection B will also be 0, which is probability of A times probability of B. Right? Since probability of A is 0, you can multiply 0 to anything, you will get 0 only. So that's why an event which can never happen is also independent of any other event. And this we have already seen that mutually exclusive events are always dependent if they have non-zero probability. So if there are two events which are mutually exclusive, so which means they have non-zero probability also, like it is given that they have non-zero probability also, which means that probability of A is not 0, probability of B is not 0. And now it is given that since they are exclusive, probability of A intersection B will be 0. So it can never be equal to probability of A into probability of B since they are non-zero. So if two events are exclusive and they have non-zero probability, they can never be independent, they will always be dependent. This we have already seen in last lecture, right? So these were a few axioms on independence of two events. Now let's see independence of three events. So this is slightly tricky. So we know that two events are independent if probability of A intersection B is probability of A into probability of B. Now three events A, B and C are independent if all of the following conditions hold. All the conditions should hold, which means A and B should be independent of each other, A and C should be independent of each other, B and C should be independent of each other, and A, B, C, which means probability of A intersection B intersection C should also be equal to PA into PB into PC. So this is like a definition, right? Like you will not see the proof, like that's not required. Like three events are independent if all the conditions hold. Well, if any one of the condition doesn't satisfy, three events are not independent of each other. Okay, that's a very some people just only check this condition. That's a common mistake. Since in two events also you only check one condition, but that's not the case here. Okay, three events are independent if all the conditions are true. So you have to check the independence of AB, AC, BC and ABC. Okay, then only three events will be independent of each other. So for example, if we see this experiment, a ball is drawn from a bag containing 4 balls. A ball is drawn from a bag containing 4 balls numbered 1, 2, 3, 4 with each outcome equally likely. So there is a bag containing 4 balls 1, 2, 3 and 4. Now event E is getting 1 or 2. So you're just pulling out one ball at random. So what is the probability of E? Probability of E is 2 by 4, which is 1 by 2. Similarly, probability of F is getting 1 or 3, which means again like 2 by 4, which is 1 by 2. What is probability of G? Again 1 by 2. Okay. Now what is the probability of E intersection F? What is common in both E and F? There is only one element common in E and F, which is 1. So it is like 1 by 4. Similarly, probability of E intersection G is also 1 by 4. There is only one element common. And probability of F intersection G is also 1 by 4. There is only one element common. And what is probability of E intersection F intersection G? We have to check 4 conditions here, right? What is probability of E intersection F intersection G? There is still one element common. There is still one element common, which is 1. So it is again 1 by 4. So is probability of E intersection F equal to probability of E into probability of F? Yes. They are 1 by 2 each. So E and F are independent of each other. Similarly, is probability of E intersection G equal to probability of E into probability of G? Yes. Since they are both 1 by 2, so E and G are also independent of each other. Is probability of F intersection G equal to probability of F into probability of G? Yes, because they are also 1 by 2. So F and G are also independent of each other. They are all pairwise independent. Now, is probability of E intersection F intersection G equal to probability of E into probability of F into probability of G? Is this correct? No, because probability of E into probability of F into probability of G is what? 1 by 2 into 1 by 2 into 1 by 2, 1 by 8. It is not true. So that's why E, F and G here are not independent of each other. These three events are not independent of each other. Only they are pairwise independent. E and F are independent, E and G are independent, and F and G are independent. Okay, but they are not all independent of each other. All the conditions should hold. Okay. Cool. Now, given the independence of three events, we have some difficult theorems to prove. Okay. If A, B and C are independent, okay, this is very tricky now. All these conditions will hold. Like if A, B and C are independent, A union B and C are also independent. Similarly, A complement union B and C are also independent. A complement, you can take complement anywhere and take union of two sets. A complement, union, B complement and C are also independent. And all three, A complement, B complement, C complement are also independent of each other. So what does it mean? So whenever you have to prove something like this, like see, lots of variations can be asked. Whenever you have to prove, just draw the Venn diagram and try to find the intersection set and try to find the probability, okay? So it is given that A, B, C are independent. It means that the four conditions hold. A and B are independent, B and C are independent, A and C are independent, and P of A intersection B intersection C is equal to PA into PB into PC. All these four conditions hold. Now you want to find this. You have to prove that these are independent or not. So what does it mean? You just have to calculate the probability of A union B intersection C. That's what you want. This is one event now. A union B, let's say, is E. Then you have to prove that E and C are independent or not, which means that probability of E intersection C should be equal to PE into PC. That is your aim. That is what you want to prove. The probability of E intersection C should be equal to probability of E into probability of C. Now, how will I get this? So here you can apply the distributive law. So intersection gets distributed inside, right? So this will be nothing but probability of A intersection C union probability of, so it's like, this is nothing but probability of A intersection C union B intersection C, right? I just distributed intersection inside, like standard set theory laws. So you can also see it using Venn diagram. This is A, this is B, this is C. What do we want? A union B, it should be in A or B and it should be in C, which means that it should be in A and B and it should be in C. So A union B is what? This entire set. And also intersection with C is this set. So it is nothing but intersection of union of A intersection C and B intersection C. You see the union. This is exactly correct using Venn diagram. So what is it? Okay, we can just apply the De Morgan's law. We can just expand union, inclusion, exclusion. So it is like probability of A intersection C plus probability of B intersection C minus probability of A intersection B intersection C. Right? Just expanded the union. So what is probability? So we know that probability of A intersection C is probability of A into probability of C. Since A, B and C are independent, these are independent, and this is independent. So this is nothing but probability of B into probability of C minus this is nothing but probability of A into probability of B into probability of C. Now you can just take probability of C out. This will become probability of A plus probability of B minus probability of A into probability of B. Right? See, we are getting where we want. This is probability of C times. We know that since A and B are also independent, we can write probability of A into probability of B as probability of A intersection B. So this is nothing but probability of A plus probability of B minus probability of A intersection B. Now this entire thing is nothing but A union B. Again, inclusion exclusion. So it is nothing but times probability of A union B. That's what we wanted. So we have proved that this is equal to this, which means that these two are independent of each other, right? So similarly, I can prove one more. So just do the expansion and like you will be good to go. Okay, like the same way you can prove the other theorems as well. We will not prove all of them. Let's try second also. What is probability of A intersection union B intersection C? Here also you can apply the distribution law. So it will become probability of A intersection A complement intersection C union B intersection C. Okay. So it is nothing but like you can just write it probability of A intersection A complement times probability of C plus probability of B times probability of C minus probability of A complement times probability of B times probability of C. And here also you can take probability of C as common and you will get probability of A complement plus probability of B complement plus probability of B minus probability of A complement times probability of B. Now here this will be slightly tricky. Now since we know that A and B are independent, from the previous lecture we know that A complement and B are also independent, right? If A and B are independent, A complement and B are also independent. So we can write this as A complement intersection B, and again we will get the same theorem. Okay. So similarly you can prove the others as well. I will not do it. Consider these two as homework, and in the doubt solving session we will see like if you have doubts. So all of these will be independent if A, B and C are independent. Okay, it's easy to prove. Just apply a few set theory laws and you'll get the results. Cool. Now this is an example on the same independence of three events. So given that A, B, C are independent and their individual probabilities are given, you need to find this. So we know that if A, B, C are independent, A union B complement and C are also independent. In the last lecture, last slide we saw that. We know that you can take union of two sets and add complement anywhere, it doesn't matter, right? So A union B complement and C are also independent, which means that that's what we want. We want to find the probability of A union B complement intersection C. That's what we want. This is nothing but probability of A union B complement times probability of C. Now you can expand this. This will become probability of A plus probability of B complement minus probability of A intersection B complement times probability of C. So it is nothing but probability of A plus probability of B complement minus. Now since A and B are independent, since A, B, C are independent, A and B are independent. Now if A and B are independent, A and B complement are also independent using last lecture. So this will be nothing but probability of A times probability of B complement times probability of C. Now we know each of these terms. We know PA, PB complement, PA, PB complement, PC. We know all of them. Everything is given. If PA is half and PB is 1 by 3, P of B complement is nothing but 2 by 3. 1 minus PB. So it's that. Okay, so you can very easily calculate this expression. And coming to the second example, what is probability of A complement intersection? We know that if A, B, C are independent, A complement, B complement and C complement are also independent. What does it mean? This is nothing but probability of A complement times probability of B complement times probability of C complement, which is half into 2 by 3 into 3 by 4, which is 1 by 4. Okay. So we are just applying the standard axioms of independence. Okay. Similar to 3 events, we can have independence of n events. So now it will be like very tricky. So when independence of 3 events, you have to hold 4 conditions. If you have to have independence of, let's say 4 events, I will tell you. Let's say you want to, very easy, okay. A, B, C, D are independent if they are pairwise independent, they are triplet-wise independent, and all 4 are independent, which means that A intersection B should be equal to PA into PB. And similarly, A intersection C, all pairwise, AB, AC, AD, BC, BD, 6 pairs, CD, okay. And then triplet wise also it should be true, which means that A, B, C should be independent, which means that PA intersection B intersection C should be equal to PA into PB into PC. Similarly, you should have A, B, D also true and B, C, D also true. Okay. And there is one more, right? 4C3 is 4. ABC, ABD, ACD and BCD. Okay. So these 4 conditions should also be true. And also all 4 should be independent, which means that PA intersection B intersection C. So all possible cases which you can think of, which means taken 2 at a time, 3 at a time and 4 at a time. So if you have a sample size of n, like if you have n events, then NC2 plus NC3 plus NC4 and so on up to NCN. These many conditions have to hold true, right? Which is nothing but 2 to the power n minus n. Okay, you can prove that. So all these conditions have to be hold true. So if for n events A1, A2 up to An are independent if they are pairwise independent, they are triplet wise independent, and so on, they are all independent. Okay. This is just need to know basis. GATE has not asked question on like independence of more than 3 events, but like you should know. Okay, like all the conditions hold, then only they are all independent, otherwise not. Cool. So this is GATE 2000 question. E1 and E2 are events in probability space satisfying the following constraints. So it is given that probability of E1 is equal to probability of E2. And it is given that probability of E1 union E2 is given to be 1. And it is also given that E1 and E2 are independent, which means that probability of E1 intersection E2 is probability of E1 times probability of E2. These 3 things are given. Now what is the probability of E1? So let's say the probability of E1 is X. Let's say the probability of E1 is X. So what is this? So what is probability of E1 union E2? It is probability of E1 plus probability of E2 minus probability of E1 intersection E2. Right? Now probability of E1 is X. And probability of E2 is equal to probability of E1. It is also X. Minus probability of E1 intersection E2 is probability of E1 into probability of E2. They are both X. So X into X becomes X square. Now this is given to be 1. This union probability is given to be 1. So what does it mean? It becomes an equation. X square minus 2x plus 1 is equal to 0. Which means that x minus 1 whole square is equal to 0. It means that x is equal to 1. X has to be equal to 1. There is only one solution. So the probability of E1 is 1. Okay. Standard, like I just applied the equation, like we know that E1 union E2 is what, and then the independence, everything was given. Cool. Cool. This is another example asked in GATE 2003. Let PE denote the probability of event E. Given that PA is 1, PB is half, the values of PA by B and PB by A are. Okay, very easy question. I already told you that if probability of any event is 1, it will be independent of every event. Probability of an event A, if it is 1,
it will be independent of every event. Axiom which we saw, okay, in the first slide. If probability of any event is 1, it is independent of any event, which means that A and B here are independent of each other. It means that it doesn't matter. Basically, A and B are independent, which means that probability of A given B has already happened will be equal to probability of A only, and also probability of B given A has already happened will be probability of B only. Even if you don't remember the axiom in the exam, we know that probability of A given B has already happened is probability of A intersection B upon probability of B. Now since probability of A is 1, probability of A intersection B will be probability of B only, and you can apply the formula, okay? So the first thing is probability of A only. Probability of A is 1, so this thing is 1, and probability of B by A is probability of B, which is half. So 1 comma half. Okay, it is based on the axiom that we have seen. Cool. So this concludes independent events. Like we have seen, like this is the major portion in probability. Like most of the questions come from independent events, condition probability, and multiplication theorem. Now we will see some more complicated stuff like Bayes theorem in coming classes, and also there are a few notations in probability like total probability, joint probability, and marginal probability. We will see all this. Very important concepts and theorems coming up in the coming sections. Okay.
Hi, most of you might be knowing Jay Bansal. For those who don't know Jay Bansal, let me introduce him one more time. So, Jay Bansal is AAR2 ranker in GATE 2019. Then he has got his MTech from IIT Bombay, and he is a 9.93 pointer. And then he is currently working in Google, so on large language models. So now in this video, Jay will explain you about. So one more thing, why am I introducing Jay Bansal is because he is going to teach. So he is going to teach GATE DA completely, and I will also be there in the course, but primarily he will be teaching the entire course. So now Jay Bansal will explain you what is the plan, what is the syllabus, how we are going to upload the videos, how we are going to solve the doubts, everything Jay Bansal will explain. Over to you, Jay.
Thanks, sir. So hi everyone. Sir like has already introduced me, and like right now I'm working as an ML engineer at Google. So yeah, I know like bits and pieces of like the entire course. We use this every day in our like day-to-day life at Google. So
and one more thing is he will give the industry perspective of to the course. He will bring that industry perspective to the course. It will not be only theoretical. He will also talk about how it is applied in the real industry as of now.
Yeah. So yeah, this is the new paper like introduced by IISc Bangalore. This time IISc is like conducting the GATE exam 2024, and they have added a new paper which everyone was waiting for, which is data science and artificial intelligence with the code DA. So a lot of colleges right now already have a bachelor's course, like they have introduced a bachelor's course in data science and AI. So you might like hear like in almost every college, even in IITs, we can get a BTech or BSc done in AI. So like this is an initiative, and like from now we will have MTech courses also specialized in AI only, and the admissions to those courses will be through DA paper. And one special thing, like any branch student, like so you can go to GATE website and see about 2 paper modes. So you can actually write 2 GATE papers. So even if you were preparing for GATE CS only this year, you can still write DA also. So you can actually write 2 GATE papers. Any student like CS, electrical, mechanical, civil engineering, you can write DA as your second paper, and you can have a career in artificial intelligence. So yeah, this is the syllabus. It's very small syllabus. Like it's the smallest syllabus of all. Like you can see any syllabus. Like mechanical is huge, computer science is huge. But this is the smallest syllabus, so you will need the like least amount of time to prepare for it. And like if you love math, like this will be easy. Like this is all about maths. You can see like large portion of the syllabus is only on maths. So like almost 50% of the syllabus is maths. So yeah, and like they will ask a lot of questions on probability, linear algebra, calculus, because these are all basics coming to any ML algorithm. So we actually learn this and apply all this information in machine learning and AI. And these 2 you can see are directly from GATE computer science. This is maths. And these 2 are only ML and AI. Like these are the only things which you need to learn new. So this is about like 25-30% of the syllabus, that's all. So if you are doing GATE CS, already you are learning all this. You just need to learn a bit more to crack GATE DA. So, and also I will like in this course, we will be covering all of this from scratch. We will be discussing every concept on YouTube on this channel. So I'll be starting with probability and stats. I'll follow the syllabus and cover each and every bit of it. And so one video will be released every day on this YouTube channel, starting tomorrow. And we will be covering we will be starting with counting, PNC. And actually you have learned most of it in GATE CS. A few things are introduced more. So these confidence intervals, Z test, and chi-square test, these are introduced, these are new topics coming to GATE DA. So, and since I told you, since maths is most of the part in GATE DA syllabus, so you can expect more questions from maths. Generally, in GATE computer science, 15 to 20 marks portion come from mathematics, right? But here you can expect around 40 marks. That's what I see. So yeah. So anyways, we will cover everything needed because we need this basics. You need to be very thorough in these. Otherwise, you'll have a difficult time learning ML and AI. So we'll cover probability and stats, linear algebra, calculus, programming DA and algo. This is exactly same as GATE CS. The only thing is the questions will be from Python. So this had to be introduced because most of the ML algorithms are easier to write in Python programming language. So ML work is done all in Python. I work on Python every day. So I used to work in C++ while I was in college, but after MTech it's all Python. So yeah, the questions will be from Python, and you can expect that even the DSA questions, the code snippets, will be given in Python only. And database is entirely from GATE CS, and these two are the new additions, and we will be having we will be covering everything.
In warehousing, some topics are added.
Yeah, actually yes. So so this is mainly because so why actually they have added databases in the syllabus. So you might have heard of the thing called big data, right? And ML models, why do we write? See, you can if you have a Google sheet, let's say, with 10 entries, one person can manually sit and do all the ML. Think about it. If you have 10 entries, I can sit and tell you all the insights. This is the anomaly. This is something. You can actually, humans can do all the ML. That's what ML is. You are giving human mind to a machine, right? So, but why are we writing algorithms? Because the data is huge. One person cannot sit and see 10 million entries, right? Think about Google search. There are 5 billion Google searches, I guess, in a day. So you cannot manually go and see every search, and have personalized search ads or anything, right? So you need ML in that. You need to actually access large amounts of data. And this is the first step in any ML project. You need to store the data, and that's where we need large data warehouses and database management. So this is important, and we will learn this as well.
Compare it with GATE computer science syllabus.
Yeah. So yeah, this is GATE CS syllabus. It's a 2-page syllabus, and this is the only maths part. If you see, right? And even in GATE DA, we don't have all the topics of discrete maths. We don't have set theory, monoids, groups, graphs. We don't have that, right? Because that is very core to GATE computer science. We only have counting. See, ML is all about counting. You have lots of data. You want to count how many entries. So these random variables can be dependent or can be independent from each other. So now we have various probabilities associated with it. For example, what is the probability? What is the probability that the random variable x is greater than the random variable y? This is a problem now. You have to get a larger number on the first row than the second row. Okay? So this is the difference between random variable and an event happening. And the concept of joint marginal condition probability work on random variables differently. So we will explain, I'll explain what a joint probability distribution is and how random variables, different random variables get associated to each other. So there are 3 main types of probability
we consider when we talk about multiple random variables? We talk about joint probability, we talk about marginal probability, and we talk about conditional probability. So what is joint probability? It is the probability of events A and B both happening. So for example, here in this example, probability, let's say I tell you, let's say the event A, forget about these events A and B. I'm creating new events A and B based on the random variables X and Y. Let's say the event A is getting an odd number on the first die. Odd number on the first die. It means that X has to be equal to 1, 3 or 5. And let's say the event B is getting a prime number on the second die. Okay, we know that these events are independent because like throwing a die, the two events are always independent of each other. So these two events will be independent of each other. That's okay. They might or might not be independent. But what is the joint probability? Joint probability will be probability of A is happening and B is also happening. A and B. So we write it like this. So basically it is like probability of X being inside odd, which means 1, 3 and 5, and Y is prime, which means Y has to be 2, 3 or 5. Okay, this is joint probability. Probability of happening of both the events. What is marginal probability? Probability of only, so we only consider one random variable in marginal probability. It doesn't matter what the other random variable is doing. Okay, what the value the other random variable is getting, it doesn't matter. Combining all the values which other random variable can get, what is the overall probability of happening of one random variable? That's all. That's marginal probability. Okay, with example it will be much more clear. In the next slide we will see an example. And conditional probability we already know. Okay, what is the probability of event A given B has already happened? So given that the random variable Y was this, like let's say given that the random variable Y is 3. Now what is the probability that the random variable X is 2? So if these two random variables are independent of each other, then it doesn't matter what the value of Y is, okay? Probability of X will remain same. But if they are dependent, it might change. So this is what conditional probability is. So now let's see an example. With this example, everything will be very clear. So let's consider two random variables X and Y and their joint probability table. This is called a joint probability table. Okay, what it means? Joint probability table will always contain joint probability values. So which means probability of X being 1 and Y being heads is 1 by 12. Probability of X being 2 and Y being tails is 1 by 12. So this is what joint probability table means. Basically writing all possible joint probability values for all random variables. Okay, so it will have all the values possible. So here we have two random variables X and Y. So the random variables are, what we are doing here, so the joint probability table shows the probability of each combination of values for X and Y. And the random variables are, X is the result of rolling a fair 6-sided die. So you are rolling a 6-sided die and the whatever value you are getting, that is X. Okay, so this is an experiment. You are rolling a 6-sided die and whatever value you are getting is the random variable X. We know that the possible values are 1, 2, 3, 4, 5 and 6. Similarly, random variable Y is like this. It is the outcome of flipping a fair coin. So now you flip a fair coin. It's like unrelated to what you were doing before. Okay. And here we know that the possible values are only heads and tails. Right. So now what happens? We know that probability of getting a 1 on the fair die and getting a heads on on flipping the fair coin will be what? So it is like probability of X being 1 and Y being heads. It is the intersection, and means intersection, right? Now it is very obvious in this example that X and Y are independent of each other, right? Which means that it doesn't matter what you're getting on the flipping of coin. It doesn't matter what you're getting on the flipping of coin. The value of die doesn't matter. So that's why this will be probability of X equal to 1 times probability of Y being heads.
Okay, this we already know from the definition of independent events, which means what is the probability of x being 1? It is 1 by 6. And what is the probability of y being heads? It is 1 by 2. So it is 1 by 12. And similarly, for any possible combination, the value will be always 1 by 12. So basically what we did, we created probability of every joint possibility. Probability of events A and B. So we basically have written down in this table all possible outcomes for both the variables. And observe that at least one of them will always happen. So that's why the sum of all this probability will always be equal to 1. In a joint probability table, if you are writing all possible random variables and all possible joint values, then the sum of all these values will always be equal to 1. So here it is the case. So this is called the joint probability table. Cool. Now we will see all the different terms. So the first term is joint probability. Obviously, it is very simple. Again, if joint probability table is given, calculating joint probability is very easy because this table contains joint probabilities, right? So for example, here, probability of x being 3 and y being heads. This is called joint probability of event A and B. Here A is getting a 3 on the die and event B is getting a heads on the fair coin. Okay. So here, if you want to calculate the joint probability, just look at the table. X being 3 and y being heads. It is 1 by 12. Okay. So sometimes what can happen here, the problem was much simpler. The dice was also fair and the coin was also fair. But sometimes the problem might be like complicated, and these events can be dependent on each other as well. Here they were independent, so that's why it was easy. Cool. So calculating joint probability is easier, right? Just see the table and just mark the values and you will get the answer. Now coming to marginal probability. So marginal probability is the probability of a single event. Marginal probability is the probability of a single event without considering the occurrence of any other events. So what happens is, always we talk about these things. We talk about these things only when we have multiple random variables, that we have already seen, right? We will have 2 or 3 random variables. So it doesn't matter what the value of other random variable was, you sum up all possible such values. Now you want to calculate the probability of only one random variable. For example, here, probability of x being 3. This is called marginal probability because we are not giving you the value of y. We are not giving you the value of y. We only worry about the value of x. That's why it is called marginal probability. So how to calculate that? Just go to the x equal to 3 row and sum all these values. It doesn't matter what y is. Y can be heads, tails. You can have 3-4 more values. It doesn't matter. If you want to calculate marginal probability, just sum the entire row. 1 by 12 plus 1 by 12. It will be 1 by 6. And we already knew the probability of x being 3 will be 1 by 6, right? Because it doesn't matter what we get on the like on the coin. Probability of getting a 3 on die is 1 by 6. So that's how you calculate marginal probability. You can calculate one more. So what is the probability of y being tails? If you have to calculate for other random variable, that is also possible. It doesn't matter what x is. So you sum all these values. You sum all these values and you'll get the probability of y being tails. So you sum all this, you'll get 1 by 2. Right? Now coming to conditional probability. So conditional probability we already know, right? It is probability of happening of one event given that other event has already happened. See, that's the biggest mistake that I have seen like a lot of students make. Joint probability table doesn't contain the information of conditional probabilities. You can calculate them using that table, but directly here the values don't represent conditional probability. This value 1 by 12 here is not the conditional probability of x on y. It is the joint probability. It is probability of x being 3 and y being heads. It is not probability of x being 3 given y equal to heads. Okay, this is different, this is different. And means intersection. This is conditional probability. Okay, so the joint probability table contains joint probabilities, not conditional probabilities. Conditional probabilities you will have to calculate. In this example, this value will also be equal to this value. In this example only, this value is equal to this value because x and y are independent events. They are independent random variables. It doesn't matter what happens to y, like the probability of x remains same. But in most of the example, this will not be the case. Then you will have to calculate the condition probability, right? So what is condition probability? Let's say I want to calculate probability. So let's say I want to calculate probability of, here we have an example. Let's say I want to calculate probability of y being tails given x is equal to 4. Okay. What is the probability of y being tails given x is equal to 4? So we know that it will be by formula. Just go by formula. What is the condition probability formula? We know the probability of A given B has already happened is probability of A intersection B upon P of B. Right? This we already know. So it will be probability of y being tails and x being 4 upon probability of x being 4. So the conditional probability is equal to the joint probability upon marginal probability. See, now we are getting all the terms, right? This is joint probability. This is marginal probability. So how to calculate the probability of y being tails and x being 4? Y being tails and x is equal to 4. So it is 1 by 12. And what is the probability of x is equal to 4? X is equal to 4. How to calculate the marginal probability? Sum all the values. 1 by 12 plus 1 by 12. It is 1 by 6. So it is 1 by 2. So what is the probability of y is tails given x is already 4? It is 1 by 2 only. In this case, see, it is not equal to the joint probability here. It is not equal to the joint probability of y equal to tail and x equal to 4. That was 1 by 12. But here we are getting 1 by 2. Right? So marginal probability, joint probability is different from conditional probability. And also here, only in this example, this is also equal to probability of y being tails. Right? Why? Because these two events are independent from each other. So when A and B are independent, we know that P of A by B is equal to P of A. Here it is the case. That's why they are independent from each other. Okay. Next, so I will take an example in which the events are not independent also. Okay. There it will be more clear. So I hope you got the concept. Joint probability, marginal probability, and conditional probability. Now let's see like another complicated example. Here it is not given that x and y are independent or not. Okay, if it is not given x and y are independent or not, we will calculate it. Okay, so you are given two random variables x and y, and we are given the joint probability distribution. It is also called the joint probability mass function. It is same as probability distribution. Okay, later when we see random variables in detail, we will have like in probability, this is basic probability. Okay, we will have random variables in detail. There we will see what probability mass function and cumulative distribution, all these are. We have in what discrete random variables are, what continuous random variables are. For now, just assume that joint PMF is nothing but joint probability distribution. Okay, so basically all these values denote the joint probability of x being 2 and y being 4. It is 1 by 12. Okay. So this is the joint probability distribution given. You can see that the sum of all these values will be 1. Okay, and so what is the joint probability of, let's say, x being 2 and y being 4? It is 1 by 12. This value. Okay, so this is called joint probability. Now you want to find, so the question is, you want to find probability of x being less than equal to 2 and y being less than equal to 4. That's the question asking. So basically, it's not just a single joint probability. Here, so x can be less than equal to 2 and y can be less than equal to 4. So there are multiple such possible options. So basically, x can be 1. See, the possible values of random variable x are given to be 1, 2 and 3, and for y they are given to be 2, 4 and 5. That is okay. So what they are saying is x has to be less than equal to 2. So x can be either 1 or 2, and y has to be less than equal to 4. So it can be either 2 or 4. So what are the possible combinations for x and y which will obey this probability? So the possible options are x being 1 and y being 2, or x can be 2 and y can be 2, x can be 1, y can be 4, and x can be 2 and y can be 4. These four combinations satisfy the condition given. So basically we have to sum all the probabilities, these 4 joint probabilities basically. So these are the 4 probabilities. In these 4 probabilities, in these 4 joint probabilities, the condition is satisfied, which means x is also less than equal to 2 and y is also less than equal to 4. So we just sum all these 4 values. So we will get 1 by 12 plus 1 by 24 plus 1 by 6 plus 1 by 12. So the denominator becomes 24. 2 plus 1 plus 4 plus 2. 9 by 24, which is 3 by 8. Okay, so this is the probability of x being less than equal to 2 and y being less than equal to 4. Cool. Now the next question is find the marginal probability distribution of x and y. So basically they want to find the, like here in this question we want to find the marginal, all the marginal probabilities of x and y. Basically probability of x being 1. This is the marginal probability of x being 1. Then we have marginal probability of x being 2, x being 3, and similarly marginal probability of y being 2, y being 4 and y being 5. The question is asking you to calculate all of them. I will just do 1 or 2 and the rest you can do it, okay? So what is the marginal probability of x being 1? You just sum this entire row. Okay, so it will be 1 by 12 plus 1 by 24 plus 1 by 24. So it will be 2, 3, 4, 4 by 24, which is 1 by 6. Very easy, right? Marginal probability. What is the probability of x being 1? You just sum this, this and this, because y can be anything. It can be 2, 4 or 5. You're summing all these up. Similarly, like let's calculate one more. What is the marginal probability of y being 4? So you want y to be 4. So you just sum this entire column. So it is 1 by 24 plus 1 by 12 plus 1 by 8. So it is denominator will be 24. 1 plus 2 plus 3, 6. So it is 1 by 4. Okay, you sum all these values. So similarly, you can calculate all other marginal probabilities as well. Okay, I just calculated 2. So here is the answer. You can take a note. So we calculated probability of x being 1 to be 1 by 6, which is correct. And we calculated probability of y being 4 to be 1 by 4, which is correct. Okay. Similarly, you can calculate the other marginal probabilities as well. Cool. Now let's look at the next question. Here you need to find the probability of y being 2 given x is 1. Again, most people make a mistake. They will just directly say it is 1 by 12. No. What is 1 by 12? 1 by 12 is the joint probability. Probability of x being 1 and y being 2 is 1 by 12. Here we have to calculate something else. Here we have to calculate probability of y being 2 given x is 1. Interesting problem, right? Like this is conditional probability. So just go with the formula, okay? It's very simple. Like we know how to solve it. Nothing to worry about. If you read the statement, calculate carefully, it will be very simple. So what is this? What is P of A given B? It is P of A and B upon P of B, which means probability of y equal to 2 and x equal to 1 upon probability of x equal to 1. I told you conditional probability is nothing. It is joint probability upon marginal probability. That's what you're getting here. What is the probability of y being 2 and x equal to 1? This is 1 by 12. And what is the probability of x equal to 1? You just sum the first row. We already did it, right? It was 1 by 6. You just sum the first row. So this is what the conditional probability of y being 2 given x is 1. See, this is interesting problem, right? Given that x is 1, so only these 3 cases can happen. Now your sample space reduced. Your sample space is only these 3 values. Among these 3 values, only this was interesting for you. That's why it was 1 by 12 upon 1 by 12 plus 1 by 24 plus 1 by 24. Okay, it's very logical. So what is this? This will be 6, 12, 1 by 2. Cool. So this is the conditional probability of y being 2 given x is 1. 1 by 2. See, now can you calculate what is probability of y being 2? That's all. I want to see these 2 events are independent or not. So I will just calculate probability of y being 2. If that is also 1 by 2, then these two events will be independent, right? What is the probability of y being 2? You just sum the first column. So it is 1 by 12 plus 1 by 6 plus 1 by 4. So the denominator will be 12. 1 plus 2 plus 3. So it is 1 by 2. It is correct. Probability of y equal to 2 given x equal to 1 is equal to probability of y equal to 2. Which means that these two events are independent from each other. Only we can say that. We cannot say that the random variables x and y are independent. For random variables x and y to be independent, all possible such combinations should be true. Basically, like none of the variables should be dependent on each other. Right now, we only know that probability of y being 2 is independent from probability of x being 1. It can be possible that probability of y being 2 is dependent on x being 2. Okay, it is only independent of x being 1. But yeah, that is correct. Okay, so the probability right now which we wanted to calculate was 1 by 2, and we also proved that these two events are independent at least. Okay, yep. Now the real question is, are x and y independent? Like, so are the random variables independent? For random variables x and y to be independent, what should happen? All such combinations should be independent of each other. So like y being 2 should be independent of x being 1. Y being 2 should be independent of x being 2. And so on. Basically check everything. So we can do it quickly. So we already checked y being 2 independent of x being 1. Right. See, I will tell you a very quick way to do this. You already calculated the marginal probabilities, right? I will do that again here. Let me just copy it from here. 1 by 6, 3 by 8, 11 by 24. So for x being, so the marginal probability of x is 1 by 6, 3 by 8 and 11 by 24. This is basically the sum of first row, second row and third row. I have written the sum here. So this is the marginal probability of x, and here I am writing the marginal probability of y. So marginal probability of y we calculated to be 1 by 2, 1 by 4 and 1 by 4. This is the sum of columns. So I told you that independent events have one more property. One of them is this. There was another formula, right? When we rearrange it, we get probability of A intersection B is probability of A into probability of B. Right? This is the independence theorem, right? Like two independent events are independent if probability of their intersection is product of their individual probabilities. You can get this from this. We already did that. So basically what you need to check is this probability should be product of this and this. That's all, right? That's much easier to do, right? Instead of calculating the conditional probability every time, checking this is simpler. See, 1 by 12 is 1 by 6 into 1 by 2, correct? Which means that y equal to 2 is independent of x equal to 1. This is independent. Just check this product. Is 1 by 6 equal to 3 by 8 into 1 by 2? No. We found the example in just the second case, okay? What could have been the blunder? In this question, you might have made a blunder. You just check the first value. First value is correct, right? The first value here, this is the product of 1 by 6 and 1 by 2. So it makes y equal to 2 independent of x equal to 1. But it doesn't make y independent of x completely. For y and x to be independent, all these values should be product of these two values. But here, y equal to 2 is not independent of x equal to 2. Okay, this product is actually 3 by 16, which is not 1 by 6. Which means that I don't need to check all other values. I found one value, which means that random variables x and y are not independent. They are dependent. Only few combinations are independent of each other, but not all. So that's why x and y are not independent. Okay. Cool. And similarly, like in this example, they were independent. The entire events were independent. Why? So here also, if we do marginal probability, For x equal to 1, this will be 1 by 6. All of them will be 1 by 6. Or here the marginal probability of heads and tails will be 1 by 2 and 1 by 2. And all the values are product of these two values. You can check, right? Very simple. So here all events, all possible combinations are independent of each other. That's why the random variables are independent of each other. But in this case, they are not. Cool. So yeah, we will discuss some more problems on this, and we will see more like interesting applications of these topics that you have seen. So just remember the terms, okay? Marginal probability, conditional probability, and joint probability. We will use these terms in the next two lectures, which will be on total probability and Bayes theorem. Very important coming to probability.
Hi everyone, welcome to lecture number 7 of complete GATE data science course. We are discussing probability, and in this lecture we will see total probability. So far we have seen like basic concepts in probability like marginal probability, conditional probability, independent events, and how to link all of them. So this theorem, total probability, the law of total probability, will actually link or like join all the concepts that we have seen so far. So it will include some concepts of independent events, some concepts of conditional probability, and so on. So let's see how it is stated. So the law of total probability is a fundamental rule relating marginal probability to conditional probabilities. In the last lecture, we have seen what marginal probability is, right? So if there are two events, just the probability of first event. Okay, so if we have two random variables, just the probability of first random variable independent of it doesn't matter what the second random variable was. So we just join sum all the probabilities of second random variable and we get the first random variable. That is marginal probability, and it links marginal probability to conditional probabilities. What is conditional probability? Probability of event A given B has already happened. So it expresses the total probability of an outcome which can be realized via several distinct events, hence the name. So see, by the definition it will be not very clear what the law is, but when we see the formula and when we see some examples, it will be very clear. Okay, so it is much of like marginal probability only. Okay, I see total probability law. It actually calculates marginal probability. Okay, but here we are formulating it. We are giving it a formula. Okay. So let's see the motivation and let's see the formula. So if Bn, okay, Bn is a set of events. So if Bn, n is equal to 1, 2, 3, is a partition of the sample space. We know what is the sample space, it's the universe. Okay, so if you're performing any experiment, the sample space is the set of all possible outcomes that can happen. So let's say this is our sample space. Okay. Which is also the universe. So I can call it universe as well. So if Bn is a partition of the sample space, so it is a partition. Okay. So what happens is Bn is like B1, B2, B3, and so on. These are events. B1, B2, B3 are events, and they are the partition of the sample space, which means they are disjoint and they are mutually exclusive. Okay, they have nothing in common, and their union is the entire sample space S. That is what partition is. So for example, this is B1, this is B2, and so on. This is Bn. So our sample space is divided in n parts. They might or might not be equal, but yeah, they are disjoint. These partitions are disjoint. They have nothing in common between them. And their union is the entire sample space. Okay, they are disjoint and their union is the entire sample space. Then for any event A, okay, the probability of happening of event A. See, sometimes it is possible that probability of any event A is not very easy to calculate. With examples, it will be more clear. So you want to for example, like you are doing some experiment like throwing a die. We know that probability of getting a prime number, probability of getting an odd number is very simple. Okay, if event A is getting an odd number, probability of A is very simple to calculate. It is not dependent on any other event. But sometimes there will be two events and probability of event A given the other event is easy to calculate, but probability of event A itself is very difficult to calculate. That's when this law of total probability is used. Okay, so for example here, let's say this is our event A. Okay, this is our sample space. It has some partitions, n partitions, and this is our event A. Now, in so problem is formulated in such a way that probability of event A is not very obvious. Okay, you cannot calculate probability of A directly, but you can calculate probability of A given B1 has already happened. This is given, let's say. Somehow this is given, okay, and also probability of A given B2 has happened. This is also given. B1, B2, B3, Bn are also events, right? They are partition of the sample space. They can also be called as events. So probability of A given this, given Bn, these are given. Probability of A given Bn has already happened. So all these probabilities are already given, but probability of A is not given. That's what you need to calculate. Then law of total probability helps. Okay. So what law of total probability says? It says that probability of A is nothing but the sum of all probabilities, probability of A intersection Bn. What is it? So it's very obvious, right? So what is probability of A? It is probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection B3 and so on plus probability of A intersection Bn. It is intersection, not given, okay? It is not conditional probability, it is joint probability. It is joint probability, okay? Intersection is joint probability, A and Bn. So we just sum all these probabilities and we will get the total probability. This is what the law of total probability is. Very easy, right? So it is nothing but probability of A and B1 happened, comma is intersection only, plus probability of A and B2 and so on, plus probability of A and Bn. Okay. Now I told you, like, even this will not be given in the question. And generally, when total probability will be applied, even this intersection probability will not be given. The conditional probability will be given. Now we know that how to calculate conditional probability, how to calculate the joint probability given the conditional probability, right? So we know that probability of A given B1 is nothing but probability of A intersection B1 upon probability of B1. So generally in these cases, probability of B1, B2, Bn will also be given. Okay. So what we can do is we can write probability of A intersection B1 as probability of A given B1 into probability of B1. Multiplication theorem, right? We are just applying multiplication theorem. So probability of A intersection Bn is nothing but probability of A given Bn has already happened times probability of Bn. So this is the law of total probability. Okay, with examples it will be more clear. So let's see one example here. So I have 3 bags and each contain 100 marbles. So this is the configuration given. See, whenever you have question with n bags, urns, okay, so whenever you have question with bags containing marbles, it's better that you draw it. Then it will be much more clear. Okay, so you will have lesser chances of making mistakes in exam. So like just seeing this and solving, you might make mistakes in numbers. So it's better to draw the configuration, then it will be much more clear. Okay. So there is bag B1, which contains 75 red and 25 blue marbles. Then there is bag B2, which contains 60 red and 40 blue marbles. And there is bag B3, which contains 45 red and 55 blue marbles. Okay, all of them contain 100 marbles each. Now what is given? I choose one of the bags at random. You choose one of the bags at random and then pick a marble from the chosen bag. So there are 2 events happening. First, choosing a bag and then choosing a marble from that bag. 2 events, okay, A and B. Also at random, okay, so you are choosing marble also at random. What is the probability that the chosen marble is red? So we want to find the probability of the chosen marble to be red. It's not very straightforward, right? Here, like, because there are 2 events happening. First, you are choosing a bag and then from that bag you are choosing a marble. So here what happens? This is your sample space. These 3 bags are independent of each other. They are disjoint from each other. Okay. So this is bag B1, bag B2, bag B3. Only one of these 3 events can happen. When you are choosing a bag at random, you can choose bag B1 or B2 or B3, right? You cannot do anything else. And also you cannot choose bag B1 and B2 both, right? So you see here, right? There is like this question comes under total probability. Why? Because we have three events which are disjoint and their union makes the entire sample space, right? So basically they are the partition of the entire sample space. So you can either choose bag B1 or B2 or B3. Probability of choosing bag B1 is 1 by 3, B2 is 1 by 3 and B3 is also 1 by 3 because it is given that the bag is chosen at random. So probability of choosing any bag is 1 by 3. Now what happens? Now you take a marble out of that bag. You take a marble out of any bag which is chosen and you need to find what is the probability that the chosen marble is red. So this is our event, getting the marble as red. Right? You can get a red marble from B1 or B2 or B3. Right? And you need to find the probability of the chosen marble being red. So I told you, like when a question from total probability comes, it will be very clear. Okay, the same setup will be given. And if you notice, probability of B1 is given, B2 is given, B3 is given. Probability of the ball being red, given B1 is chosen, it is also given. It is very easy. Given that you have chosen bag B1, what is the probability of the marble being red? It is 75 upon 100, right? Given that you have chosen bag B1, if you pull a marble out of bag B1, what is the probability of it being red? 75 upon 100. Similarly, probability of the ball being red, marble being red, given bag B2 is chosen, is 60 over 100. And similarly, probability of marble being red, given the bag B3 is chosen, is 45 over 100. Right? So now what is the total probability? We need to find the total probability of getting a red marble. The total probability of getting a red marble is, so I'm not writing the entire formula, we are just using the second equation. So either you are getting the first bag, probability of getting the first bag, times probability of getting a red ball, given first bag is chosen, so 75 upon 100, plus probability of choosing the second bag, times in the second bag what is the probability of getting a red marble, plus probability of choosing the third bag, times probability of choosing a red ball given third bag is chosen. So what is this? It is 1 by 3 we can take as common, and in denominator we can take 100 as common. It is 75 plus 60 plus 45. So what is it? 105, 110, 180. Okay. So it is 3 by 5. So the overall probability of getting a red ball in this scenario is 3 by 5. It can come from bag B1 or B2 or B3, doesn't matter. The overall probability of getting a red ball is 3 by 5. Okay, or 0.6. See, you don't even need to think about the formula. So once you solve a lot of problems from total probability, you won't be thinking about the formula. Just by seeing the question, you will solve it. Okay, what is the probability of getting a red ball? At the end, either you choose the bag B1, what is the probability of bag B1? 1 by 3. Times, now if bag B1 is chosen, what is the probability of getting a red ball? 75 by 100. You will directly write it, okay, in the exam. You don't need to do this. Cool. So here is the both the versions of total probability. I have already given you this diagram, okay. So this is your sample space. And let's say we have 6 events in which we can partition the sample space: B1, B2, B3, B4, B5, B6. And the event A might have something in common with all these events. Then the probability of event A is nothing but probability of any event B times probability of A given B has already happened, and sum over all events. Similarly, like this law we will never use. Okay, basically this is like an extended version of total probability. What it says is like, now what if I want to find the probability of A given another event C has happened. Okay, let's say this is event C. Okay, it has nothing to do with the experiment, but yeah, like there is another event C which is given to have happened. Okay, it has already happened. You just apply C all the way in the equation. Okay, so it is probability of B given C has already happened times probability of A given C and B1 both have happened. Okay, we will never use this equation, but yeah, when we see an example it will be clear. Okay, but yeah, this is the most important version of total probability. Cool. Let's solve some problems from total probability. First is like very simple problem. Now let's say you roll 2 dice. Okay. What is the probability of getting a 2 on second die? Okay, it's very simple. We don't need to apply total probability here. We already know first dice is independent of second die. Okay, not exclusive, independent. So it doesn't matter what you get on the first die. Probability of getting a 2 on the second die is 1 by 6. We already know. But now let's say I forget about independence for 1 second. I want to apply total probability. What happens now? This is our sample space. Okay. So let's say I partition the sample space on the first die. So on the first die I can get, from the first die I can get a 1, 2, 3, 4, 5 or 6. Right. In the first die I can get 1, 2, 3, 4, 5 or 6. They are disjoint. I cannot get 1 and 2 both. They are disjoint. Now this is the second dice. Getting a 2 on the second die. This is our event. This is what I want to find. Okay. So you can get a 2 on second die and 1 on the first die. You can get a 2 on the second die and 2 on the first die. So it has intersection with any, like every one of them. So you can get it 6 on the first die and you can get a 2 on the second die. So that's what it is, right? So what is the probability of getting a 2 on the second die? It is probability of getting a 1 on the first die times probability of getting a 2 on the second die, given that you have a 1 on the first die. So it is again 1 by 6 plus probability of getting a 2 on the first die. So now we have solved this. Now we will solve this. 1 by 6 into 1 by 6. So you will have the same term repeated 6 times. So this sum will be nothing but 1 by 6. Okay. We don't need to apply total probability here because the events are independent. But in general, when this law is applied, the events will not be independent. So even if you forget about the fact that they are independent, if you like just apply the rule, you will get the correct answer. Okay. So the probability is 1 by 6. Now let's see another example. So just read the example and pause the video and try to solve it on your own. So I'll read it out for you. Suppose that 2 factories supply light bulbs to the market. Now factory X, there is a factory X and factory Y. Okay. Again, always draw. There is a factory X and a factory Y. So factory X's bulbs work for over 5,000 hours in 99% of cases. So in factory X, what happens? The chances of a bulb working for over 5,000 hours. The chances of working of a bulb for over 5,000 hours is 99%. In 99% cases, it works for over 5,000 hours. In factory Y, the bulbs work for over 5,000 hours in 95% of cases. So here it is 95%. Okay. Now it is known that factory X supplies 60% of total bulbs. Okay. So probability of a bulb being getting a bulb from factory X is given to be 60%. So similarly, from factory Y it is 40%. Okay. Now, what is the chance that a purchased bulb will work for longer than 5,000 hours? Interesting problem, and it's very obvious that it is from total probability, right? Why? We want to find the total probability of, so basically you are selecting any random bulb in the market. What is the chances that it will work for over 5,000 hours? So there are 2 cases. It might come from factory X or it might come from factory Y. So again, like very easy. This is our sample space. It might come from factory X or factory Y. It is our sample space. And this is the event that the bulb will work more than 5,000 hours. Okay. So a bulb might work for more than 5,000 hours given that it is from factory X or from factory Y. Both are given. So let's say this event is, let's say A. A is the event that a bulb selected at random works for more than 5,000 hours. So we are given probability of A given X. It is given, right? What it is? It is given to be 0.99. The chances of a bulb working for more than 5,000 hours given that it is from factory X is 0.99. It is given. Similarly, chances of a bulb working for more than 5,000 hours given that it is from factory Y
is 0.95. And also probability of x is given. Probability of x here is not 1 by 2, it is given to be 0.6. And probability of y is given to be 0.4. Just apply the law of total probability. What is the probability of event A? 0.6 are the chances of it be from factory x times 0.99 plus 0.4 times 0.95. I'm just applying the formula, okay? It can be from factory x times probability of it working more than 5000 hours given that it is from factory x plus similarly for y. So you just solve it, you'll get 0.974. Okay. So this is total probability. We have similar examples. Let's solve more examples, okay? So this is the second example. A person has undertaken a mining job. The probability of completion of job on time with and without rain are 0.42 and 0.9. So if the probability that it will rain is 0.5, then determine the probability that the mining job will complete on time. Okay, very simple. I will not draw the diagram this time, okay? We just want to find the probability of event A. A is mining job will be completed on time. What it is? There are two events given. It can rain or it cannot rain. So if it rains, the probability of raining is 0.45. Now if it rains, the probability of job getting completed is 0.42. If it rains, the probability of job getting completed is 0.42. And what is the probability of not raining? 0.55. See, the probability of raining is 0.45. Then probability of not raining is 0.55. 1 minus 0.45. So if it doesn't rain, now if it doesn't rain, what is the probability of the job getting completed? 0.9. So you just solve it, okay? You will get 0.684. You don't need to draw the diagram every time. It's very simple here, okay? If you need, I can draw it for you because it is just the second example. This is our sample space. It can be divided among, in rain and not rain. Probability of rain is given to be 0.45. Probability of not raining is given to be 0.55. And this is our event A. The event A is the job will be completed on time. So we are given probability of A given rains. Probability of A given rains is 0.42. And similarly, we are given probability of A given not rain. So I just applied the law of total probability. Okay, I hope it helps. Okay, like very standard problems. And GATE has asked a lot of questions on total probability. Okay, trust me, like at least one question is guaranteed from this topic. It is that important. So, and it will be very simple. Okay, once you solve too many problems, it will be very simple. Cool. Let's see one more example. Again, pause the video and try it on your own first. So bag A contains 2 green and 3 red balls. Bag B contains 3 red and 2 green balls. You draw a ball from bag A and place it in bag B. This is slightly different, okay? You draw a ball from bag A and place it in bag B. Then we draw a ball from bag B. What is the probability that this ball will be red? This is slightly different, okay? Here what we are doing, here we are taking a ball from bag A and placing it in bag B. So what happens? There is a bag A, there is a bag B. Bag A contains 2 green and 3 red balls. Bag B contains 3 red and 2 green balls. You draw a ball from bag A randomly and place it in bag B. Then you draw a ball from bag B. First you do this, then you do this. What is the probability that the second drawn ball, this, from the bag B is red? See, here, like it's not very different, okay? Like what we are doing, there are two events happening. First, we are taking this ball and placing it in bag B. There is a condition probability on this ball. Because if this ball is red, this bag will contain 4 red and 2 green balls, right? And if this ball is green, then now this bag will contain 3 red and 3 green balls. So the probability of this ball being red depends on what this ball was.
I hope you're getting it right. So what happens here? This is your sample space. It is divided in two pieces. The first half is that the first ball is green. First ball is green. And the second half is the first ball is red. They are disjoint and only one of these can happen. Ki first ball can be green or first ball can be red. And in any of these two cases, the second ball can be red. So this is our main event. The main event A is getting a red on the second ball. In a red ball from second bag. Let's call it R so that it will be more easier to interpret. Okay, let's say that the event is R, getting a red ball from the second bag. Now you can get a red ball from the second bag given that you had a green ball in the first bag, and also you can get a red ball from the second bag given that you had a red ball on the first bag, right? So it is clear, right? Like both these events can happen. So what is the total probability of the second ball being red? So firstly, let's say this case happens, that you get a green ball in the first attempt. So probability of getting a green ball, so let's say, let me call it this way. Probability of getting a red ball in the second attempt is probability of first ball being green times probability of second ball being red. Probability of second ball being red given that first ball is green, plus probability of first ball being red times probability of second ball being red given that first ball is red, right? Just applying total probability here. So first ball can be green or first ball can be red. Now if first ball is green, we know that what is probability of first ball is green. Like it's very simple to calculate, it's 2 by 5. So probability of this is very easy to calculate, it's 2 by 5 and this is 3 by 5. And also, now given that the first ball is green, probability of second ball is being red is also simple to calculate. If first ball is green, the configuration is what? 3 red and 3 green balls, right? If the first ball is red, if the first ball is green, the configuration of second bag will become 3 red and 3 green balls. Now the probability of red taking a red ball from here will be 1 by 2, right? 3 by 6. So this probability of the second ball being red given that the first ball is green is 3 by 6. Why? Because if first ball is green, the second bag becomes 3 red and 3 green balls. I hope this makes sense, right? Similarly, this probability also we can calculate. Probability of second ball being red given that first ball is red. So if first ball is red, the second bag B becomes what? Bag B will contain, you are basically taking a red ball and placing it here. So now this bag will contain 4 red and 2 green balls. This is the configuration. So now what is the probability of getting a red ball from the second bag? It is 4 by 6. So this we can calculate, this we calculated, this we calculated, this we know, this we know. Now we can apply the law of total probability. So I'll just write the values here. Probability of first ball being green is 2 by 5. 2 by 5 times 3 by 6 plus 3 by 5 times 4 by 6. So 3, 2, 6 cancels. 3, 4, 6 cancels and gives a 2 on the top. So it is 2 plus 1, 3 by 5. Okay, so there are 60% chances that the second ball is red. So it was conditioned on first ball. First ball could have been red or green. I hope this makes sense, okay? And more complicated questions can come, okay? You can have 3 bags now. Generally, GATE will not ask 3 bags, okay? Because it will be too long. Like the question will be too long to answer. So generally, you'll have questions which can be solved in 1 or 2 minutes. So this is the most complicated version that can come in exam. But I hope you understood, okay? And how total probability is applied here. Cool. Cool. So like this was the last question that we had. We will solve more questions on total probability in the next lecture. So this is an important concept that's why we will have more questions on total probability. So like next lecture also we will discuss total probability only. Hi everyone, welcome to lecture number 8 of probability under a GATE complete course, GATE data science complete course.
So in the last lecture, we discussed total probability, what total probability is. So probability of an event A, which is not very straightforward to calculate. We have a sample space which is partitioned into n events, B1, B2 up to Bn, and probability of A given B1 given B2 is easier to calculate, and also probability of B1, B2, B3 is given. Then what is probability of A? It is just the sum of probability of A given Bi times probability of Bi for all I from 1 to n, right? So we'll use the same law. This is the law, and solve a few more questions. It is very important coming to GATE exam. A lot of questions have been asked from total probability. So let's solve a few more questions. So in a bag, there are 3 balls. So it is a like slightly trickier question. Now we have already solved easier problems in the last lecture. In this lecture, we will solve a few advanced problems and GATE previous year questions. So just try to solve this question. In a bag, there are 3 balls. One of the ball is not known to be red. The probability of any of the other ball being red is 0.5. What is the probability that the randomly chosen ball from the bag will be red? Okay, so it's not very straightforward. So what it is given? So there are 3 balls in a bag. So this is our bag. There are 3 balls. First ball is given to be red. It is sure like to be red. So probability of this ball being red is 1. Then the other ball can be red or non-red. It can be red or any other color. But the probability of this ball being red is given to 0.5. And similarly for the third ball also, it can be red or not red. Probability of this ball being red is also 0.5. Okay. Now we choose a ball at random from this bag. So what is the probability that the chosen ball is red? So it can be this ball. If this ball is chosen, then the probability of this being red is 1. It is like it will surely be red. But it is not necessarily that we are choosing this ball only, right? The probability of this ball being chosen is only 1 by 3. With the other 2 by 3 probability, this or this ball can also be chosen. But if this or this ball is chosen, the probability of the ball being red is only 0.5. Okay, so it's very simple. Okay, total probability. So probability of the second ball being red is, so if you choose this ball, the probability of choosing this ball is 1 by 3. Now if you choose this ball, the probability of the ball being red is 1. If you choose the second ball, probability of choosing the second ball is 1 by 3. If you choose the second ball, probability of it being red is 0.5. So I'm not drawing the diagram, I'm directly applying the equation, okay? And probability of choosing the third ball is 1 by 3. And probability of getting a red ball given the third ball is chosen is 0.5. So it is 1 by 3 plus 1 by 3 times 1 by 2. So it's 2 by 3 times 1 by 2. So it's 2 by 3. Okay, so there are 2/3 chances that overall, if you choose a ball randomly from this bag, it will be red in color. Okay, if you want the diagram, I can draw it. So the entire sample space can be divided in 3 parts. You choose the first ball, you choose the second ball, or you choose the third ball. And this is our event, getting a red ball overall. So you can get a red ball given the first ball is chosen, you can get a red ball given the second ball is chosen, or you can get the red ball given the third ball is chosen. Probability of all these 3 is 1 by 3. Choosing the first, second or third ball. Now probability of red ball given the first ball is chosen is 1. Probability of red ball given the second ball is chosen. It's conditional, not joint. Okay, conditional probability. So probability of getting a red ball given the second ball is chosen, it is 0.5. And similarly for the third ball. Okay, so I just applied the formula and we get 2 by 3. Cool. So let's see one more example. A bag contains 4 fair and 3 unfair coins. Okay, simple again. I always draw. So a bag contains 4 fair coins. They are fair. Okay. What do I mean by a fair coin? Probability of it lending it heads is 1 by 2 and tails is also 1 by 2. And there are 3 unfair coins. There are 3 unfair coins. And it is given that probability of getting a heads on unfair coin is 1 by 3. So probability of getting a heads on unfair coin is 1 by 3 and tails will be 2 by 3. Right? Now a coin is drawn from the bag and tossed. A random coin is taken from the bag and tossed. What is the probability that it will land on heads. Okay. So again, like you don't need to draw the diagram every time. So you either can get a fair coin or an unfair coin. So the probability of getting a fair coin so basically you're taking a coin out and then tossing it. So when you're taking a coin out, you can get a fair or unfair coin. You don't know. Okay, you're choosing a coin randomly. So the probability of getting a fair coin is 4 by 7. Right? There are total 7 coins. 4 of them are fair. So probability of getting a fair coin is 4 by 7. So if you're getting a fair coin, given the probability of heads, given that you got a fair coin is what? 1 by 2. So this probability is probability of getting heads given that you chose a fair coin. Or you can get an unfair coin. Unfair coin, the probability is 3 by 7. Now probability of getting heads given that you got an unfair coin is 1 by 3. It is given to be 1 by 3. So this is the total probability. So this is 2, this is 1. So it's 2 plus 1, 3 by 7. So there are 3 by 7 chances that finally the coin will land on heads, and 4 by 7 that the chances that finally when you toss the coin it will land on tails. Okay, you can draw the diagram again. It's not required. The entire sample space can be divided into fair and unfair, and then you are tossing the coin. Okay. So there is another version of the same problem. So the same configuration is given, 4 fair and 3 unfair coins. And now 2 coins are taken out from the bag and tossed. Okay. So what happens? There are 4 fair and 3 unfair coins. And probability of getting a head from the fair coin is 1 by 2. Probability of getting a head from the unfair coin is 1 by 3. Now 2 coins are taken out from the bag and tossed. So nothing is given. So basically you're taking 2 coins. So they are not uniform. Okay. You're taking the first and second coin together. So both of them can be fair. One can be fair and one can be unfair. And both of them can be unfair coins. Right. So either one of these 3 cases can happen. So now what is the probability that both the coins will land on heads? That's what I need to calculate. So firstly, let's calculate what is the probability of getting 2 fair coins. So now we come to counting. Okay, in counting we have seen basically there are 7 coins, and in how many ways can we get both fair coins? So probability of getting both fair coins is what? So in overall, how many cases do we have? If we have 7 coins in a bag, in how many ways can I take out 2 coins? Okay, 7C2, right? And in how many ways both of them will be fair? 4C2, right? And similarly, we have 7C2 cases. In how many ways will be 1 fair and 1 unfair? So 4C1 into 3C1. Okay, so you take 1 fair and 1 unfair coin. So there are 12 possible cases. Similarly, when you what is the probability of getting both unfair coins? 3C2 over 7C2. Right? So if you want to verify that these numbers are correct, you can just sum the numerators. The sum of the numerators should come out to be the denominator, right? Because only one of these 3 cases should be can happen. Basically, the sum of these 3 probabilities should be 1. So what is 7C2? 7C2 is 7 into 6 over 2, which is 21. What is 4C2? 4 into 3 over 2, which is 6. What is 4C1 into 3C1? It is 4 into 3, which is 12. What is 3C2? 3C2 is 3 into 2 over 2, which is 3. So what is 12 plus 3 plus 6? That is 21. So right, yeah. Sum of the numerators comes out to be 21, which means only one of these 3 cases can happen. And we calculated the probability of each one of the configurations. Now, what is one of these 3 cases can happen. So in total probability terms, this is our sample space. Either you can get both fair, or you can get 1 fair, 1 unfair, or you can get both unfair. Now this is your event. What is the probability of getting both heads? Both of them landing on heads. So so let's call them like 3 events. Let the events be E1, E2 and E3. Now probability of both landing on heads is probability of event E1, which is 4C2 by 7C2, which is 6 by 21, times probability of both heads given both of them are fair. Probability of both heads given both of them are fair. So which is 1 by 2 into 1 by 2. Plus probability of one fair and one unfair coin, which is 12 by 21, times getting both heads given that one is fair and one is unfair. So on the fair coin, the probability of getting in heads is 1 by 2, and on the unfair coin, the probability of getting in heads is 1 by 3, plus if both of them are unfair, which means the probability is 3 by 21, times if both of them are unfair, the probability of getting both heads is 1 by 3 into 1 by 3. So you just need to solve this entire expression, okay? And you'll get 0.183. So there are 18% chances that both the coins will land on heads. Generally, like in GATE, you won't be asked this much complicated question, but yeah, if required, you can answer it, okay? It involves some concepts of counting and probability both, and it involves total probability as well. So this is how you solve it. Cool. So this is GATE 96 question. 2 dice are thrown simultaneously. The probability that at least one of them will have a 6 facing up is what? So you are throwing 2 dice simultaneously. So this is not necessarily from total probability, okay? It's very simple to calculate. You don't need to apply total probability here. It's just a previous year question. That's why I added it here. The probability that at least one of them will have 6 facing up is, okay? So you can actually enumerate all 36 cases, right? You can enumerate all 36 cases. So from 1, 1 to... Okay, so at least one of them having 6 facing up. So what are the total cases? So let's say the first dice is having a 6 on the top. So the second die can have 1, 2, 3, 4, 5, 6, anything. So this is the first die and this is the second die. Or you can have a second die facing a 6, and in the first die you can have anything from 1 to 6, right? But here we are overcounting one case. 6, 6 is present here also, and 6, 6 is present here also. So there are 6 cases here, right? 6, 1, 6, 2, up to 6, 6. And what are the cases present here? 1, 6, 2, 6, up to 6, 6. So I should not include 6, 6 again, right? I should not overcount it twice. So let me just add up to 5, 6 only, because I already added 6, 6 here. So what is the total number of cases? 6 plus 5, which is 11. So there are 11 cases in which you get at least one of them having a 6 facing up, right? So the total probability is 11 by 36. Okay, these are the 11 cases in which you get at least one 6. Cool. Now let's see this GATE 2007 question. Suppose there are 2 coins. The first coin gives heads with probability 5 by 8 when tossed. The second coin gives heads with probability 1 by 4. One of the 2 coins is picked up at random with equal probability. What is the probability of obtaining heads? Very simple question, right? And this is the simplest question which can be asked in total probability. There are 2 coins. One of them is chosen randomly at tossed. So choosing this coin, the probability is 1 by 2, and this coin also the probability is 1 by 2. If this coin is tossed, the probability of getting in heads is 5 by 8, and the tails will be 3 by 8. If this coin is tossed, the probability of getting in heads is 1 by 4, and tails it is 3 by 4. Now one of the coins is chosen randomly and tossed. What is the probability of getting heads? So if first coin is chosen, the probability is 1 by 2. And if first coin is chosen, the probability of getting in heads is 5 by 8. Plus, if the second coin is chosen, the probability of getting in heads given the second coin is chosen is 1 by 4. So this is the total probability of getting in heads, right? You can draw the diagram, and this is the first coin, this is the second coin, this is the probability of getting heads. Probability of getting the first coin is 1 by 2, second coin is 1 by 2. Probability of getting in heads given first coin is chosen is given to be 5 by 8, and probability of getting in heads given the second coin is chosen is 3 by 8, and I have just applied the law of total probability here, right? So what is this value? You can calculate it. So how to do this quickly? Make this also 8 and make a 2 above. So this will be upon 16, so it will be 5 plus 2 upon 16, so it is 7 upon 16. Cool. So this is the probability, total probability of getting in heads. So this is GATE 2019 question. 2 numbers are chosen independently and uniformly at random from a set 1 to 13. The probability that their 4-bit binary representations have the same most significant bit is. So this again need not be from total probability. Okay, so I just added this question to tell you that not everything is from total probability. Okay, so you just need to see the question and like understand what it is trying to ask. So two numbers are chosen independently and uniformly. What does uniformly mean? I told you if uniformly is written, it means that you choose the first coin, the first number and then put it back. Okay, there is no connection of the two numbers which you are choosing. You are not choosing, so if you are choosing 2 in the first go, you can again choose 2 in the second go. Okay, and trust me, I made this mistake in the exam, so it's like the simpler problem. See, the more difficult problem to solve is you are choosing a 2 and you are choosing another number, right? You are not putting it back. That is more difficult because that will involve combination 13C2, 6C2 and so on, right? But here there is no combination. It is written that the numbers are chosen independently and uniformly. Okay, so don't make this mistake. Now the probability that their 4-bit binary representation of the same most significant bit. Okay, so this comes under digital logic a bit, but yeah, like it's very simple to solve. So if you know binary representation, we know that 1 is what? 1 is 1. We know that 2 is what? 1 0. And 3 is what? 1 1. You know how to calculate binary, right? And we want 4-bit binary representation. So basically, the 4-bit binary representation of 1 is 0001, of 2 is 0010, 3 is 0011, 4 is 011100, and so on. 8 becomes 1000. This is 8, right? And 9 is 1001. So this is 1, 2, 3, 4. This is 9. Similarly, we are having up to 13. So 13 will be what? 8 and 4, 12 and 1, 13. Okay, this is 13. So these are all the numbers that we have. So basically, I should have 8 this side because we are having, it will be better if I have 7 here. 7 is 0, 1, 1, 1. 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. And we have up to 13, which is 1, 1, 0, 1. So these are all the numbers that we have. So, and two numbers are chosen independently and uniformly. So you choose one number, put it back and then choose another number. Okay, that is okay. So basically, these are independent events. These are independent events. So, and what is the probability that both the numbers chosen have the same most significant bit? See, all these numbers have the same most significant bit. So here the most significant bit is 0. Most significant bit is the leftmost bit. And for all these numbers, the most significant bit is 1. Right? So for all these numbers, the most significant bit is 0. For all these numbers, the most significant bit is 1. So there are, so 1 to 7, how many numbers are there? 7. And 8 to 13, how many numbers are there? 6. 8, 9, 10, 11, 12, 13, right? So there are 7 numbers which have 0 as the most significant bit, and you have 6 numbers which have 1 as the most significant bit. So what is the probability that both the numbers chosen have the same most significant bit? It is like somewhat related to total probability. How? So if you choose, so let's say this is set S1 and this is set S2. So basically the probability of getting same most significant bit is what? Same MSB is what? Probability of choosing the first number from set S1 times, now you need to choose the second number also from S1. So this is like probability of choosing first number from S1 times probability of choosing the second number also from S1 given that the first number was from S1. Right? Or probability of first number being chosen from S2 times probability of second number is also from S2 given that first number is from S2. Right? And since first and second numbers are independent of each other, this will be very easy to calculate. The probability of second number being from S1 given that first number is also from S1 is nothing but probability of second number is from S1. Right? Since these two events are independent, it is given to be independent. Right? So this will not have any impact. So what is the probability of first number being from S1? It is 7 by 13 times the second number is also from S1. given that the first number is found. So first number and second number are independent. It doesn't matter. So probability of second number being from the set S1 is again 7 by 13. Plus probability of first number being from set S2, it is 6 by 13. Now probability of second number also being from S2, given that first number is from S2. So they are again independent, so it is also 6 by 13. So you just calculate this. So it's 49 plus 36 over 169. You can calculate using calculator. Okay, you'll get 0.503. So there are around 50% chances that both the numbers will have same most significant bit. In the next lecture, we will see the most important theorem of all. It will combine everything that we have seen so far. It is the Bayes theorem, and that will conclude the basics of probability. Hi everyone, welcome to lecture number 9 of probability under GATE DA complete course. In this lecture, we will see Bayes theorem. It is one of the most powerful theorems in basic probability. It combines everything we have seen so far: condition probability, marginal probability. Like we will see some new terms called prior, posterior, and most importantly, the total probability. Okay, so we'll rearrange total probability in such a way that we will get what we want. Cool. So let's see the motivation behind this Bayes theorem. So I'm discussing a problem first, and then I'll tell you what the theorem is. So consider these 4 problems, okay? So there are 3 bags given. First bag A contains 2 red and 3 green balls. Bag B, 1 red, 4 green balls. Bag C contains 3 red and 2 green balls. So this is the configuration given. Bag A contains 2 red and 3 green balls. Bag B contains 1 red and 4 green balls. And bag C contains 3 red and 2 green balls. So all of them contains 5 balls each. First question is, find the probability of getting a red ball given bag A is chosen. Very easy problem. Probability of getting a red ball given that bag A is chosen. So from bag A, what is the probability of getting a red ball? It is 2 by 5. So very simple problem, right? So the probability is 2 by 5. Now second question is, find what is the probability of getting a red ball from bag A. So this is different. Okay, here what we want is, so basically like frame this question this way. A bag is chosen randomly and then a ball is pulled out. What is the probability that the chosen ball is red and the bag chosen is the first bag or the bag A? So here it is given. Given means condition probability. So here we wanted to find probability of A given red Here we wanted to find probability of red ball given A is chosen, which was 2 by 5. Here we want to find probability of getting a red ball from bag A, which means probability of getting a red ball and bag A is chosen. It is different from this, right? So what is this? So we know that probability of getting a red ball given that bag A is chosen is nothing but probability of getting a red ball and bag A upon probability of getting bag A. So probability of getting a red ball and bag A is probability of getting a red ball given that bag A is chosen times probability of getting a bag A. So it is 2 by 5 times, what is the probability of getting bag A? If one of the bag is chosen randomly, it is 1 by 3. So this probability is 2 by 15 and not 2 by 5. So just see the question carefully. From bag A, which means bag A is chosen and red ball is chosen. So this is intersection. And here given, so it was conditional probability. Right? Now third question is, what is the probability of getting a red ball overall? So you are choosing one bag and taking one ball out. What is the probability of getting a red ball? So this is total probability. So you can get it from the first bag or the second bag or the third bag. So total probability diagram, easy question to solve. So probability of getting bag A times probability of getting a red ball from bag A, which is 2 by 5. Plus probability of getting the bag B times probability of getting a red ball from bag B, which means 1 by 5. Plus probability of getting bag C times probability of getting a red ball given that bag C is chosen, which is 3 by 5. So it is 1 by 3, we can take common and denominator is 5. 3 plus 1 plus 2 is 6. So the total probability is 2 by 5. The total probability of getting a red ball is 2 by 5. right? Cool. So now, so this was up till total probability. These all three things we have seen already, right? Now the question is, what is the probability that bag A was chosen given that the red ball is drawn? So this is like a reverse. This is reverse engineering, right? This is like it is given that you choose a bag and then a ball is drawn from that bag, and it is given that this drawn ball is red in color. What is the probability that it came from bag A? See, it might have came from bag A or B or C. So if I see the total probability diagram, there were three events which can happen. You could have got bag A or B or C, and this was the probability of getting a red ball. So you can get a red ball from bag A or from bag B or from bag C. Now it is given that this happened. It is given that red ball came out. What is the probability that it came from bag A? So it is like reverse probability. It is probability of bag A was chosen given that the drawn ball was red. This we have not seen so far. Right? We have not calculated this probability so far. We know how to calculate the total probability of getting red ball. We know the reverse of it. See, you will always apply Bayes' theorem when you know the reverse probability. So like probability of A given B is wanted, but you will always know probability of B given A. In such cases, generally Bayes' theorem is what will be applicable, okay? And the setup is of total probability. So we want the like probability of bag A given red ball is chosen, right? So this is the motivation. Now let's see the formula first, and then we will solve this problem. So this formula is taken from Wikipedia. Like, so the Bayes' theorem is mathematically stated as the following equation. So what we want is, we want probability of A given B has already happened, but we don't have this information. But we have the reverse information. We know what is the probability of B given A has happened. That is easier problem. So this, so we know that this is what? This is probability of A intersection B upon probability of B, right? And we can write probability of A intersection B as like the reverse probability. It can be written as probability of B given A times probability of A. Right? This can be written as this multiplication theorem. So now we are not resolving it as probability of A given B, but we are resolving it as probability of B given A. So this is the equation. So this is what the Bayes' theorem is. Here A and B are events, and probability of B cannot be 0. If probability of B is 0, this will go to infinity, right? So probability of B cannot be 0. Now there are few terminologies. Probability of A given B is the condition probability. This is what we want to calculate. We know that this is condition probability. The probability of event A occurring given that B is true. It is also called the posterior probability of A given B. This is called the posterior. This is what we want to find. What happens next? What is the posterior probability of A given B has already happened. Probability of B given A is also a condition probability. This is also a condition probability. This is probability of B given that A is true. And this can also be interpreted as the likelihood of A given f fixed B. So this is also called like the likelihood of A. So these are just terms, okay? So this is posterior of A given B has already happened. This is the likelihood of A. And probability of A and B are the probabilities of like the events A and B separately. Okay, they are marginal probabilities of A and B without any given conditions. They are also called marginal probability or the prior probability. So these are called marginal probabilities or the prior probabilities. So probability of A given B, the posterior probability of A is the likelihood of A times marginal probability of A upon prior probability of B. Okay, don't go too much into the terminology. Okay, I'm giving the terminology just for the sake of completeness. Okay, the naming convention is not required, but I hope you understood the formula at least, right? So this is what the formula is. Now let's get back to the question that we had in hand. The probability of bag A is chosen given that the ball drawn is red. So it's very simple now, okay? And also see, the first few questions in every equation you will need to solve using the formula. After that, it will be so obvious, you will not write the formula even, okay? You will just directly write the expression and solve it. So what is the probability that bag A is chosen given that the ball drawn is red? It is probability of getting a red ball given that bag A is chosen times, okay, yeah, times the probability of A, which is probability of getting bag A, upon the total probability of red ball being chosen. So in the denominator in Bayes theorem, in the denominator you will have the total probability always. The total probability of event R, getting the red ball. Okay? And in the numerator, we have the condition probability of getting the red ball from A times probability of A. See, it is very intuitive also. I'll tell you the intuition behind it. So what happens here? See, this was our sample event. Our sample event was, this is our sample space, and we could have got bag A or B or bag C. This is the probability of getting a red ball. Now red ball could have been gotten from bag A or from bag B or from bag C. The total probability of getting a red ball was what? It was sum of the probabilities that it could have been gotten from bag A or bag B or bag C. So the contribution of bag A was what? Probability of bag A times probability of getting a red ball given that bag A is chosen in the total probability formula. Probability of red ball is probability of A times probability of red given bag A is chosen, plus the contribution of bag B only was what? The contribution of bag B was probability of getting bag B times probability of getting a red ball given bag B is chosen. And the contribution of bag C was what? Probability of bag C times probability of getting a red ball given bag C was chosen. And we sum all these three and we get the total probability of red ball. Now the reverse question is, what is the probability that bag A was chosen given that the ball drawn is red? It is what? Just take the contribution of A. We don't want the contribution of B and C. What is the probability that bag A is chosen? So the contribution of A is this expression. So it is this expression upon the total probability. This plus this plus this. See, there were three contributions, C1, C2, C3. The overall probability of getting bag A given red ball is chosen is what? Just the contribution C1 upon C1 plus C2 plus C3. Okay. So just sum C1 plus C2 plus C3, which is nothing but probability of getting red ball, the total probability of getting red ball. So it is intuitive also. Okay. Bayes theorem is not just the formula, it's like the intuition behind it. That's what you need to understand. So it is the contribution of bag A in the total probability of getting red ball upon the total probability of getting red ball. Cool. Let's solve some. So we can solve this as well. Like, what is the probability of getting a red ball? See, this is the contribution of the first bag, right? This is the contribution of bag A. This is the contribution of bag B. This is the contribution of bag C. So the probability of it coming from bag A is what? This one. So this upon this total sum. So with the formula also, we'll get the same thing. Probability of getting red ball given bag A is chosen is what? It's 2 by 5 times probability of choosing bag A is 1 by 3 upon the total probability, this plus this plus this, which is 2 by 5. So it is 1 by 3. Okay. Cool. So let's solve a few more questions. It will be more clear. So this question we have already seen in total probability. Okay. Up to this part, we have seen this question in total probability lecture. Now one more question is introduced, which is from Bayes theorem. So again, two factories supply light bulbs to the market. There is a factory X, there is a factory Y. The probability that the factory X's bulbs work for over 5,000 hours is 99% cases. So the probability that a bulb will work for more than 5,000 hours given that it is from factory X is 0.99. So it is working for more than 5,000 hours. Given that it is from factory X, it's 0.99. Similarly, the probability of the bulb working for more than 5,000 hours, given that it is from factory Y, it is given to be 0.95. And it is given that factory X supplies 60% of total bulbs. So probability of X is 0.6. And it is given that Y supplies 40% of the bulbs. So probability of Y is 0.4. So what is the probability that a randomly chosen bulb will work for longer than 5,000 hours? So it is just the total probability that, so let's say that, let's name this event something, okay, it is very long event, that the purchased bulb will work more than 5000 hours. Let's say this event is anything, let's say it is T, which denotes total probability, okay. So probability of event T is what? There are 60% chances that you get it from the factory X times 99% chances that given that it is from factory X, it will work for more than 5000 hours, plus from factory Y 0.4 times the condition probability is 0.95. Okay, so which is, we solved it before, you can calculate it. Okay, I am not calculating it again. So this is the total probability of event T. Cool. This is the total probability of event T, which is the probability of a given bulb which will work for more than 5000 hours. Now the question, reverse engineering question, the Bayes theorem question is what? Given that the purchased bulb worked for more than 5000 hours, given that T happened, what is the probability that it was produced by factory X? See, this formula was nothing but total probability was probability of choosing factory X times probability of it working for more than 5000 hours given factory X is chosen, plus probability of factory Y times probability of working for more than 5000 hours given that Y is chosen. Now the question is, what is the probability that factory X, that the bulb was from factory X given that it worked for more than 5000 hours? It's the reverse question. I told you Bayes theorem will be applied when you know the answer to the reverse question, like the probability of T given X is known, right? So it is nothing but, see, in the total probability of a bulb working for more than 5000 hours, this was the component of X, factory X, and this was the component of factory Y. So it is just this upon this entire thing, right? And you can apply the formula also, you'll get the same thing. It is probability of X times probability of T given X upon probability of T, right? So it will be 0.6 times 0.99 upon 0.6 times 0.99 plus 0.4 times 0.95. Okay, so the answer to this question is just the total probability. It will be it will come out to be 0.974. So this thing is 0.974. This we solved in total probability also. Okay, so this denominator is 0.974. Now you can solve, if you solve this denominator, it will come out to be 0.61. Okay, so this is the condition probability that the bulb was from factory X given that it worked for more than 5000 hours. Cool. Now let's see one more question. A person has undertaken a mining job. The probabilities of completion of job on time with and without rain are 0.42 and 0.9. If the probability that it will rain is 0.5, then determine the probability that the mining job will be completed on time. This question again we have seen in total probability, but the main question that we need to solve is what is the probability that it didn't rain given that the mining job is completed. So let's solve it. So there are two cases given, that it rains and it doesn't rain. The probability that the job will complete on time with rain is 0.42. So this is the probability that the job will be completed. Let's say the job is completed is J. The probability of the job being completed given that it rains is 0.42 and given that it doesn't rain is 0.9. And it is given that the probability that it will rain, probability of rain is given to be 0.45 and probability of not raining is 0.55, 1 minus 0.45. So what is the total probability that the job will be completed on time? The probability of job will be completed on time is probability of raining times probability of job being completed given that it rained plus probability of not raining times probability of job being completed given that it didn't rain. Total probability is simple now, right? So it is 0.45 into 0.42 plus 0.455 times 0.9. Right? So this will come out to be 0.684. Cool. Now what we want? We want probability of not raining, probability that it didn't rain given that the mining job is completed on time. So probability of didn't rain given that the mining job is completed. Now this will apply Bayes theorem. So the contribution of not raining was this much. Probability of raining was this much. So the contribution of raining was this much, not raining was this much. So the answer to this is this upon this entire thing. So it is 0.55 into 0.9 upon the total probability, 0.684. You can apply the formula also. Probability of n given j will be probability of n times probability of j given n upon probability of j, which is this thing. So if you solve this, it will come out to be 0.724. Okay, there are similar questions like always you will need to calculate the total probability. From the total probability, it will be very clear. So let's see one more question. Bag A contains 2 green and 3 red balls. Bag B contains 3 red and 2 green balls. You draw a ball from bag A and place it in bag B. Then we draw a ball from bag B. What is the probability that the chosen ball is red? Again, we have seen this problem in total probability. But the amazing question is, what is the probability of getting a red ball in the first draw, given that the ball we got from the second draw is red? Okay, it's the most complicated probability question which can happen here. Okay, so what they are saying? So this is bag A, and it contains 2 green and 3 red balls. And there is bag B, which contains 3 red and 2 green balls. Now you draw a ball from bag A and place it in bag B. Then you draw a ball from bag B. After this, you do this. Then, so the second question is, what is the probability that the first draw gave you a red ball, given that the second draw gave you a red ball? So it is given that this particular event gave you a red ball. Then what is the probability that this event was also a red ball? Okay, so firstly, let's solve the first part of the problem. What is the total probability of ball being red? What is the probability that the second ball is red? It is probability that the first ball is red times probability that the second ball is red, given that the first ball is red, plus probability of first ball being green times probability of second ball being red, given that the first ball is green. Right? So this you already seen. What is the probability of first ball being red? It is 3 by 5 times what is the probability of second ball being red, given that the first ball was red. If the first ball was red, then the configuration changes. If the first ball was red, then you will have 4 red and 2 green balls. So the probability of second ball being red is 4 by 6. Plus, what is the probability of first ball being green? It is 2 by 5. Times, what is the probability of second ball is red, given that the first ball is green? It is 3 by 6. Okay? You can solve this equation, you will get 3 by 5. Now the question that is asked is, the second part is, what is the probability that the first ball is red? So this is what is asked. What is the probability that the first ball is red, given that the second ball is red? Okay, it's the reverse question. We know this part. So again, this is the contribution of first ball being red in the total probability of second ball being red. And this is the contribution of first ball being green in the second ball being red. So it is this contribution upon the total sum. So it is 3 by 5 into 4 by 6 upon 3 by 5. So you get 2 by 3. Okay, there is some mistake in the answer. So it is, so what is the probability that the first ball is red, given that the second ball is red? So firstly, let's see if this is correct. Okay, 2 by 3. So it is 2 by 5 plus 1 by 5. So it is 3 by 5. So this answer is correct. Now, what is the probability of first draw gives you a red ball? So first ball being red is this component. So it is 3 by 5 into 4 by 6 upon 3 by 5. So it is 4 by 6. Okay, it has to be 2 by 3. And we can calculate the other way around also, just to be sure. What is the probability of first ball being green given the second ball is red? So it will be 2 by 5 into 3 by 6 upon 3 by 5. So it will be, so 3 and 3 will cancel, 5 and 5 will cancel. So it will become 1 by 3. Yeah, correct. So the answer is 2 by 3, okay? I hope you got it, right? So again, Bayes theorem, very basic, but you just need to see the contributions. So just go with the intuition, not always go with the, again, if you apply the formula, you'll get the same thing, right? If you apply the formula, you'll get this thing upon the probability of SR. Cool. Let's solve one more problem. In a bag, there are 3 balls. One of the ball is known to be red. The probability of any other of the balls being red is 0.5. What is the probability that a randomly chosen ball from the bag will be red? And the second question is, what is the probability that all balls in the bag were red, given that a randomly chosen ball from the bag is red? So first part we have seen in previous lectures, in the total probability lectures. So there are 3 balls in a bag. This is your bag. One ball is known surely to be red. This is red with probability 1. The other ball can be red or non-red. The probability of red is given to be 1 by 2. And the third ball can be red or non-red. The probability of it being red is given to be 1 by 2. So what is the probability that a randomly chosen ball is red? Probability of a randomly chosen ball is red is, so let's say this is the first ball, this is the second ball, this is the third ball. So it is probability of first ball times probability of getting a red ball given the first ball is chosen, plus probability of getting a second ball, plus probability of taking the second ball, okay, times probability of getting a red ball given the second ball is chosen, plus probability of getting the third ball times probability of getting a red ball given the third ball is chosen. So it is 1 by 3 times 1 plus 1 by 3 times 1 by 2 plus 1 by 3 times 1 by 2. So it is 1 by 3 plus 1 by 3, which is 2 by 3. Now what we want? See, this is not very simple question. So if you do it this way, now what is the second question? So first part of the question is answered. It is just the total probability of getting a red ball. The second part of question is, what is the probability that all the balls in the bag were red? That all the balls in the bag were red, given that the randomly chosen ball is red. See, this is like, we cannot calculate it using this mechanism. Like if in this setup, in the setup which we draw for total probability, we cannot calculate this. What we want is probability that both the remaining balls are red, given that the chosen ball is red. We don't have this probability that both the probabilities are red here in this expression. Here we only have first ball, second ball and third ball. Right? We need to change our total probability in such a way that we can calculate this. See, this is also correct. Right? But here the partitions that we made were first ball, second ball and third ball. Instead, we have to make the partitions in such a way that the remaining 2 balls are both red, one is red and one is not red, and both are not red. If we make the partition that way, then we will be able to solve this problem. So let's solve the problem. I will rewrite the total probability, okay? So this is slightly non-intuitive, okay? So I will just write the sample space like this. That both the balls are red. Both the unfair balls, basically. We are only talking about the like non-red balls, like those which have a probability of 1 by 2. We know that this ball is anyway red, right? So I'm only talking about these 2 balls, second and third ball. So both of them can be red, or we can partition it in 4 ways. So this is our sample space. I'm partitioning it in 4 ways. How? That the second ball is red and the third ball is red. The second ball is not red, the third ball is red. The second ball is red and the third ball is not red, and second and third both balls are not red. Right? These are the configuration of second and third balls. First ball is known to be red, right? We don't have to do anything about it. So this is the overall partition now. This is like a new partition. And here also we have the same event R, getting a red ball in a randomly chosen configuration, right? So what is the probability of getting a red ball? It is probability that both the balls are red, which is, this is also red, this is also red. So 1 by 2 times 1 by 2. So it is 1 by 4. 1 by 4 times. So if this is also red, this is also red, what is the probability of getting a red ball overall? So it is 1 into 1 into 1, right? So if all the 3 balls are red in color, what is the probability of getting a red ball overall? It is 1, right? Plus. Okay. What is the probability of this thing? See, actually we don't need to calculate this thing. We can apply the formula now directly. Okay, what you can do is, we know that probability of red is 2 by 3. We already calculated it using other way, right? Calculating this probability using this way will be difficult. Okay, it's an amazing question. See it this way. Probability of getting a red ball using this way would be what? Probability that second and third balls are red times probability of getting a red ball given that second and third balls are red, plus probability that second ball is red. Probability that second ball is not red and third ball is red times probability of red given that second ball is not red and third ball is red. See, this probability is not very straightforward, right? How will you calculate this? Probability of getting a red ball given that this is red and this is not red. This again we will need to calculate in a complicated way. See, this again you will need to calculate, like you can get the first or second or third ball. Okay, this is not straightforward. So in this question only, the total probability has to be calculated using the first way, right? The standard way, like the first, second and third ball. Only this part we know. This part is easier to calculate. Instead of calculating the total probability using this configuration, just calculate this part, because this is the part that we require when solving the question. So what is the probability of getting a red ball? Like what is the probability of getting of first ball, second ball being red and third ball being red? It is 1 by 2 into 1 by 2. And now what is the probability of getting a red ball given that the second and third both balls are red in color? It is 1, right? Because if this happens, all the balls will be red. So if you take out any ball, it will be red in color. So just this probability is 1 by 4. Right? So now what we want to calculate that what is the probability that all the balls are red, which means second and third are also red. Given that red ball is chosen, it is nothing but this thing, which is probability of both balls being red times probability of getting a red ball given all the balls are red upon the total probability of getting a red ball. This we already calculated to be 2 by 3 using the other way. So this is nothing but 1 by 4 over 2 by 3. So it is 3 by 8. Right? Amazing question. You have to calculate the total probability using other formula and you have to calculate this probability using the standard way. Okay? So there are two partitions that we created. Cool. So these were a few questions from Bayes theorem. In the next lecture, we will again solve a few problems on Bayes theorem. It is not over yet. And we will see some previous year questions also which have been asked on Bayes theorem. It's a very important theorem and a lot of questions have been asked in GATE exam. Hi everyone, welcome to lecture number 10. This is the last lecture of basic probability under GATE data science and we will continue Bayes theorem. So we have seen the theorem, we have solved a few problems under this category in the last lecture. We will just solve a few more questions and previous year questions and yeah, like discuss more about Bayes theorem. So like just to discuss the theorem, we need to find the probability of A given B, but this is not very easy to find. So what we do is we just find the contribution of B in the probability of A. So it's like what? It's probability of B given A has already happened times probability of A upon probability of B. Right? This is what Bayes theorem was. So like we will discuss more questions on this. So a bag contains 4 fair and 3 unfair coins and probability of heads for any unfair coin is 1 by 3. A coin is drawn from the bag and tossed. What is the probability that it will land on heads? This is the first part. This is from total probability. Now let's say you tossed a random coin from the bag and it landed on heads. What is the probability of the coin which you tossed was fair? So it's an easy problem. Bag contains 4 fair and 3 unfair coins. Probability of heads in a fair coin is 1 by 2. Probability of heads in an unfair coin is given to be 1 by 3. Now you took out a coin at random and tossed it. What is the probability of it being landing in heads? It is probability of you taking a fair coin times probability of getting an heads in a fair coin plus probability of you getting an unfair coin times probability of getting an heads on an unfair coin. So it is 4 by 7. 4 by 7 is the probability of getting a fair coin, right? 4 by total coins are 7. Times probability of head given fair coin is tossed 1 by 2. Probability of getting an unfair coin is 3 by 7 times probability of getting a heads in an unfair coin is 1 by 3. So this is 2 by 7 plus 1 by 7. which is 3 by 7. So this 2 by 7 is the fair coins part and 1 by 7 is the unfair coins contribution, right? Fair coins contribution is 2 by 7, unfair coin contribution is 1 by 7 in the total probability. Now what we need to calculate, what is the probability that you got in fair coin? Given that you landed on heads, it is just the contribution of heads of the fair coin upon overall total probability, which is 3 by 7. So it is 2 by 3, right? You can apply the formula also. It will be this term upon the probability of heads. So you'll get 2 by 3. Cool. Let's see the next problem. There are 3 bags and they all contain white and black balls. First bag contains 3 white and 2 black balls. The second contains 2 white and 3 black balls. And the third bag contains 4 white and 1 black ball. Without any biasing, one urn is chosen and one ball is chosen randomly and it turned out to be white. What is the probability that it came from the third urn? Okay. So there are 3 bags. Bag B1, it contains 3 white and 2 black balls. There is bag B2, it contains 2 white and 3 black balls. And there is bag B3, it contains 4 white and 1 black ball. Without any biasing, you choose a urn and choose an urn and take a ball out of it, and this ball comes out to be white. So what is the probability that it came from the third bag? So you just need to calculate the probability of third bag given the chosen ball is white. So it is nothing but probability of getting a white ball given the third bag is chosen times probability of third bag being chosen upon probability of overall probability, total probability of getting a white ball. So it is probability of getting a white ball from the third bag, which is 4 by 5, times probability of choosing third bag, which is 1 by 3, upon total probability. So this is just the contribution of third bag. What are the total contribution of the first bag? It is 3 by 5 into 1 by 3. Plus from the second bag, the contribution is 2 by 5 into 1 by 3. And for the third bag, the contribution is 4 by 5 into 1 by 3. Okay, so this is our formula. Here I didn't calculate total, I calculated the total probability here itself. Okay, I didn't write the overall formula. So this is how we calculated. So here 1 by 3, 1 by 3, 1 by 3 gets cancelled. And the denominator 5, 5, 5 gets cancelled. So you'll get 4 over 4, 5, 6, 7, 8, 9, 4 by 9. Okay, so this is the probability of third bag being chosen given that the ball was white. Cool. So this is GATE 2016 question. A box P has 2 red balls and 3 blue balls. So there is a box P. It contains 2 red balls and 3 blue balls. And there is a box Q. It contains 3 red balls and 1 blue ball. Okay. A ball is selected as follows. So there is a system given. So firstly you select a box at random. No, it is not like uniformly random. It is given that the probability of getting a box P is 1 by 3 and getting box Q is 2 by 3. Okay. So you first select a box and then you choose a ball from the selected box such that each ball in the box is equally likely to be chosen. So the probability of selecting box P is given to be 1 by 3. And probability of selecting box Q is given to be 2 by 3. Okay. Now, given that the ball selected in the above process is red ball, given that the final ball is red, what is the probability that it came from box P? Okay. So we want to find the probability that it came from box P given that the red ball is chosen. So it is nothing but probability of getting a red ball from bag P times probability of getting bag P upon overall total probability of getting a red ball. Right? It's very easy. From the question now, it is like obvious that it is Bayes theorem, right? Because we know the total probability of red ball. But now it's the reverse engineering problem. Given that the ball is red, what is the probability that it came from bag P? So it is just the contribution of bag P, which is this. So it is probability of getting a red ball. Given that bag P is chosen, it is 2 by 5. So it is 2 by 5 into probability of choosing bag P, it is 1 by 3 upon The total probability of red ball is you can get it from back P or back Q. So firstly, for back P, the chances are 2 by 5 into 1 by 3, plus for back Q, the chances of getting a red ball is 3 by 4. So 3 by 4 times the chances of selecting back Q is 2 by 3. So this is your answer. You can like calculate it. So it is 2 by 15 upon 2 by 15 plus 1 by 2. So it is nothing but 2 by 15 upon. So how to calculate this? Make this also, so like make everything 30 in the denominator. So it will become 4 plus 15 over 30, and this will be 4 by 30. So this is nothing but 4 over 19. So the required probability is 4 over 19. Okay. So now let's see this question. Beautiful question from GATE 2021. They tried to make it using like computer networks, but yeah, it's not required. It's just a problem from Bayes theorem. So a sender S transmits a signal which can be one of the two kinds, H and L. So probability of the signal being H is given to be 0.1, and probability of the signal being of kind L is 0.9. In a graph below, the weight of the edge UV, the weight of edge, let's say HH, is the probability of receiving V when U is transmitted. So probability of receiving H given H is transmitted is 0.3. Probability of receiving H given L is transmitted is 0.9. Probability of receiving L given H is transmitted is 0.7. And probability of receiving L given L is transmitted is 0.2. So this, like, how do you interpret it? Given that it is given that probability of H is 0.1, it is given that probability of L is 0.9. Now probability of receiving H given H is transmitted is 0.3 from the weight of the graph, and probability of receiving H given L is transmitted is 0.9. Probability of receiving L given H is transmitted is 0.7, and probability of receiving L given L is transmitted is 0.2. This is what is given. Okay. Now, for example, so this is the same example. Now, if the received signal is H, it is given that the received signal is H. Okay, so basically this is like received given send. Okay, you can add R and S here as well. So it's better that we add R and S. So this is probability of send H, S, S. This is sent. This is received given sent. This is received given sent. Received given sent, received given sent. Okay. Now it is given that the received signal is H. What is the probability that the transmitted signal was also H? So you have to find the probability of transmitted signal being H, given that the received signal is also H. Okay. So you are given the final total probability that the received signal is given to be H. So it now is from Bayes theorem, right? We don't know this, but we know the reverse of this. We know the reverse of this, right? We know probability of HR given HS. So it is from Bayes theorem. It is nothing but probability of received signal being H given the transmitted signal is H times probability that transmitted signal is H upon the total probability of received signal being H. So it is nothing but probability of this is given to be 0.3. So 0.3 times probability of send signal being H, 0.1, upon what is the total probability of received signal being H? It is for the received signal to be H, the transmitted signal can be H or L, both. It can be H or L. So it is probability that the transmitted signal is H times the sent signal is H times this probability that the received signal is H given the transmitted signal is H. So it is 0.3 plus, if the transmitted signal was L, the probability is 0.9. If the transmitted signal is L, what is the probability that the received signal is H? It is again 0.9. Okay, I might have probability that the received signal is H given that the transmitted signal is L. It is 0.8. Okay, it's not 0.9, it's 0.8. So it is 0.8 here. So this is our expression. Okay, I just applied Bayes theorem. So it is 0.03 upon 0.03 plus say 0.722. So it is 3 over 75. You can calculate it and you have to round it to 2 decimal places. You will get 0.04. Okay. So that's how you do it. Cool. So this question is from GATE 2016. Suppose that a shop has an equal number of LED bulbs of 2 different types. Okay. The probability of an LED bulb lasting for more than 100 hours, that given that it is of type 1 is 0.7 and given that it is of type 2 is 0.4. The probability that an LED bulb chosen uniformly at random lasts more than 100 hours is. Not every question is from Bayes theorem. Read the question carefully. What is given? There are 2 types of bulbs, T1 and T2. The probability that it will last more than 100 hours, probability that it will last more than 100 hours, given that it is from T1 is 0.7. And probability that it will last more than 100 hours, given that it is from type 2 is 0.4. Now, an LED bulb is chosen randomly at random, okay? And it is given that there are equal number of 2 types of bulbs. So, probability of type T1 is 1 by 2 and type T2 is also 1 by 2. Okay, so what is the probability that a randomly chosen bulb will last more than 100 hours? So it can be from type T1 times probability that it will last more than 100 hours given that it is from T1 plus probability that it is of type T2 times probability that it will last more than 100 hours given that it is of type T2. This is the overall probability of lasting more than 100 hours. So it is 1 by 2 times 0.7 plus 1 by 2 times 0.4. Okay. It is 1.1 upon 2, it is 0.55. Okay, this is total probability question only. Had it been the question be like this way, ki, given that a randomly chosen bulb, LED bulb lasts more than 100 hours, what is the probability that it is of type T1? Then it is Bayes theorem, then it would have been this thing upon 0.55, right? So now you got it, right? Like just read the question carefully, what it wants, and you'll be able to do it. Cool. So this problem, consider it as an homework problem. I'll not solve it here right now. We will have discussion sessions live and I will solve it here. It's an amazing problem of Bayes theorem. Read it carefully, try to solve it, and don't look up internet, try to solve it on your own. Okay, it's a beautiful problem and we will discuss it, okay, in the discussion session. So I'll just take a screenshot and try to solve it. And it involves all the concepts that we have seen so far and we will solve it, okay. Cool. So thanks a lot. We have discussed like all the basic probability, axioms, theorems, everything. Now we will go deep into random variables, statistics, which are part of GATE DA course. Thanks a lot. Bye.